Hello, everyone. A very good morning to you all if you're on the west coast of the United States, which is where I'm located. But good afternoon, good evening, good night, depending on where you are joining us from today. First off, I want to take a moment and extend my deepest condolences to everyone that has been affected by the war. My sincere thoughts and prayers with them. I hope things get resolved soon, and hopefully, this needless loss of life can be put to an end soon. With that, I want to welcome you all to the second annual Cisco Research Quantum Summit. Building on the success of the first ever Quantum Summit that we held last year, we are continuing this year with a very fresh set of talks and speakers in various areas of quantum technology. It's going to be super exciting, I promise. We also have a great lineup of speakers from within Cisco to showcase some of the key innovations that are happening both in my group, that is Cisco Research, as well as other business units within Cisco. Obviously, programs like these don't automatically just happen. It requires a lot of coordination and getting together a lot of people. I really want to thank Carla Lee in my team, Janine Godfrey, Cisco TV folks who have been hosting the entire production, the Cisco Quantum Research team, our collaborators from across Cisco, and last but not the least, the entire set of speakers who have graciously made themselves available to make this exciting event happen. And without you all, this event would not be possible. So a really big thank you to all. Just want to say that Cisco Research is nested within an organization called Outshift within Cisco. And Outshift is really the incubation and innovation arm of Cisco and is responsible for creating and pursuing new and emerging market opportunities for Cisco. And Cisco Research actually partners with Outshift to bring many of the research ideas to life, along with other BUs as well, especially in cutting edge areas such as AI, ML, quantum, and so on and so forth. So what better way to understand this synergy than to have the leader of Outshift himself spend a few minutes talking about this directly? So without further ado, it's my great pleasure and honor to invite our SVP of Outshift, a chief outshifter as we call him, Bijoy Pandey, to share a few thoughts on why quantum matters to Outshift and Cisco at large, and kick this summit off. Over to you, Bijoy.
Thank you, Ramana. Yes, so first of all, I also want to start with just a sober moment with everything that's happening in that part of the world, especially because we have a ton of team members actually in that part of the world as well, and they are personally affected by this, but what's going on. But as Ramana said, I'm Vijay. I run this group, Outshift, and we just rebranded ourselves recently to Outshift. We were called Emerging Tech and Incubation. But the whole notion behind Outshift is to build net new, meaningful businesses for Cisco in areas that are new to Cisco. So if you think about the areas that Cisco plays in currently, it's networking, security, observability, collaboration, and a few others. And what we are looking at within Outshift is where to go next. So which personas do we talk to in terms of practitioners? Which personas do we sell to as buyers? And we have four key pillars of our strategy and also of Cisco's technology strategy. And one of the key pillars of that strategy is actually quantum. So we are here today to talk about quantum. And given our pedigree in security and networking, we are focusing on quantum security and networking. On quantum security, it's primarily focusing on the post quantum cryptography world or the post PQC world. And we're looking at how quantum attributes themselves can help secure our communications in the future. On the networking side, we are thinking about how to build larger and larger systems out of these relatively small quantum nodes today, and how we can bridge the classical as well as the quantum worlds together. And to do all of this, just recently we opened up a new lab, a shining new lab. I think it's still being polished as we speak. It's in Santa Monica, and they will be setting up a whole bunch of test beds and doing some experimentation as well. With that, I would also like to welcome you all to the second Quantum Summit. I'm looking forward to some great discussions and towards being able to help define our cumulative quantum future together. And Ramana, back to you.
Thank you, Vijay. Yeah, absolutely. Exciting times ahead for quantum world, and super excited that we all, have a front row seat in this next generation of innovation, right? Yeah, so I have about, I would say 20, 25 minutes. So I'm just going to talk a little bit about Cisco Research and broadly, and go into a little bit about quantum research directions that Vijay has already kind of mentioned, but maybe into slightly more depth. Um, so before I start, my presentation, I want to just let the audience know that we have a few polls going on throughout the entire summit, and you should have received registration key for you to be able to participate in these polls. We would have one up uh, right now, and please take a moment to participate in this poll. This is the way for us to gather information about, for example, where you're joining today from, as well as your background around quantum and other questions. And this is great for us to get a sense of our audience. This will also help us potentially do this better the next time around, so that we can bring appropriate speakers and topics that matter to you all. Okay, so let me share my screen right now. Okay, so I want to talk a little bit about Cisco Research. And Cisco Research is, as I mentioned, it's a research organization that is currently nested within the Outshift organization, but we really cater to the entire Cisco. And our goal is to conduct and foster research in technology areas of strategic interest to Cisco, with an aim to generate, business, technology, and societal impact. So I've been at this role for about 3+ years, and over the past 3 years, we have been really steadily looking to establish Cisco Research as a premier industry research labs across the world. My team largely consists of, PhDs and experienced researchers that focus on various emerging areas of technology. And my team actually routinely publishes papers in top academic conferences and journals. Uh, they, they give invited talks, keynotes in academic and industrial venues. They participate in building prototypes around some of the project ideas that they may have, some of which end up being open sourced. Um, and some of the product innovations or prototypes can actually end up in products as well. So over the last year alone, we've had 25 plus publications published by my team in several areas of emerging interest to Cisco, and in top conferences and journals. So we've been steadily making progress around just showcasing our research and participating in all these international venues. So in addition to doing our own research, we actually partner with several university research labs. We have some sponsored research partners that we have established master agreements with, uh, some of which have been listed here. And in addition to those universities that we work with at a pretty broad level, we also fund several research programs across the world in 25 plus countries, 100 plus universities. And in addition, we also participate in several university industry consortiums, such as the NSF Center for Quantum Networks. We've been members there for the past 2+ years now. QEDC, the MIT Machine Learning and Applications, consortium, and so on and so forth. So the key areas of research that we've been really focused on, four broad buckets. AI ML, of course, AI ML is pretty hot right now, thanks to the large language models and generative AI components. But in addition to those, we have been focused on things like efficient, trustworthy AI, computer vision as well. The second area is network systems. So we obviously Cisco is a networking and systems company. We have a fair bit of research activities around cloud, edge computing, distributed systems, data processing, and things associated with that. In addition, we have cybersecurity as a key focus area, things like malware analysis, software supply chain, attack path analysis, to name a few. And last but not the least, quantum, which is the focus of this summit. And we do routinely host PI summits across all these different areas, and tune into our Cisco Research YouTube channel for a lot more of these videos and PI summits that bring latest and greatest research innovations from Cisco and around all the partner institutions that we work with to our audience. Okay, so I want to just start with why is Cisco interested in quantum, right? So I think one of the key things that probably everybody, most of the audience is probably already familiar with, it starts with the first premise that quantum computing can really solve some classically hard problems faster. And if you have only a single quantum computer, it can probably scale to a certain limit. But beyond that, just as how we have managed to scale classical computing, scaling a quantum computer, to a much larger number of qubits requires a quantum interconnect. And that's an opportunity for Cisco, right? Quantum networking is actually a big opportunity for us. In addition, if you look at quantum sensing, the promise of quantum sensing is that it can offer significantly more accurate data. By tapping into the quantum mechanics principles, you can sense better and therefore you get more accurate data. But you need to still transfer that information from the quantum realm to a quantum computer that can actually process this information. That requires a quantum network. Not just like local scale, but potentially the sensor could be so far away from where the quantum computers are located. So which means you need a pretty wide area quantum network. So both opportunities clearly point to the fact that there is a significant need for a local area quantum interconnect as well as a wide area quantum network. So this is a key opportunity that Cisco is interested in. The other side of it is quantum computing is a real threat to classical security. Ever since Shor's algorithm came about, it was very clear that if quantum computers were ever built to be large enough, the entire classical security infrastructure is at risk. So there's a huge amount of interest and activity around post-quantum crypto, right? Post-quantum crypto is being actively developed and standardized by NIST. So this is an area that we are constantly watching and making sure that the entire digital infrastructure that Cisco caters to is ready for this new wave of post-quantum crypto and make sure that our customers are secure. Finally, quantum mechanics actually offers these no cloning guarantees, which can actually be tapped into towards developing technologies such as the quantum key distribution to really take advantage of these principles to secure the next generation of infrastructure. So this is clearly, there is the networking aspect and there's a security aspect that is of great interest to Cisco. And this is where we really have a lot of research directions carved out over the past couple of years. To begin with, in the networking realm, we've been looking at this idea of quantum packet switching. So packet switching is, of course, the bread and butter for classical internet. This is how we have been able to really build out the foundations of the current internet, as opposed to circuit switching, which used to be the predominant technology for telephony. So now So quantum packet switching is really talking about how we can extend packet switching to take quantum payloads. Just as like, today, IP packets have classical information with an IP header so that you can transmit this information from any sender to any receiver that is located across the entire internet. The question is, can we actually embed quantum information into a classical packet so that quantum information can truly be transmitted from across, from any source to any destination across the world. And we have a bunch of work in this space, mostly very preliminary, but there's a lot of interest, at least from our group, into identifying the hurdles in actually realizing such a converged internet infrastructure and actually solving them. So that's one line of the research that we've been pursuing. Another key component for wide area quantum communications is something called the quantum repeater. Just as we have classical repeaters in optical realm, right? If you have a long haul link, for example, between I don't know, Los Angeles and New York, you need, because of the attenuation of the optical signals, you need optical amplifiers placed at strategic locations so that you can boost the signal and make sure that the signals are received with appropriate fidelity. A similar notion applies to even the quantum communications realm. Because you're using photons to transfer quantum information, you need a quantum repeater to amplify the signal every so often. Unfortunately, because of the no cloning theorem, you can't just take a photon with quantum information and just amplify it directly. So you have to do the photonic decoding and then encoding of that, re-encoding of that information in the quantum realm. And I think this is a hot topic of research that is being pursued across the world, and we've had some publications in this space as well. Now, real networks are hard to build. A lot of research needs to happen, using simulators. Just as NS2 and NS3 have been pretty instrumental in doing a lot of simulations and advancing the classical networking field. We need simulators in the quantum realm. And Cisco Research has been investing in a project called the QNet Lab, which Stephen Diademo in my team is going to talk about tomorrow a little bit about. So we are in the process of open sourcing some of this technology, but really we are trying to make sure that simulators become easy to use with an easy to use UI and can plug in with many different backends that are simulating various aspects of quantum networking technologies. Finally, another body of work that we've been looking at is called Entanglement Distribution Network. Folks may be familiar with the notion of entanglement distribution. It's really about, you have an entangled pair of photons, you distribute the entanglement to the receiver, and now you can actually send information between the source and receiver via what is known as quantum teleportation. So you need an entanglement distribution network in order to distribute these entanglements across the entire network. And so we've had some work around where to optimally place these quantum repeaters in a large wide area network so that you can optimally maximize a utility function. So there's some preliminary work going on in this space, but stay tuned for more information in this direction. In the security realm, we've been looking actively at quantum key distribution and post-quantum crypto. Now, there's a debate going on between whether PQC is sufficient and whether we really need QKD, or is there a world where like both can coexist or not? And that's one of the foundational questions. But at Cisco Research, we've been looking at both post-quantum crypto as well as quantum key distribution as two tools in the toolkit that you can use to ensure post-quantum security for your digital infrastructure. Finally, we are looking at key management systems and quantum random number generation as two other key pieces of the security pillar. And in all of this, in all of these activities, we have both theory, software, protocols, as well as real experimentation going. As Vijay talked about, we've recently announced the Cisco Quantum Lab in Santa Monica. So the Cisco Quantum Lab in Santa Monica is going to host a bunch of optical test beds and test beds for experimentation purposes, while of course the Cisco Quantum Research team is sort of globally present, but all the experimentation will be happening in the Cisco Quantum Lab based out of Santa Monica. We have a bunch of leadership roles open in this space, and so definitely, if you're interested, if you're active in this space and want to really change the shape of quantum networking, do contact me, and we can discuss further. Okay, so the rest of the summit, I just wanted to quickly go over some of the key things in the summit, key sessions we have in the summit. The first session after our keynote is going to be around worldwide quantum networking projects. We have a stellar group of researchers that are going to talk about some of their quantum networking projects that are happening in their labs, followed by a panel discussion around quantum networking. Here is an opportunity for folks to ask questions to this eminent panel and get some of the answers that you're looking for. So then we have a session in the afternoon around quantum technologies, things like photon sources, repeaters, and so on and so forth. And that concludes the end of the day one. The second day is going to be focused mostly on security and network protocols. So we have a session entirely on quantum security, and then we have a session dedicated towards the Cisco's quantum safe security efforts from both within Cisco Research as well as across other BUs. And finally, we have a couple of talks from Cisco Research on quantum network protocols, like we talked about the simulator stuff, as well as some of the repeater related efforts. And that should conclude the session, the summit around 2:30 Pacific tomorrow. Okay, so I have about like 5 minutes or so, and I just want to pose some questions, which I think at least are, really the questions that are burning in my own head around how really the quantum networking and security can take off. So one of the first questions I have in my mind is, what is the real killer application for quantum networking? Of course, quantum security is one that we talked about. Quantum sensing is another. But what would be that, HTTP equivalent for the classical internet, for quantum internet, right? I mean, if you look at how the classical internet evolved, there was initially the mail applications, file transfer like applications, and stuff like that. And really, what ignited the entire internet was basically HTTP with the help of a web browser. The moment that started, just the traffic just shot through the roof, right? So, what would be that kind of a moment for quantum networking? Is that going to be quantum sensing? Is that going to be quantum security? Remains to be seen. But this is a question that I think would be a good directional question to ask ourselves. So I kind of alluded to this, right? There's, if post-quantum crypto is standardized, which NIST is actively pursuing, however, of course, every time there's a contender in the final final round, they have been hacked. So just because there is a PQC schema that is out there doesn't really mean that it will not be hacked. So there is probably a role for QKD, but again, I mean, if truly there is a post-quantum crypto scheme that is standardized, widely deployed, and do we still need QKD, right? And I think broadly speaking, the synergy between PQC and QKD, one or the other or both, is a question that I'm actively interested in, and nobody knows the answer. Time will tell, but we are closely looking at both technologies. Okay, so it's a couple of interesting things here. While we talk about this classical communications infrastructure, right, like the internet that we know of today, the photonics-based internet infrastructure that we have today, we talk about how potentially that can be leveraged to transmit quantum information. But things like entanglement and things like teleportation, right, which are quintessentially quantum communications tech, cannot be applied to classical communications. And if we do apply that, will that increase the speed of classical communications, or will that have any kind of impact on classical communications? I think last year, a few of the panelists mentioned something around covert communications. Like, for example, if you have Alice and Bob exchange entanglement, and now you can do classical communications via teleportation, which means the information that Alice and Bob are exchanging are not necessarily on the wire. They're actually being teleported. So which means, would that mean that the classical channel capacity has increased in any which way? Will that mean that you would have covert communications between them that is non-interceptable by an intermediate third party? What have you? I think the impact of quantum on classical communications is an interesting direction that needs more exploration. And yeah, so this is a promising, interesting direction. The other question, is the synergy between artificial intelligence and quantum. So we have some threads happening within Cisco Research around how machine learning can help decode quantum information better. There's some papers that Stephen Diadamo and folks have written around this. But what about the other way around? Can quantum technologies really benefit AI or machine learning? So there is a field called quantum machine learning, right? So there is a lot of promise around that, but how much of it is promise and how much of it is realizable, at least in the near term? These are great questions that I would at least like to seek some answers towards. Finally, one of my favorite questions, right? So, history had many different, examples where there is a technology X and a technology Y sort of competing at a similar time, and then one technology just wins the race, and the other technology just loses out, right? Like, for example, during the VHS tape era, we had the Sony versus Betamax, and Betamax just disappeared. Sony just took over. Similarly, there was the HD DVD versus Blu-ray, and Blu-ray became the de facto. Of course, now nobody looks at discs anymore, probably. But so a similar kind of a race is happening between superconducting, trapped ion, and to some extent photonics. The question is, which technology will eventually win the quantum race? The jury is out. I mean, the verdict, I don't think we'll have a verdict anytime soon. All technologies will probably be pursued over the next, I don't know, several years to come. But it'll be interesting to see what will eventually win the quantum race. From a Cisco perspective, obviously we are vested a lot in photonics, given our expertise around quantum photonics networking and all that. So photonics-based quantum computing would be pretty interesting for us, because then you can do computation as well as communication in all photonics realm, and the pesky little transducer devices that you need to transduce from one realm to other could disappear, making components much simpler and the technology much simpler. So, but photonics technology is still to it will take time for photonics to catch up to superconducting and trapped ion, perhaps. But this race is an interesting one and something that we would like to closely watch. Okay, that's the end of my talk. Let me stop sharing my screen. And I think we are pretty much at time pretty much on time to step into the keynote. So maybe this is a good time to sort of introduce our keynote speaker. It's my great privilege and pleasure to introduce Dr. Jerry Chow, our keynote speaker today. Dr. Jerry Chow is an IBM fellow and the director of quantum systems and runtime technology at IBM, leading the effort to deliver the world's leading quantum computing systems to run the most advanced quantum circuits, strategically implementing IBM's industry-defining quantum roadmap. His technical expertise is in the area of superconducting qubit quantum computing, which is kind of a nice segue for my previous question. I would love to hear his thoughts on some of those topics. And Dr. Chow graduated magna cum laude from with a BA in physics and MS in applied math from Harvard, and subsequently a PhD from Yale. And he leads the as I mentioned, he leads the IBM quantum. He led the IBM Quantum Experience project, placing a real quantum processor accessible to anyone in the cloud in 2016. And in 2021, he was named an APS Fellow in the Division of Quantum Information, received the Yale Science and Engineering Association Award for Advancement of Basic and Applied Science. So without further ado, over to you, Jerry, and we are so excited to listen to you on your thoughts around how quantum tech has evolved from utility scale computers to now what you call quantum-centric supercomputing. So over to you. Thank you so much.
Thank you so much, Romana, for the kind introduction and the invitation to this the Cisco Quantum Summit. Very excited to be speaking with you all today. Let me just share my slides here, and I'll start by saying that I think a lot of the questions that you brought up there in your opening discussion are very relevant, and hopefully I can help touch on a few of those elements as we go through, and certainly from our IBM quantum perspective of how we see things shaping out as we really forge ahead from interestingly, I would say right now where we're in, which is this newest era of utility scale quantum, and I'll define what that means. And as we transition into the future, as we really augment what we know about HPC today and what we know about supercomputing to have that quantum-centric element. So just to start, our IBM quantum mission is pretty simple. It's too fast. It has two phases. One is to bring useful quantum computing to the world, and then on the other side of it, it's making the world quantum safe. So along the lines of what Romana you mentioned, some of these post-quantum cryptography type of strategies, right? To actually to help the world be protected as quantum computers become more powerful, more accessible, to potentially tackle some of those Shor's algorithms and so forth. But what I'll do is I'll primarily focus today on the quantum computing piece and the technologies that have been going in there, both from an overall roadmap perspective and where we see the drive towards what we call a utility scale, and over time applications to really hopefully change the world by making quantum easier to use and certainly higher performing. And I like to show this just because I think it's a fun way to see where we are pictorially, right? That quantum really is this new age of computation. We look back at the digital computational history, and we certainly all know about Colossus and how it made a huge impact, right, in terms of being a programmable computing device, but also was this large scale infrastructure to even do something. We have large scale infrastructure today with our cryogenic implementation of superconducting qubits for making these quantum computing devices usable and accessible. I think one difference is that it is available via the cloud, right? Colossus certainly wasn't something that was just cloud hosted. You really needed to be able to access these large building size machines in some way or other to program on them. And so we really have a leg up on the potential evolution and the potential growth of the quantum computing industry through this cloud access, right? And so that is really one of those key benchmark points that we look at in terms of driving progress in the quantum computing field, which was we first placed the quantum computer on the cloud. It was only 5 qubits in 2016, but it really changed the way that we think about how quantum computing could be leveraged, right? It no longer had to be physics experiments in a particular physics laboratory. It could be actually accessible through a programmable interface via the cloud. And then we evolved, we evolved that with Qiskit, our open source quantum software development kit in 2017, to really push forward a openness to build the community around driving different facets of what it takes to make a fully programmable, usable quantum computer. So you start getting different layers of engagement from all the way at the top in terms of applications development to various pieces in between, such as the compiler and transpiler, to even running at the circuit level. So understanding some of the physics behind pulses as they control the underlying superconducting qubits. In 2019, we also wanted to show that this was more than just something that is deployable just in a research laboratory environment, but we developed IBM Quantum System 1 as a real commercial deployment of a quantum computer that can sit, really frankly, in any location. And that really brought to bear the concept of systematizing the whole thing. And although these initial system ones are sort of on their own, it starts to lend that vision for how we want to move forward towards even data center scale population of potentially quantum systems. And just in terms of engagement of our quantum computing service and usage of our quantum computing platform over the many years, it's been just a tremendous uptake, right? So this taking quite a little bit to play through, but you can certainly see the numbers of circuits that are actually executed on real hardware is getting up there in the several hundreds of billions into the trillions by the time this ends. And the user engagement that we've had has been in the nearly 500,000 range, right? And in terms of the scientific output, it's really changed the way that research can be done, right? No longer did you need to have that theoretician plus experimentalist engagement, but instead you can actually just use the cloud compute services that we hosted through IBM through our IBM Quantum platform to develop your research ideas and to test them on real hardware. And we've been seeing that through over 2,000 published research papers since we initially launched on the cloud in 2016. Now, beyond the science element, there's a very wide range of interested industry partners too. So we have our business ecosystem, which is called the IBM Quantum Network, with over 250 plus members worldwide. These network members, they get access to our systems with preferred usage in terms of wait times of using the actual running quantum circuits. They're part of an exclusive group of members that are able to really hear from us in terms of the latest and greatest of what's coming through from IBM Quantum. And we really see this as the growth of the business ecosystem to engage with quantum, right? To be a part of developing a lot of the use cases and applications as we proceed with improvements and performance increases in the underlying technology over the years to come. And this network membership includes entities from Fortune 500 companies, from universities, from national laboratories, startups to engage startups to enable them. So a really wide range of members worldwide. And in terms of those deployed systems, we've really been looking at how to grow our expanse. So what you're looking at here is actually one of our System 1 deployments from earlier in the year at the Cleveland Clinic in Ohio. This is actually sitting in their cafeteria, right? So just to show you that we really are able to put these in almost any environment, that we're even able to put this in the Cleveland Clinic cafeteria, surrounded by people sipping on their coffees. And today we have multiple quantum computational centers. These are driving local ecosystems of access to these various systems for various reasons. Different clients have particular needs for how to handle the usage of their own cloud services or their local cloud networks to engage local clients. And so this is how we've been further expanding our reach, right? So besides our New York-based quantum computational data center, which is actually hosted up in Poughkeepsie, where we host over 20 systems today, we have deployed around the world in Germany, Japan, as I mentioned, Ohio, and most recently just up in Canada, with a few more to come planned in the coming years. And so we really see that our quantum platform really is a way that we want to see useful work get done, right? That it's not just about the hardware and the systems, but it's about having that open source technology toolkit with Qiskit, right? And the software interface that surrounds that. It's that plus our access to our systems that really leads to the novel work that we're looking to get done in the field of quantum. And our IBM Quantum platform has evolved to really capture that, right? So you can work with IBM Quantum platform today. There's multiple tiers of access. There are even free tiers to actually access our 100+ qubit systems today. There's various different tools that are built in from the software stack at different layers to access various things such as primitive functions, and complementing that is an entire learning platform where we have tremendous outreach and engagement with in terms of learning courses that have been developed by world-renowned expert John Watrous, and a number of hands-on tutorials that lets you get right in there and actually run quantum circuits, look at different types of algorithms, and build them to run on actual quantum systems. So just to take a quick step back, right, in terms of talking about like why we're so excited, right? I think from the computational standpoint, we often talk about qubits and the novel concept that the qubit is this unit of information, right, that follows quantum mechanics. But really the fundamental computational element that we should think about is the quantum circuit. And that is the quantum circuit that has a collection of various gate operations on these qubits that ends up being the sort of fundamental unit of computation, and from which the complexity with which we want to drive advantage over classical circuit computation comes, right? And so there are different categories of quantum circuits, right? So we can make quantum circuits that can be very easily simulable classically, and they're not very useful. But the whole point and the whole beauty of the quantum circuit formalism is that by the right combination of various elements that make up the quantum circuit, we can use them to address various different types of classes of problems. We can look at, in fact, simulating nature, from understanding Hamiltonians that belie various physics processes, or understanding things such as molecular structure for chemistry. We can also make particular circuits that are good for looking at, for example, quantum enhanced kernels for machine learning. So actually processing data with structure in ways that one might find advantages over how you would do classification classically. Interestingly enough, this data with structure, the factoring problem itself with Shor's algorithm, can be mapped in that way. And then there's another class of problems which is more optimization-based, polynomial speedups, such as sampling and Monte Carlo estimation, Monte Carlo sampling, which has the potential to influence financial industries, risk analysis, option pricing. But of course, with the polynomial speed up, where that boundary occurs is to be seen. And the main thing with quantum circuits that we need to measure ourselves by is the scale, like how many numbers of qubits can we actually build up to run quantum circuits, and the depth. So the depth is effectively the number of complex operations, some of these multi-qubit entangling operations that you might want to do that makes use of the full computational space of the qubits that comprise the quantum circuit. And from an industry perspective, this is independent analysis from Boston Consulting Group, which has really shown that why we're so excited is that quantum computing has this potential to drive potentially $500 billion of value across many different industries, from aerospace and automotives to financial services to high tech materials industry. To energy and certainly also healthcare and life sciences. And there are a number of engaged, pretty well-known industrial players already stepping onto the plate to look at what quantum can do for them. And with regards to these different areas, there's a number of really exciting work that we've certainly been doing, looking at what is the potential paths to looking at something like molecular simulation, looking at machine learning in terms of quantum kernel enhanced estimation, and also looking at improved optimization methods using quantum circuits. And to the point earlier, there are already engaged industries making use of our systems and working on exploring how some of these various techniques of quantum circuits could potentially impact their businesses, right? So Amgen using these quantum kernel estimations for some of their electronic health records, right? Boeing looking at combinatorial combinations of some of the materials on their wings, and so forth, as I've shown on this slide. And so really there's truly a lot of excitement. A lot of these are really meant to be looking at long-term where the path goes, right? In terms of what are these types of problems going to do at maturity, but also we're starting to see a lot more of engagement in terms of what can you possibly do with some of the systems that we're building, and I'll get to that shortly. And so just in terms of looking across the growing industry, across these different areas of what I mentioned before, simulating nature, processing data with structure and search and optimization, we're seeing interests across these traditional industry verticals, which translates to a number of industry clients that are developing quantum computing use cases. So how do we really make this more tangible, right? And especially if we're doing a lot of these use cases looking at long-term where quantum can impact these various types of applications, but we want to also be able to drive towards this quantum advantage in a few different ways. And there's really a two-phase strategy that we're working on. One thing is we need to find those interesting problems that make use of the quantum circuits. So what I just showed is basically that, how we have engaged industry partners to look at the applications that best map onto the quantum circuit formalism, and they're known to be really challenging for classical computers to simulate, right? So this has to be done in partnership. This has to be done. We're not the industry experts, certainly in many of those verticals, and so we engage our diverse quantum network to drive the development of those interesting problems. And then on the other front, it's really running quantum circuits faster on quantum hardware. And this is about charting a development roadmap with technology, right? That brings us the ability to run these quantum circuits in a noise-free way, right? That starts to surpass what you can do using classical hardware alone. And that we address with what we call our quantum development roadmap, which I'll try to highlight more shortly. But I think what's really exciting about where we are today is that when we look at this concept of quantum circuits, we've entered into a new phase, which we call the utility scale phase, where quantum circuits are now of a particular size and complexity that quantum computers, in some ways, are the can be really the only way to verify a particular problem and compare against the best classical approximation methods. And so I'll dive into a little bit more, right? Which is that we believe that we're in this phase now where quantum computers can give reliable results at a scale that exact classical computations don't exist, right? So exact sort of closed computations don't exist. And where classical approximate methods, which one might use, that leverage, for example, high performance supercomputing, break down and at least are in a phase of being compared to running those quantum circuits on a real quantum computer. So this is important, right? Because this is saying that we're in this phase where, we're not saying quantum advantage, that it's definitively at a point where quantum computers are better than classical computers for certain types of problems. But we are at a scale with the complexity of the circuits that we can build and look at, and using error mitigation methods, which I'll describe shortly, that allows us to go head to head with the best known classical methods. And sometimes those classical methods need to be altered to improve how they look at certain types of quantum circuits, right, and simulate them, right, approximately. And there's going to be this back and forth. But even on the quantum side, we're going to be able to drive that circuit complexity in a way that at some point really broadens that gap, where the simulation cost, even with approximate methods from classical, becomes too high, right? And we certainly know that there's this long-term path where using the concepts of fault tolerance and quantum error correction, we need to be able to get to achieve some of the most complex algorithms and complex applications. And yet we have this now continuous path where we can chart a roadmap that drives improvements in technology, that drives improvements in the usability of the entire quantum stack, and makes use of noise learning error mitigation techniques to bridge us towards full quantum error correction over time. And so here's just a really quick breakdown of what I mean when I talk about error mitigation, right? In which error correction really is the idea that the concept is much like classical error correction, except that what you're doing is we need to encode information across a plurality of physical qubits, right? And just because of the no cloning nature of how quantum information, the no cloning means that we need to use very specific types of codes that can be very costly in terms of the physical overhead of running these types of error correction codes. But then error mitigation is a strategy in which we're able to actually combine outcomes of many noisy circuits and effectively remove the noise for getting certain types of results, where we're not necessarily looking for the full exact solution to a problem. But if we limit ourselves to say we only need to care about expectation values, for example, of observables, which is certainly the case for looking at, for example, the energy of a molecule, right? Or the magnetization of a spin Hamiltonian. Then error mitigation gives us a path that allows us to, in the near term at least, correct for some of the noise through running circuits more. So you actually, in one case, error correction, you trade off space and physical circuit complexity to initiate codes to remove errors. In error mitigation, we use time. So running many types of noisy circuits, understanding the underlying noise processes that impact those circuits to combine to get a better estimation of the circuit output, especially when we limit ourselves to certain types of expected values. And so just to give you a sense of where we are today, in this paper we recently published in June in Nature, we were able to use one of our Eagle processors, which has 127 qubits. And remember when I spoke about the concept of width versus depth, we're able to go to depth 60 across 127 qubits, right? And this was looking at a particular spin Hamiltonian problem that we wanted to look at, a kicked icing model of and find the magnetization of it. But just for a benchmark comparison, when we first looked at very simple magnetization of problem back in 2017, we were only running 4 qubits with depth 2. So we've gone a long way since then in terms of the complexity of the quantum circuits that we're able to run, and that's by leveraging some of these error mitigation techniques. And so in this paper, right, which we published, we call this the evidence for utility, in that by looking at particular observables of this kicked icing model, we were able to pit the quantum circuit run against some of our, at least at the time, our best known approximate classical methods, and for which we knew that an exact classical method of simulation failed, right? What's interesting there is that, in fact, almost immediately subsequent to us releasing this paper, there was tremendous output from the community in augmenting some of the known approximate classical methods to actually simulate the same type of circuit and to simulate the same kinds of expectation values. Now, what's fun about that, though, is that in many of these cases with the simulation methods, there's still some differences of around 20% between the various methods. And so we really are in this phase where it's not clear which one of these is the most correct answer, because there is no exact solution. And so in some sense, our experimental results can be used to verify the accuracy of these classical computational approximate solution methods. And so this is what we call utility, that there's this interplay of what one would typically use classical approximate methods, but now you actually have a quantum computer that you can run those quantum circuits on as a tool to compare with. And so that becomes a new element of scientific exploration for users to have, in addition to their typical HPC simulation methods. And so this utility scale, this utility scale push that we see moving forward has brought about certainly even exciting new progress with being able to look at problems across over 100 qubits, right? And so really it's at that 100 qubit level that we start to see some of these types of problems that really push the limits of what you can do classically. So just as an example, here's another paper that looked at concepts of many body localization across 124 qubits, and then more recently other work that's been looking at the Schwinger model, right, which is a very well-known field theory model, excuse me, and other types of ground states of spin chains, right? And so we're starting to see this new uptake now, what we're calling utility scale experiments, where the starting point needs to be, you need to access over 100 qubit systems. And alongside that, what we're doing from a service perspective and from our quantum cloud platform is we are continuing to bring better performant and higher performing and more of these 100 plus qubit systems available over the cloud. Now, I talked a little bit about what some of those industries were looking at, right, in terms of use cases and what they see that they can map onto quantum circuits, especially for that longer term view, right, that impacts their business. But also, we're really excited to bring together what we're calling these technical working groups in a few of these key verticals: optimization, materials, high energy physics, and healthcare and life sciences, to look at this utility domain as well, right? What can we really drive towards in the near term? And what can we really start to use these quantum circuits, right, that we can run in the utility scale that pushes what they typically would be doing otherwise using high performance computing. And this is where I think there's going to be a lot of really interesting engagement in the near term, in the years to come. And just looking at the full landscape of where we're going, right? So we're in this utility scale with this most recent Eagle demonstration, which is up here in the black triangle with 127 qubits, depth 60. We're committing to hit what we're calling 100 by 100, which is over 100 qubits and over 100 depth in the circuit runs by the end of 2024. And we really see this, overall push towards driving more circuit depth, more circuit width, as the direction to go to really find that type of quantum advantage. And so, as we drive towards that 100 by 100 challenge, right, a big part of that is how do we build the quantum hardware behind it. And so, I do want to touch on my remaining time a little bit about what we're building, show you our development roadmap, right, and certainly what do we see to come in the years to come, right? So this is our development roadmap, which highlights various aspects across the entire quantum stack, right? From a hardware perspective with various generations of processors that increase in scale. And then with various layers of software interfaces that enable different types of personas, right? And so above that sort of hardware level, we build in a circuit layer, right, that enables quantum physicists that want to optimize how they run on performant hardware, understand how noise impacts their circuits, and correct for those noises using various error mitigation techniques or over time error correction techniques. Then above that is this layer, which we call quantum computational scientists. And here what we want to build are the tools that combine running things in the quantum circuit language and running it on quantum hardware with other tools that are typically used by these computer scientists in their domains of expertise. And so, like, if they use HPC, then they continue to find a way to use HPC. If they use other types of machine learning, AI through the cloud, they find ways to use that too. And that is all stitched together with something we call middleware for quantum to provide that sort of over time intelligent orchestration of a problem across quantum circuit runs, right, on actual quantum hardware, across other parts of your compute resources that you typically use. Then at the very top, we want to define what we call quantum software functions, right? And here the idea is that these are going to be driven towards particular domains, right, of industry domains, right, or use cases, for example, for machine learning or for optimization or for natural sciences. And here the idea is really to hide a lot of the things that might be under the covers, right, and just expose what's needed for users to get the work done by calling the appropriate libraries that might make use of different tools for their workloads. And so as you can see with our development roadmap, we have aggressive targets over the years to hit various aspects throughout this stack. And from the hardware aspect, we've been driving scale at first in a very monolithic sense. So over the past few years, increasing the number of qubits in a single processor by driving various types of integration techniques that enables the scaling. So last year we hit Osprey at 433 qubits. This year we're targeting Condor 1,000 with over 1,000 qubits. And you'll hear more about that by the end of the year. But also we need to drive improvements in terms of the underlying performance of some of the entangling operations like 2-qubit gates, right? And so this is just an improvement of our underlying architecture, which we had on a 33-qubit device, which shows sub 1e-3 error per gate for a 2-qubit gate. And that's really pushing some of the highest performance in terms of 2-qubit entangling gate fidelities that have been achieved, especially with superconducting qubits. And we're making use of a novel tunable coupler architecture. And we're going to upload this into a new 133 qubit processor, which we're going to be releasing near the end of the year, called Heron. And so just to give the vision of how this all comes together, especially in this next phase that we're looking at, right? And how we bridge from where we are today with utility scale to what we call quantum centric. I want to introduce this concept of why we call it quantum centric supercomputing. And I think that Ramana had some really interesting points in his initial talk where you guys talked about interconnects, right? And interconnects are absolutely important, especially when we talk about how to further scale computational workloads, right? How did high performance computing scale? It's scaled by some very core principles. They're actually listed right here. I think they're very similar. Modularity, right, in terms of how you actually compose modular architectures, right, for supercomputers. Communication, and communication at different layers of your system, between chip to chip, between package to package, right, between node to node, cluster to cluster, and across data centers. And then obviously, to make it all work together, how you access it all down to the software, or what we call the middleware, to orchestrate across that. And so what we call quantum-centric supercomputing is this vision, right, that we're going to use modular architectures to enable scaling. It's going to combine communication, both quantum communication and classical communication, to increase the computational capacity. And then it's all orchestrated together and integrated together with quantum and classical workloads using this type of, you can really consider it a hybrid cloud middleware. So from that hardware aspect, modularity is absolutely important from a even just cost per system perspective, right? We need to drive down the infrastructural costs, especially if we want to drive towards tens of thousands to hundreds of thousands of qubits, both at the processor's level, right? Looking at how we can efficiently yield multiple chips, but then that means we need to build in near-in chip-to-chip communications, chip-to-chip couplers. We need to bring down and increase the density of a lot of the infrastructure that goes into the system, such as the wiring, right, and some of the circuit boards. And then certainly at the electronics and the classical infrastructure level, how we control the qubits, how we actually build together the cryogenic infrastructure needs to be scalable, right? And so this is where that, I talked about that early room scale architecture, right? Hopefully we don't need that to run over time, right? But at the start, it might still be something like that, a room size infrastructure to put together tens of thousands to 100,000 qubits. And the interconnect piece is really, really interesting, and it really points towards a number of challenges that we're excited about undertaking in the years to come. Right, so there's a very sort of I'll call it simple view of parallelization, which is just even the classical communication between multiple quantum processors provides for a number of potential advantages, right? To allow us to do certain applications like circuit knitting, where you can actually in fact do dynamic scheduling across multiple chips, right? So having this type of classical communication between quantum processors is actually something that we're targeting towards demonstrating this year. But then comes some of those quantum interconnects. And here there's the concept of, well, you're going to need quantum links, but they might be at different length scales. What we can look at is within a cryogenic infrastructure, right, within the same cryogenic environment, microwave links that connect our superconducting qubits at the sort of meter length, right? What this does is this allows us to more easily scale in terms of the I/O bottlenecks, right? But then, of course, there's certainly many challenges with how do you preserve fidelities, preserve the right amount of interconnectivity between multiple modules. And then, something really exciting about, I heard earlier, repeaters, right? And how we can break down the hierarchy of being closed in just one of these systems is, well, eventually we want to scale towards optical connectivity, right? Optical interconnects that make use of microwave to optics transduction, that makes use of optical fiber links, right? That allows us to build I think I also heard earlier micro, right? Instead of the micro and the macro. And I'm not talking about the macro scale, but even in the intranet sense of having multiple quantum nodes connected together with these optical quantum coherent optical interconnects. And then, so really just looking at the full stack as we march towards quantum centric supercomputing. I mentioned this a little bit briefly in the full discussion of the roadmap, but it's absolutely important to understand that from the same HPC lens, we need to understand the breakdown of how things are done in parallel and how different personas are going to make use of these different timescales and drive their workloads to most optimally use the different layers, right? And so it shows that there's very important aspects of how we parallelize, but how we parallelize and which parts we parallelize are all part of the detailed structure that we need to compose this supercomputing roadmap looking forward. And so although we can neatly wrap up a lot of these elements that are quantum circuit based within what we call a runtime layer combined with the hardware infrastructure, we start to see a more diverse view of what can be used by computational scientists in this middleware layer, where for a particular problem, it doesn't matter necessarily for them to wait on execution on the quantum part. They can be doing all kinds of other stuff on parts of their other workflows. And so just as an example, this is how this serverless concept is coming to bear, where we want the developer to be able to focus on the code to explore the combination of quantum and classical. It's never going to be that just the quantum sort of sits on its own, right? There's going to be a part of how a particular problem is mapped to circuits that need to be run, but that mapping itself can be done, right, asynchronously on various cloud compute services, and then the analyzation of those results after it comes back from the quantum circuit runs on the quantum hardware can again be done, right, in this serverless fashion on any computational cloud platform of the user's choosing. Right, so this serverless concept really is going to augment, right, how I think we want to architect the engagement model for using quantum computers in the future, right? That is really part of this entire quantum plus classical, what we call quantum-centric supercomputing, right, in terms of how it is actually used. And so I'll just end by talking a little bit about where we see the evolution of the systems, right? So we have our IBM Quantum System 1, which really, from a overall standpoint in terms of the infrastructure, we designed it for 200 qubits or so, and over time we're scaling out to IBM Quantum System 2, which really pushes us into this 1,000 qubit level. And as we look forward, we certainly have a model for how this can potentially all come together towards a 100,000 qubit quantum centric supercomputer. But there's a number of exciting research directions that need to be done here, right? As I mentioned, in terms of middleware, in terms of those interconnects, right? Developing the right types of algorithms, developing the right types of error correction codes that sit on top of the lattices that we can build into some type of infrastructure like this. And then from a supply chain perspective, how do we bring down the cost? How do we bring in modularity? How do we make sure that it's competitive to put together a system of this particular scale? And, as we look forward, that vision, right, where quantum is not just quantum on its own, it is part of an entire future compute platform. Then you want to have a multi-cloud native interface that you can access, your traditional hyperscalers, your AI compute, other CPU compute, and then quantum is just another aspect of that. And so with that, I thank you.
Thanks, Jerry. I think this was a wonderful talk. I think you went from the evolution to all the way to the future of where we will be probably 10 years down, right? That's amazing. And I think I like the the fact that at the end of the day, all this complexity of quantum, GPU, CPU, everything, right, should hide behind the nice abstractions of, what cloud and, Kubernetes and all these things have provided for us. So it's kind of marrying the new world with our current world. So it's actually pretty awesome future. And so we have a bunch of questions. I know originally we planned a 15-minute break. So our next session is going to start at 9:30, but there's a few questions if you'd be so kind to stick around for the next 10 minutes or so, and
Sure.
maybe okay. So the first question is so the QPU interconnections, right? So do you have a roadmap for the QPU interconnections, especially in things like Flamingo, and what technology will actually serve these connections?
Yeah.
So that's a question that came in.
Yeah, so I mean, we're working on the technologies that will go into both Crossbill and Flamingo right now, right? From a Flamingo standpoint, that's, as I mentioned, it's finding the right microwave link within a cryogenic environment. It's really targeting that to give us that flexibility of that around 3 meter space, 1 meter space, right? And so, that comes down to there's not many options there. You need some type of cable. You need some type of coherence, right, within that. So you need superconducting cable, right? And so that's certainly the direction we're going to in Flamingo. And then Crossbill comes down to finding the right types of multi-chip cross-chip gate operations, right? And so, especially as we've been looking at various technologies, well, we for the longest time we've been doing microwave only gates, and more recently we've been looking at tunable couplers too. And so there's a various different challenges here in looking at what the right type of gate to bridge across multiple chips is. And we'll be talking a lot more about that in the technologies that go into that in the year to come.
In a similar vein, I think the question is, what is the biggest hurdle for the interconnect, right? I think you're probably your interconnects that you're designing are mostly related to superconducting
Yeah.
superconducting realm, right? Like,
Yeah.
but I mean, of course, like these are like the HPC equivalent, right? You could have your InfiniBand, or you have
Yeah. I mean, mainly the with any of these superconducting qubit types of integration challenges, the
Right.
biggest concern is always you add an element and you just turn the coherence of the device to be very poor, right? And so we certainly have very good coherence times, right, at the level of 200 to 400 microseconds. On single qubit devices, we've pushed even well into the milliseconds range. But anytime you introduce sort of new elements, there's a view of how do you minimize its impact. And so, a lot of the technology development that we do comes into that sort of interplay of, testing some new way of functionally attaching, right, this type of new interconnect, or processing this new interconnect in a way that, in a multi-chip module is using advanced packaging techniques, but doing so in a way that we can, understand where all the loss mechanisms are and making sure that we're immune to those.
So another question that came in, does IBM explore the use of semiconducting quantum dots as qubits?
No, so we are Josephson junction based superconducting qubits, and those are the quantum circuits those are the physical circuits that we built using superconducting materials, using Josephson junctions to build up all of our chips.
So what are the classical at least feelings around this whole superconducting based is the low temperatures and just the it's just not the most wieldiest of form factors, right? So whereas these trapped ion versus maybe even photonics, right? So these are all like operational a little bit on room temperatures. Is there any thought
I think,
process?
yeah. I mean, I think interestingly there, like you see trapped ions and photonics go into cryogenic solutions too. Maybe they don't go as cold, but they also need, especially
Not
from a
the
noise
0.1
perspective.
Kelvin or
Yeah,
whatever.
exactly. And to be very frank, right? When I started my PhD in this area, right, in 2005. We were working with large dilution refrigerators that we had to fill with liquid helium every 2 days.
Wow.
Right? And that's not a scalable technology at all, because the level of cooling changes and fluctuates as it evaporates out, right? But the refrigeration technology has matured leaps and bounds on its own, right? That they are turnkey solutions. They maintain temperature at 15 millikelvin for years, right, if desired. And on that end, there will be, as we scale out, there will be the question of, well, how much cooling will we need at different temperatures? And that all depends on how we architect the underlying hardware system, right? Like if we go towards some of these CMOS controllers that need to be at 4 Kelvin, then we're going to need more 4 Kelvin, right? So, that's all part of the system engineering challenges that we foresee. But, I certainly in no sense see that the infrastructure should be prohibitive. If that's the case, I would say the infrastructure for HPC is prohibitive, right? Because it's just a different aspect of cooling that you need for those types of problems.
Yeah, I guess where I was heading towards is, if you were to truly bring quantum, I mean, of course, as long as it resides in the cloud and I don't know what cage it is residing in, and keeping those low temperatures, all I need is like an API to access the computing platform. I think I'm good. But let's say the power of quantum needs to be brought all the way to the devices that are closer to the edge, like your mobile phones or your laptops or whichever, right? There, I think there would be a substantial advantage to having something that is run at.
That's where, to your point earlier about like Betamax versus
Yeah,
VHS, right? Like,
VHS.
it's gonna be
I
like,
goofed up on that,
there might be
but
different there might be different endpoints for different types of qubits.
right.
And what's I wouldn't per se I wouldn't say that you should put a superconducting qubit, in a refrigerator at some edge, right?
Right.
Because of the infrastructure that goes around it. But maybe depending on its application, maybe you do want a quantum sensor with a flux qubit or something like that. But I think that's one of those points that type of how things scale out and how things exist in this full network ecosystem is still TBD. And it's exciting to see that there are multiple technologies that have at least some differences in what they could potentially are good at, can scale to, right? And sort of environments that they can live in.
So maybe just touching back on my question, right? Like, which is, in your opinion, of course, you're probably biased, and for good reasons you're biased. But in your opinion, which technology you think will actually outlast the others?
Superconducting qubits from I'll tell you why, right? Just because I work on it, right? But the way that we look at it is there's threefold. There's scale, there's quality, and there's speed. From the scale standpoint, right, the ability to drive interconnects, right, and drive this scalability in a way that, in the end, we are leveraging a lot of our know-how from IBM's perspective of our semiconductor days. And that type of advanced packaging that we're being able to bring into the current roadmap has been all due to that, and we foresee that to continue. So from the scale standpoint, that plus the drive towards these various interconnects, we don't see that as necessarily like a hard blocker for how to scale. And then from a quality standpoint, we haven't there's no been driving the aspects of coherence, driving down the error rates, and we've seen successive progress over the many years. So that's sort of like there had to be a Moore's law, right? There's the gate quality and coherence times of devices that has continuously made advancements down, and we see no physics reason to block what we can achieve. And then from the point of view of speed, I think that's actually a really important one that gets missed a lot, which is that because of the clock rates that we can drive with the gate times and the refresh rate, right? Readout and reset of the qubits in the microseconds or tens of microseconds, at most hundreds of microseconds range, that especially in this model where we're going to need to run millions, if not hundreds of millions of circuits to run any particular problem, that becomes prohibitive to certain technologies that might require milliseconds to seconds in terms of their clock speeds. And so that model I see as, that speed element is absolutely going to be crucial, because you don't ever just run one single circuit to get the answer to your solution.
Of course. Of course. No, that makes a ton of sense. And thank you for staying up a little bit after the allotted time. But I think we are at around 9:25 Pacific, and probably take a 5-minute break before we start the next session, where we have an exciting set of speakers around to talk about worldwide quantum networking projects. But I really like to thank Jerry for an inspiring keynote. And I want to just maybe show the poll, the results of the poll around where people are joining in from before we head into the break. Can you please pull it up? Okay, looks like I would have thought US would be the biggest, but looks like we have a lot of people from UK. I guess the reason is probably because people in the US have put their cities, and so, but UK seems to be the standout. That's pretty cool. So we have a new poll in the next five minutes or so that is going to be launched. So please participate. And also, please keep the questions coming, and we are actively moderating them. And I will try to slip in into the discussions, and yeah. So please post your questions. Thank you, and we'll return back in about 3-4 minutes. All right. So we are kickstarting the next session on worldwide networking projects. And as I mentioned before, we have eminent set of speakers. To begin with, we have Professor Maria Spiropoulou from Caltech. So she's the Shang-Yi Chen Professor of Physics at Caltech. She received her PhD in physics from Harvard, and she's been working with the Department of Energy and partnering government agencies on National Quantum Initiative and the Quantum Internet Blueprint. And I'm so excited and honored and privileged to cede the floor to Maria to talk about some of her promising work in the quantum networking arena. So over to you, Maria.
All right, am I check? Am I unmuted? Yes. I think I should be fine. Thank you, Romana. Thanks, everybody, and Cisco Research. I know this is the second summit, and I heard from last year a lot of my colleagues and collaborators followed the first summit, and they got really excited. So I'm really glad that you're keeping it up. I am also extremely excited to hear from the other participants today and speakers regarding progress on quantum networking and communications at large. And so this is very nice that you put together this session. I wanted to say that for what I'm going to be presenting today, Romana said it exactly. He put the context in a very solid way. That first of all, my training for 30 years, I have been a high energy physicist. I worked at the Tevatron at Fermilab, and also at the LHC at CERN. And still, this is my day job is elementary particle physics experimental. However, since 2013, the intersections with quantum science have become paramount in terms of the impact in fundamental science. So I know that the quantum computing companies and quantum computing and quantum networking companies, they want to hold the torch about how we bring these technologies in the marketplace. But there is always on the sidebar, which for many of us is really the core, on how we actually use these technologies for our research. In high energy physics, this could be a sensor network, a quantum sensor network, in order to be able to probe, for example, the primordial gravitational waves from the Big Bang, or a quantum sensor network in order to try to probe faint signals of dark matter or axion-like dark matter. So fundamental physics that requires this type of technologies in order to make progress and answer questions that one may not consider them as killer apps, but they could offer, because they are such unreasonable questions, they could offer technologies that then you see organically killer apps appear from tackling such requirements, such very, very strict requirements for this type of sciences. And so in 2017, because of the infrastructure and work with Calgary and JPL in terms of single photon detection systems based on SNSPD, cryogenic ones, there was already the Calgary demonstration of the Metropolitan Quantum Network, and we partnered with the JPL, Calgary, and with some private injection of money from the then AT&T CSO and then CEO, who thought that there is a vision for quantum networks in the future, even if the killer app is not exactly known, So we started this so-called Cisco Research Program, which stands for Intelligent Quantum Networks and Technologies. And Romana, in his introduction, asked the question, how, for example, quantum AI and quantum machine learning and the algorithms, how all of this is connected. How do you connect the AI aspect with quantum algorithms and do boosting in terms of algorithms in quantum devices and quantum processors? So that was part of the initial vision, that we would be doing quantum networking, quantum AI, quantum technologies in terms of actually doing boosting the cryogenic readouts, scaling up devices, and especially in the technologies, having systems that can work in a similar way that we have in high energy physics, detectors and accelerators that work with a very high duty cycle. They don't stop, they reboot surely, but they are 24/7, and they provide, let's say, beams of entanglement or the resource, the quantum resource you need in order to accomplish be it teleportation, be it QKDs, be it any other protocol that you would find it useful. But before you find it useful, you need to benchmark that it is possible to do. And then some quantum fundamental in terms of the origin of space-time, if the physics of entanglement has anything to do with origin of space-time and quantum gravity considerations and bringing quantum information together with string theory in some sort of a framework where we understand if the fabric of space-time is really quantum sourced. And so there is some work and that has been published across all of these areas. What I'm going to talk today in this focus session on networks and communications is about the test beds that we have built since 2008, starting first at Fermilab, then at Caltech. The Caltech one is the research and commissioning, and what are we doing now, and some vision for going forward, and in some sense, proliferation of metropolitan fiber-based and free space-based hybrid networks under the auspices of the DOE, but with a lot of other stakeholders being participants and collaborating. And of course, I should say, being in a small university, one of our biggest sort of resources are the students, and the students seem to be very poised to get engaged in this type of, however you want to call it, applied fundamental, fundamental applied, fundamental physics engineering, multidisciplinary challenges that involve quantum technologies. So if I am to go down, I will talk therefore about our fiber-based networks and architectures. As I said, the ones that we started with JPL and Caltech, the Caltech intranet, and of course the Fermilab Argon with its new architectures and results that we have from that. All of these are some net. It's FQNet, CQNet, IQNet, Eisenhower Express Quantum Network, the Fermilab Argon Quantum Network, and so on. And I mentioned that in terms of hybrid architectures, we have also another DOE project with LBL that is using a hybridization so that we have ion traps and color centers, and try to connect this hybrid quantum computing architectures through interfaces that we build. We're going to talk a little bit about free space entanglement distribution and also the hybridization, because there has been in the world advances on that, especially in China, but elsewhere. And some of what I will mention here, of course, there is amazing progress in the UK with Bristol that Reza is going to talk about, and also clearly in pioneering work at Delft, where they have a very visionary long-range quantum network development that we will hear from Ronald. The last thing that I will mention is this hybrid species of architectures with quantum frequency conversion as a resource or as an interface in order to be able to connect various different architectures. And I stole this from Ronald's paper with Stephanie from the Delft paper of 2018. The way they have envisioned the stages of quantum networking in terms of the hardware evolution and functionality and examples of known applications. I will tell you, just like I said earlier, for me and for a lot of the people, especially doing questions like I mentioned about origin of the universe and figuring out what is dark matter, a system that operates in the Heisenberg limit, and where you read states, quantum states, you transmit them, you transfer them without quantumly, in a quantum length, and you process them in a machine that IBM or whoever in industry will make that can do quantum, that can take advantage of the quantum processing. This type of system, end-to-end, is for what has to do with fundamental physics, but one can make a bet that it can have other applications. But in terms of fundamental physics, this is unparalleled and shining a totally new way of understanding the universe in the spirit of how Feynman envisioned it. But that requires a quantum link, or requires the quantum state, and it requires the quantum processing without compromising anything. Now, we heard that, of course, in terms of quantum processing, you have to have local quantum QPUs that are connected with quantum links and also a wide network, Romana said earlier. But here, for example, I think we are at the first stages of the functionality, and we're going to see also from Ronald that we do have protocols with entanglement generation and entanglement, the teleportation-based protocols. And some networks with quantum memory start appearing. I will show some of them with their references and their demos that are being done. These are recent, in the past couple of years. And of course, people, especially theorists, but also experimentalists and people in industry, are trying to figure out the killer app. I would like to say that with all the resources of a quantum network, be it to how we engage it, other than thinking whether we will have the equivalent of HTTP or the quantum HTTP or what is that, figuring out how to use it for problems in terms of, you mentioned, Ramana mentioned security, for sure security, because you can have links that are secure, but together with security, depending on the resource you're using, you can have synchronization and timing that can be your classical leg of the quantum communication, but that can prove that, for example, it can, for local GPS disruptions, you may be able to do reset with that kind of very precise classical link for the quantum communication that has very high requirements, very precise requirements for the synchronization. So you might find that you have that the quantum networking systems can provide solutions to problems that you wouldn't just think out of the box that they would solve them. And it is quite possible that one of the killer apps will come from this type of application. Here is, I asked Raju and Iraj in my group to put together the latest sort of census of the kind of quantum networks that are operating. These are with trusted nodes. We have a ways to go because before we develop untrusted sort of nodes. So you see that in terms of the different topologies, we've got everything from mesh to tree to fully connected to star and everything in between. And then the various distances that are being noted in this table are from as low as 10 kilometers to as high as 2,000 kilometers. And there is one more with 4,000 kilometers that is not in the table that is being used with QKDs for banking in China. I have a reference later on, but the latest with that they put out from the Chinese colleagues is the fully connected and star with 46 nodes and the 2,000 kilometer with 109 nodes. Now, if we see this, we see what if we had the people from Corning that worked on the 2000 versions of NIST, BBN, Boston networks would tell you that in this country, we had about 15 years of sort of hiatus where quantum networks quantum computing was being pursued vigorously by the companies. And I think this is good when companies can do something, let them do it. Quantum networking was not pursued very much in this country. It was in Europe more than in the US, but the reflection of that is that most of these have been in China, and we do have still the DARPA. We do have the Swiss quantum and the Japanese quantum network that is listed here. So this is the latest that I could find. I mentioned earlier, and I'm pretty sure Ronald will get into that, but I just wanted to show one slide on that. On memory-based quantum network demos that have been springing about recently, and they are quite impressive efforts. The Boston area quantum network, this is using silicon vacancies for the Delft one. I believe it's ion traps. The remote quantum memory entanglement in China, that is rubidium based. And then there is the Innsbruck also with ion-ion entanglement. Maybe this is nitrogen vacancies for the Delft. Yeah, I think so. Ronald will say probably something more, and this is a relatively recent development. So I have it here. These are the references for those four. And this is the Boston, the Delft, China, and Innsbruck. So to keep noting it. So for us here, and the work that we're doing in the various DOE-based networks and the Caltech, JPL, Fermilab, IncuNet vision is to put systems together with fiber-based entanglement distribution. And you see here the BSM node, the source. We have a very nice development with a fast source, entanglement source, and then have hybridization with free space entanglement distribution, and also quantum interfaces, as I mentioned, with quantum frequency conversion. We connect at Caltech with a Photon lab that there is some memory development, but the memory there is the whole lab together with all the students and everything. So we don't have devices, memory devices that we can put in our fiber-based network. Now here, just wanted to sort of say that within Caltech, we have a lot of labs that are quantum transduction, memory, atom-based atom-based quantum computing infrastructures, fiber-based, and these are the various superconducting qubits with Mir Hosseini and Oscar Painter and Photon and Andrews, a lot of honest to God quantum computing people that they've worked all their life on that. So the idea of trying to connect all of them and also trying to do packaging and sort of integrating photonics on the chips. We do have this type of infrastructure, despite we are small, and we are trying to do some of this synergetic work and connect. We have already connected with Photon's labs, the Millikan Library, and we have also telescopes on top of Lauritsen, Downs Lauritsen, where both the InQNet infrastructure and the Atom infrastructure is here, and there's labs and the InQNet labs. So we do have some leverage, and also we do have the leverage of having some of the adaptive optics that we are using at JPL and with the astronomers as well, that we can purpose in order to do free space entanglement distribution between JPL and Caltech, and also use the fiber-based. So there is a lot of vision there. But let me go a little bit back to 2020 to tell you this is all news. This is the teleportation, the quantum teleportation in the lab that we had done in the commissioning at Caltech, and then we did the fielding at Fermilab, and we have done it at what is the old D0 area on the one side and the Feynman Computing Center on the other side. These are about 3.4 kilometers apart on the Tevatron ring. So this has presented us with a field, a version of fielding the whole network and doing the experiments, the teleportation using nodes at distance. And we published that. And it was in 2020. That was, I think, on one of the first volumes of the PRX Quantum. I just want to mention that because people can criticize that or can ask the question. This is post-selected, so we only count photons that made it after the losses, so not we take, let's say, some the fiducial, some acceptance, let's say, in terms of how we calculate the fidelity. It's post-selected, and we arrive at fidelities of 97%. The whole setup is very similar to the setups that have been used before. Like I said, in Calgary, we have all the diagnostics, the BSM measurement, the indistinguishability of the photons, the home measurement, and we have some custom-made advancement in terms of the superconducting nanowire detectors. And I'm very glad that Matt is going to go into that in the afternoon, because there is even more unreasonable optimization across dark counts, across jitter, across scaling up. So it's invaluable to have this resource with JPL and MDL, and to have the InQNet labs with the JPL people at Caltech. This has been an incredible resource. So I'm glad that he will talk to you about that, because this makes a big difference in terms of achieving the goals, as well as a lot of electronics, monitoring, DAQ, that we ported from all the knowledge that we have from LHC experiments, where we do have to have 24/7 monitoring and data acquisition and real-time data analysis, so that we can monitor what is going on and do a lot of benchmarking studies with that. So that was a very nice demonstration for the test beds, the CQNet, Caltech, and the FQNet, and we show the fidelity here both from quantum state tomography and DSM. Now, since then, we have pushed a few fronts. So we have pushed the front of teleportation of entanglement. So this is actually, or swapping, entanglement swapping. And in fact, these are two Caltech students, one undergraduate and one graduate. Sam Davis is the graduate student that is in charge of the entanglement swapping demo, together with our Fermilab people at Fermilab. And she showed the preliminary results and the design of the experiment at the APS March meeting this year. And of course, very carefully and very rightfully, Anton Zeilinger said that we shouldn't name it entanglement swapping, but we should really name it what it is, namely the transfer of entanglement through the different nodes. In other words, the teleportation of entanglement, which is an effective repeater mechanism, if you want. Here is Zeilinger with the students, undergraduate student Esme is here, and graduate student Volkan is here from the lab. So we haven't published this yet, but I'm going to show you some of the diagnostics. This is at the testbed at Fermilab, again, between D0 or DAB and FCC. And also, we're planning to do it with argon as well. Here is some of the diagnostics on two-fold home, threefold with Alice heralding, threefold home with Bob heralding, and the fourfold home, which is around 90%, so good enough. So these are encouraging diagnostics and more.
Yeah.
Yes.
Sorry to interrupt, but we are at the top of the hour, and I think there's a few questions coming in from the audience. But I mean,
All right.
do you have like a few more slides you want to wrap up, or?
Yeah, let me wrap with 3 more slides. I will skip the rest of the entanglement, the swapping, the teleportation of entanglement, just to say that we are planning it from Fermilab to Argon. And I wanted to say that with the synchronization and the high rate time bin entanglement, we are going to get in the realm now of doing gigahertz networks. And so this is a demo that you can find also on YouTube. And let me skip the high dimensional entanglement, other than saying that it is possible that we can avoid noise if we do high dimensional quantum entanglement. There is a bunch of articles that have been published recently on that, and we are looking into that and to understanding if we can have lower noise by using higher dimensional entanglement in the network. We have some results, but with that, I will stop here and maybe only say one thing about the resource of for QuantNet. This is the Berkeley experiment with the ion traps in the color centers, where we managed to have the stabilization of the polarization link for a significant amount of time, and stop here with all the advancements that we have done also for using quantum frequency conversion there.
Thank you, Maria. I think this is power-packed, lots of stuff to talk about.
Yes, I apologize that I wasn't able to go through in details, but I hope I gave you a taste of the progress, at least, that we are marking in the different areas, and the hybridization especially is quite important.
Yeah, so I think we'll have a lot more time in the panel, and thanks for sticking around for the panel. But maybe one quick question that you may answer, and then I'll switch to Ronald. So one of the audience questions is, what is the main challenge in quantum networking regarding high-dimensional entanglement distribution?
Right. So in high-dimensional entanglement distribution is how you create those states, and how do you do a BSM, high-dimensional BSM measurement. I would have to say that this is the biggest challenge. So if we look at this at the vision here, if we really need to do high-dimensional BSM, this is kind of difficult. Additionally, turbulence and doing it over the air is also quite difficult. And there is a few people that they are doing demos. We will try to do, but I think these are some of the difficulties. On the other hand, it's very exciting to attempt that, because it is promising to have a better noise, more tolerant to noise.
Thank you, Maria, for your wonderful talk, and I'm looking forward to seeing you in the panel, and where we can continue some of these discussions.
Okay, and let me stop my let's see. I don't know. Can you hijack my share, because I am yeah.
I think we can move on to the next speaker, and that automatically sort of.
Yeah, I think I managed to get rid of my sharing.
Yep, perfect. Thank you once again, Maria. So moving on to the second talk, it is my pleasure to and privilege to introduce Ronald Hansen. Professor Hansen is a distinguished professor at Delft University of Technology, and one of the principal investigators at QTech. He's one of the 4 founding professors at QTech, and his lab has done an amazing amount of work in the realm of quantum entanglement and teleportation space. He's won numerous awards and is one of the most well-known figures in quantum networking space, and I'll not take too much time away from him. This is, looking forward to a wonderful presentation around all the activities that are happening in the QTech Delft networking space, quantum networking space. Thank you. Over to you, Ronald.
Oh, thank you very much, Romana. Also to the rest of the team for organizing this summit. It's a great crowd. And also thank you, Maria, for doing some of the introduction. I think you will see some slides that are familiar from the previous presentation. So my talk is going to focus on entanglement-based quantum networks.
Ronald, I think, I'm not sure if your content, your slides are actually showing. Would you mind maybe unsharing and sharing again?
Sure.
It's taking time to load.
Does it work?
Yeah, now it's on. Perfect.
Okay,
Thank you.
I'll assume there's a little bit of a delay when I switch slides in. All right. So entanglement-based quantum networks, and maybe it's good at the beginning of the talk to already get to the same page about terminology. And actually, to do that, I do want to use the paper that Maria referred to, that we wrote a couple of years ago. Actually, we had 2 reasons to write this paper. One was to try to get people that work from different disciplines on quantum networking to have them speak the same language. So we have physicists, electrical engineers, computer scientists, and who knows what. And we want to bundle them together because we need all these disciplines to actually make the difference in quantum networking. And so indeed, probably the most important figure from that paper, or we also say just the summary of the paper, is the definition of the different stages of the network. In the paper, we give clear definitions of each technology level that these names can correspond to, from trusted repeater up to the quantum computing level. But what is important is that each of these technological stages is linked to a certain number of applications that you can run. So it gives you kind of a guide for how good your network has to be in order to run a certain type of application. That being said, this is of course the state of knowledge that we now have, and actually I would put it as a challenge to the computer scientists watching this to actually see if they can actually bring some of the applications down, because it's not given that they actually need the level of technology that we give in this paper. So that's maybe the challenge that I want to give to the people there. Now, to kind of see where we are today in terms of this ladder of functionalities, outside the lab, we're actually at the lowest stage, which is the trusted repeater stage. It means that we can do quantum links, point-to-point quantum links, for example, quantum key distribution, but we cannot do more than that. So we don't have like true quantum networks yet outside the lab. We do have quantum networks inside the lab. I will show the quantum network that we have in Delft in a couple of slides later on. And these networks actually operate at what we call the quantum memory stage. So what we have there is that we can generate entanglement in a heralded fashion between different nodes. And the heralded fashion is important because it basically technically means that there's a signal that tells you that the entanglement has been generated between the nodes. And you need this if you want to use that entanglement later on in another application, or actually if you want to swap that entanglement on. If you want to do this in a scalable fashion, this heralding signal is actually crucial. Now, the other thing is that these nodes actually contain small quantum processors. The quantum information can be controlled, errors can be corrected, it can be read out. So basically, you should see these as small quantum computers connected into a network. And then finally, of course, it has to be several links to really be a network and to be a quantum network in our definition. All right. So that being said, these are the three topics that I want to discuss in this presentation. I will start with an introduction to the EU's Quantum Internet Alliance. I think it's interesting to see how we are kind of organized and what our long-term goal is. Then I will say a few words about the multi-node entanglement-based network in the lab. And finally, I will present some very new results, very fresh, in which we try to kind of do the same thing, entanglement generation between small processors, but then over metropolitan scale. Okay, so I'll start with the Quantum Internet Alliance, as I'm the European speaker on quantum networks here. So a little bit of background story. This started back in 2017 when a couple of researchers from different institutions in Europe came together and thought, okay, it would actually be good to join forces and make one European effort on quantum internet development. And we developed this joint vision that we brought to the European Commission. The European Commission is basically the body that decides on all pan-European efforts. And the European Commission granted us the mandate to start the Quantum Internet Alliance as part of the European Quantum Flagship in the ramp-up phase. So we should actually get started. We got a consortium of many different partners, also including companies and RTOs. I will show them in a slide later on. And just last year, we came out of this ramp-up phase and we were awarded a 7-year partnership agreement, basically meaning that we got the funding and the mandate now to really try to build a quantum internet made in Europe. Now, this consortium is not just a couple of researchers. It has universities and institutions, of course, but it has European RTOs, but also many of the industry players that are relevant in the European realm. And what we also see, and this is really something that is just from the past few years, there's a lot of quantum startups actually coming out now. And these startups, they start to have 50, 100 people already. So they're really significant. And we believe they will actually make the change in the coming 5, 10 years. And then in the other segment, there's, for example, you see Quantum Delta NL, but this is the Dutch quantum technology program that also does a very significant funding of the efforts. So what does this Quantum Internet Alliance try to do? Well, actually, there's two things. So there is a technical goal, which is to build a prototype network that I will say a bit more in the next slide. But also it is a platform for building a European quantum internet ecosystem. So really to drive innovation in the end, jobs and businesses. So what is this prototype network that we're talking about? So the goal that the Quantum Internet Alliance had set itself is that in 2029, we call this a moonshot mission because this is not easy. We want to have a full stack prototype network that consists of 2 metropolitan scale networks. These are these two guys. These metropolitan scale networks, they're defined by that the different parties here can connect maybe via a central hub, but without using quantum repeaters. So in principle, it's a direct link can be made between the different nodes there. And so they could be processing nodes, being small quantum computers, but also something that we call photonic clients. It could be more simple devices with only photonic access that don't need like big fridges and low temperatures and so on. And then they would be connected by a long distance backbone that is capable of really transmitting entanglement over more than 500 kilometers. So this is made of the quantum repeater type. And so again, this is it's supposed to be a full stack system. So we're building also all the software layers on top of that, having different user devices, and we've defined some test programs already now that we're using in the coming years. But we'll have a couple of more as we advance in the technology. But certainly the blind quantum computation based test programs are kind of interesting because they make use of all the different functionalities of a quantum internet. All right. Then maybe a little bit about the hardware. There's different types of hardware platforms in Europe. We have trapped ions in Innsbruck. We have rare earth ion ensembles at Barcelona, trapped atoms in Munich, and we have color center qubits in Delft that I will talk about in the rest of this talk. But it's actually quite interesting to work together with all these different people. The systems look very different. Like if you can come into a lab. Once you talk about the protocols and how you make entanglement, what are the challenges, there's a lot of commonality. So there's a lot of help and synergy actually in bringing these platforms together under one umbrella. Okay, so then I'll change gears and go to the work that we've done in Delft in the lab to realize a multi-node entanglement-based network. So this network consists of 3 nodes. Of course, they're called Alice, Bob, and Charlie. Each of these nodes has a diamond chip with an MV center electron spin qubit in there. So the MV center is a color center in diamond, and the 2 basic assets that it has a very long-lived electronic spin, which you can use to store and process information with, and it has the optical interface. Actually, it's interfacing to visible light, 637 nanometers, and then we can actually use to make spin photon entangled states, and by photon interference on beam splitters, and actually in a variation of the entanglement swapping that Maria talked about, we can actually create entanglement between the NV electronic spins, even though they are at a distance to each other. And so in this test network, the nodes are separated by a couple of meters. Alice is in a different lab, but it's still close range. So actually we can just work at the 637 nanometer wavelength. We don't suffer so much from loss. And then we also have single nuclear spins that are next to these electronic spins that we can fully control. And they are actually really good memory qubits. So we can store entanglement there and also process entanglement in these extra qubits. And I think it's good to say that at the moment, the network that we have now, we're basically using only 1 nuclear spin per electron spin. But in different experiments, we've shown that you can actually use up to 10 of these nuclear spins. So that makes sort of 11 qubit register. And there's other experiments where we've seen that we can actually target even up to 50. So in principle, these local registers could be really made into small, well, actually decent size quantum processors. All right. So what does this look like in the lab? Well, this is really research lab. You see lots of optical elements on the table, so you can really to change things around. There's a lot of cables left and right, and in the lower left you actually peek into one of the cryostats. These MV centers are cooled to 4 Kelvin, and if you look very carefully, you can see actually the diamond chip sitting there in the middle. And I particularly like that picture in the lower left because it reminds me of some other really nice technology that you may know. Maybe you have the same association, and this is the famous eye from Chow. Of course, our setups do not have their own will, and they still actually do what we want them to do. So it's not it's not as scared as in the Space Odyssey. So in 2021, we actually connected these nodes for the first time, and we ran 2 protocols. And the first one was to do a multipartite entanglement distribution. So in this protocol, we actually make sure we entangle Alice, Bob, and Charlie in a joint quantum entangled state, the so-called GHZ state, which is a basic resource state for many quantum protocols. And we could do this in a fully heralded fashion, meaning that we had a signal that told us really, okay, at this point in time you have the entanglement, and now you can actually do something else with it. Or maybe say it in a different way, once the heralding signal is there, the entanglement is really live and existing on the nodes. And this is something that had not been done before for 3 entangled particles separated by microscopic distance. Second experiment that we did is called entanglement swapping. And here what we do is that we connect Alice to Charlie. So we make an entangled link between Alice and Charlie, but Alice and Charlie don't have a direct connection to them. So they actually go via Bob, and I will show you in the next slide how that actually works. Because we use this entanglement swapping also for an experiment that is quantum teleportation. Now, you've heard already in the previous slide, quantum teleportation is actually a crucial feature of future quantum networks because it allows you to transfer quantum information over distances without suffering from the loss. The thing you have to do is to make sure you have a shared entangled state between the sender and the receiver. But once that entangled state is in place, the teleportation of that information can be fully deterministic and without any loss. And of course, if you think about large-scale networks, this is something that is extremely important. Now, I will just walk you through how this experiment works in a sort of cartoon fashion. Then I'll show you also the gate circuit just to give you an impression. But I think it's interesting to see what actually this network has to do in order to make this happen. So in this teleportation experiment, there are 3 steps. You have to prepare the teleporter first, which basically means I have to make an entangled state between Alice and Charlie. And the way to do that is via Bob. So we first make entanglement between Alice and Bob. Then we store the entanglement on Bob's side into the nuclear spin. So we have this local memory there so that the electron spin of Alice is entangled with the nuclear spin of Bob. Then the electron spin of Bob is free and it can be used to entangle Bob with Charlie. So now we have in principle entangled links all over the place, but now we have to swap the entanglement at Bob out to Alice and Charlie, which is done by a so-called Bell state measurement. It's not really important for this talk how that works in detail, but it's a measurement on these 2 qubits in a particular basis. And then we get entanglement between the electron spins of Alice and Charlie. Then we swap the entanglement on Charlie's side into the nuclear spin, and we have basically the resource state that we need for teleportation. Then the next step is to prepare the state that we want to teleport. So we prepare some state, some qubit state psi on the electron spin. And then we run the teleportation, which basically is another Bell state measurement on Charlie's 2 qubits, and a feed forward of the measurement result to Alice. And because the coherence times of these qubits are very long, milliseconds, actually up to seconds if we push them, there's enough time to feed that signal forward to apply the correction in real time and to restore the state on Alice's side. So this is an experiment we did last year. And I have to say that although according to me the experiment we did a year before to really show for the first time these 3 nodes was the more important experiment, I think that was really the one that made the big leap forward. It was this experiment and that actually came in a lot of the media, and I think the reason for that is simply that it had the term teleportation in there. So still after 25 years after the first demonstration, teleportation is still something that is kind of very appealing, I think, to the layman. I also wanted to show the circuit diagram for the experts. So every little block here is actually a quantum gate that we apply to one of the qubits. And what you can see is that there's really a lot of gates going on. There's a lot of feed forward going on. So this is really an experiment that is really similar to what people run on quantum computers these days. And really, the network that we have is really a small quantum computer network. So what we do now with this network in the lab is to use it also as a test bed. So our computer science colleagues are building up these different layers of the control stack, and now they actually want hardware to show that this works. So one experiment that we did a year ago is to run entanglement delivery via the link layer. So they wrote a link layer protocol, and via the link layer just requests, there's a request coming in, please make entanglement at fidelity X. And then link layer and the physical layer actually have to deliver that. And we can check that the requested fidelity indeed meets up to the fidelity that we measure upon delivery. So it's a nice, I think a nice demonstration of how you can actually use the hardware to start test the rudimentary quantum network stacks that we are developing. So then finally, I want to switch gears again and show you some recent results on metropolitan scale entanglement link. And the goal here is really to see what happens, what challenges do we encounter if we want to bring this technology that we have in the lab based on the diamond NV qubits outside the lab, so at a metropolitan distance. And the setup that we have is there's one of these NV centers is in the lab in Delft, and we will bring one into a site of the Dutch telecom provider KPN. It's about 10 kilometers away, and actually they are connected via mid-station in another small city, Rijswijk, in total via 25 kilometers of deployed fiber. So this has, everything that you have in the deployed fibers, bad splicers, bad connectors, all kinds of stuff. So it's like the real thing. So you have to care now about distance-related classical communication times, and we are using an entanglement scheme that also requires optical phase control. So we actually do need phase locking and tracking of optical paths and sources over distance. So yeah, these are things that you have to implement. And of course, the nodes are very far away apart from each other, so they have to operate reliably, but also fully independently, right? They cannot share like a single laser or so, something you can do if they are in a single lock. So this is a cartoon picture that one of the people working on this system made to kind of show what elements are in there. You have these NV center qubits. We use quantum frequency conversion to bring them to the about 1588 nanometers. So we have a low loss in the fibers. There's a distributed clock. You have to work on feedback for the optical phase control, etc., etc. There's actually a lot of details that we will also release when we will publish the results on this. So in spring 2023, we had the two nodes still in one lab, as you can see on that picture, and a very basic schematic of what that experiment then is. You have your NV center qubit. There's some laser control. Of course, there's more than one laser. The single photons emitted by the NV center entangled with the electron spin are sent to a quantum frequency converter, and then they meet up with photons coming from the other node to do the Bell-state measurement and to create entanglement between these NV centers. So we did the test in 2023 in the lab, running basically everything and showing that indeed we could get an entangled states out. You get two types of entangled states depending on which of the two detectors in this picture actually clicks. It leads to a phase difference on the entangled state, but we can see that the fidelities are more or less what we expected from the modeling of this. So this is the baseline for the performance at 10 kilometers. Then in just this summer, we moved one of the nodes to the remote KPN site. And you really have to see it's really, we just moved the optical table. So there's many of the components are just on there. We just put it in the truck, drove it on there, set it up again. And after a week or so of calibrations, everything was running again. And we could actually try the experiment that we wanted to do. So it's actually kind of amazing. Of course, this is not how you want to do it in the end. Everything should actually go in 19-inch racks, etc. But for this demonstration, was actually possible to move the setup as it was from Delft to The Hague. And so some preliminary data that we have here over 10 kilometers. Now we have these two NV centers. They are separated by this distance. And we run an experiment in which we do the entanglement generation in the following way. Namely, we make the spin photon entanglement at each of the nodes, so the photons are emitted. But then we immediately read out the electron spin. The photons travel to the midpoint, and they will interfere, and maybe they will give a heralding signal. But it's not true heralding because we actually already read out the spin state. Now, in quantum theory, it doesn't matter in which order you do these things, so you can actually still check what's going on. But this is experimentally now easier because it means you can run a high repetition rate. You don't have to wait for the heralding signal to come back. And so in this first experiment, we actually got, again, quantum entangled states. They're well above 50%, and they are in good agreement with the model that we have. So we know what the noise sources are in this case. So it does indeed prove that we can make entanglement using this system over 10 kilometers. But there's a final demonstration left on the list, because I've been saying heralded so many times this talk that you know that this is something I really like and value. And so we actually also want to do like the full heralding, or sometimes called event-ready entanglement, where we send the photons out, let them interfere, wait for the heralding signal to come back, apply any feedback based on that heralding signal, right? So we can actually make the state that's generated independent of which detector clicked. We can map psi plus into psi minus, and then actually only do the readout, which is the final demonstration that would show that we can actually do entanglement generation at full heralding. So for that, stay tuned, and hopefully we can show you these results very soon. Now, finally, I want to say one thing about our vision towards large-scale networks, because I've shown you these results now on MV centers in Diamond, which is a very good system to basically build these first networks and make these test beds. But we don't believe that this is the system that will actually make us, the large-scale systems that we need. And for that, we actually need to combine stable spin qubits in solids with on-chip efficient quantum optical interfaces that actually enhance the qubits optical interface, and then combine it with photonic integration, so we can really massively scale these devices. So this is direction that we've started to take already a couple of years ago, and I think this is going to be really the main direction in terms of technology to push this to like a true technology platform. So with that, we can think again about our 2029 goal. This is where we want to go, onwards to that. And with that, I want to end the presentation. I'll show you a reference to the work that we have. And if you want to know more about the Quantum Internet Alliance, I have a link here to the website, and there's also a link to the national quantum network that is run in the Netherlands. So with that, I thank you for your attention.
Thank you, Ronald. I mean, this is amazing. So I just have a very quick question. So in your experimentation, right? So what rates of what is the rate of bits that you can transport using teleportation?
Yeah.
Like, is it like kilobits per second? Is it?
Yeah. So that would be nice, but we're definitely not there yet. So if you look at the multi-node network in the lab, the individual entanglement links, they run at roughly 10 hertz. But when you bring this out to out into the field on these MV center qubits, this goes about a factor of 10, maybe more like factor of 20 down. So you're at like half a hertz over this distance. If you just do it as we would do it now. Now, of course, looking forward, you cannot build a quantum internet on 10 hertz or like that. So the way to increase this rate, or at least I think this is the way that I and many others feel about that, is that but in the end, you don't have a node where there's like one qubit here trying to make entanglement with another qubit there, but you will just do massive multiplexing on this. So one of these nodes will actually have a million qubits trying to connect to a million qubits on the other side, such that you can just get that rate up so high. We call this entanglement factory, that there basically will always be entanglement available for processing later on. And for that, if you think about these type devices, like times a million, for instance, then really this vision of combining the photonic integration with the on-chip qubits is really crucial.
So yeah, so you're sort of like even before you want to transfer the information, right? You want to prepare the channel so that there's sufficient number of entanglements already, in a good state for you to be able to leverage, right? As opposed
Yeah.
to, there's some information that you want to transfer and now you're trying to like establish versus proactively just establish these, and reuse them or use them whenever you absolutely need to. So.
Exactly. Yeah. And that is I think the vision that we're working towards. That will be the network will always make entanglement, will always have entanglement available, and you just pull it out when you need it for a certain application.
Yeah. So there's also a question around whether is it going to be like a hub and spoke kind of a model where like you showed the Charlie in the middle, right? Like you could use the bells, you could establish entanglements with both Alice and Bob, and you could do the swapping part. Do you think of like a node that is essentially facilitating entanglements across all the nodes that are wanting to like communicate, or like is it going to be like every node will just try to establish entanglements with the nodes that they want to communicate? I mean, how do you anticipate the kind of like today if you look at packets, right? If I want to talk to you, I'll just send a packet to you and the switch will route it appropriately. That's the way it is. But if I don't know that I want to talk to you, and maybe the application will generate at some point, then if I start doing the entanglement, that's too late because that will just the delay is too much. So that means I have to anticipate in ahead and start establishing entanglements with pretty much all the parties that I would want to communicate. I mean, is that how you anticipate, or like do you think there's going to be a?
Well, let me first. I think the question of entanglement routing or how to make entanglement available. This is an open research question, right? So, but a couple of things that you could envision, right, is that you have sort of massive entanglement generation backbones that you can tap an entanglement of. And if you want to connect to somebody who's like 2-3 backbones away, you have to connect the entanglement in the different backbones, right? So there is maybe on these different stretches there's entanglement being made all the time, but it doesn't get you to the endpoint. You need to go further or some other. So there will be, depending on where you want to go, there will be points where you have to merge this entanglement or glue this entanglement together in this type of Bell state measurement that I showed. And that is basically entanglement routing, because it will tell you to which party you're going to entangle in the end. So this definitely has to take place in some way, because otherwise you would need to have entanglement shared between you and everybody else, which is
which is unscalable, right? Like that
which is a very fast, on a very small network already unscalable. Yeah.
Right, exactly. So two more questions. I know you're not able to like stick around for the panel, so I just want to like see if I can fit in a couple of questions from the audience. The first one is there a reason why you used Bell states psi over phi or phi?
There are technical reasons, but you can actually convert all these Bell states into each other. So there's no, in principle, it doesn't matter. It's just a matter of, you could even say if you change your reference frame on one side, you actually convert one of the Bell states into the other. There's no specific reason. So in this case, yeah, we just went for one of them. So the entanglement generation. So this idea of spin photon entanglement and the measurements, that does actually produce two specific type of Bell states. But as I said, you can actually go from one Bell state to the other if you want. Yeah.
Another question is, could those qubits used in teleportation nodes lead us eventually to a distributed type of quantum computer?
Yeah, absolutely. So there's many similarities, I think, in the modular approach that you see that quantum computing efforts are now taking, right? So you cannot build everything on a single chip. So you need to build in a modular fashion, and in a sense, what we are doing, we're also building things in a modular fashion, but the distance will be larger. So there are differences, but there are also definitely on the technical side there are also things that are the same. And in fact, in Delft, we have a project with Fujitsu actually exploring these type of systems for modular quantum computing. So this the link is actually very direct. Yeah.
Perfect. Thank you. Thanks, Ronald. This is awesome, and thank you so much for making yourself available to come and give a talk in our summit. Thank you once
Thank you.
again.
My pleasure.
Okay, moving on to the last talk in the session. It's my great pleasure to introduce Professor Reza Najabati, who's currently a chair professor of intelligent networks and head of the high performance networking group in the Department of Electrical and Electronic Engineering in the University of Bristol, UK. So he's also visiting professor and Cisco chair in the Cisco Center for Intent-Based Networking in the Curtin University, Australia. And he's established successful and international recognized research activities in autonomous and intent-based networks as well as quantum networks. So over to you, Reza. Thank you so much, and yeah, looking forward to your talk.
For the introduction, as the introduction says, I am coming from classical telecom background that is doing for last 10 years research on quantum. So what I am going to present today, you saw the activity from the US, from Maria and Ronald from Europe. I mean, UK has its own quantum program, which the communication program is focused on the quantum communication hub. And I am going to present the activity there, which is basically mainly focusing dynamic quantum networking for security. And then recently we are moving toward the quantum computing interconnects. I start with my talk general, a little bit of the advertisement and the overview of what is the national quantum hub program on communication in UK. UK government has divided its investment on quantum technology in the center of excellence around the computing, communication, sensing, and imaging. And my team is a part of quantum communication center of excellence or quantum communication hub. And our view is that to build a network, quantum network at all distances from short to large distances. We have done 2 phases of the 5 years, 10 years so far research on this. We are approaching toward the end of the second 5 years or 10 years of the research. And our differentiator is that we are working on creating a very dynamic quantum network at short distance, and then point-to-point long distance quantum communication with fiber and satellite. And we started with security when we increasingly moving to a scale level in terms of the number of the users, and also doing application beyond security for quantum computing. So there is a large of the industry are involved in this project. This gives you a glimpse on the size of the project. I don't go through them, but what I want to share with you with the work that my team does as a part of this project, and generally what we go beyond the security. If we are looking at the quantum technology, a little bit of background, basically we can use quantum for both security and also computing and sensing. But if you look at if you can create a network that connects together, and the network, in my opinion, has to have certain features to be a dynamic, support entanglement distribution, and also doesn't make a sense to think about the networks if we are thinking at the scale to be a dedicated dark fiber network for this. We have to think about the network that can carry classical and quantum information together. And such a network also has to support the multi-user and multi-tenancy with all this application. If you think about all these features together, then we can think about one definition of quantum internet, which is creating distributed quantum sensing, quantum data center, and giving access to quantum data center, quantum cloud computing. Now, if you look at what happened across the world, it's different view from what Maria showed you. Is there a lot of activities going on across Europe and US and China? the most impressive one is China, long distance, lot of node in a star topology and mesh topology. But all of them share most of them are looking at the QKD security, and the one that even look at the other things like entanglement distribution and teleportation, they are purely point-to-point. So although they create a star or mesh topology, what they are point-to-point, there is no dynamic one. In UK, we are taking different approach. I believe we are one of the most advanced national quantum network testbed we are building. We have built already. So it goes from east coast of UK to west coast of the UK, from Cambridge to Bristol. In Cambridge and Bristol, we have two metropolitan networks connected with a long distance point-to-point, the two cities across the country. So the good thing about the uniqueness is about that both Cambridge and Bristol mesh network are dynamic. We are fully mesh in Bristol. Cambridge is a metro ring. But nevertheless, we do a dynamic and we do a networking experiment there. I go through that a little bit on Bristol side, which my group comes from. The other thing that we do in Quantum Hub in UK, we are looking at a longer distance. In the first quarter of the next year, we aim to launch together with the Canadian partners our first CubeSat satellite that allows us to integrate our ground network, which I showed in previous slide, with the satellite connectivity for long distance for QKD. So this is just gives overview where are we in our UK networks and testbed. Now a little bit of my group activity in Quantum Hub in UK and what is make unique the quantum network activity we do in UK. We very much focus on making the dynamic networking, one of the aspects that we make it unique. What we have done in my group, we developed what we call the quantum ROADM or quantum switch, which is basically allows us to switch quantum channel and classical channel over the same fiber or different fiber dynamically between the different nodes. So we have created a network using these switches that you can see in right hand side. If I try to turn on my pointer, give me a minute. Yeah. So here is we can create a network that is basically, first of all, is software defined control. You can run all the routing algorithms. You can independently route the quantum and classical channel. They are carried over same fiber or different fiber. To be able to put the quantum classical channel together, we run a machine learning techniques to adjust the power, modulation format, distance between quantum classical channel. We can make this multi-tenant, multi-user, can have a different quantum communication, classical communication. And also we use it primarily at the moment for security. So we can have a different encryption, decryption techniques using quantum keys running over this. Now we have implemented this in the city of Bristol. So there are a fully mesh fiber network, carry classical and quantum channel, all the nodes equipped with this switch. And then also to be able to show the benefit, we have connected to a very advanced testbed we have in the Bristol city, which is a 5G testbed. So I tell you what, on that is a very advanced 5G softwareized future, next generation wireless network. So what we do, we have done it for first time a security use case in a disaggregated softwareized 5G network where the antenna in the top corner you see here in my laser pointer connected to a data center running the 5G software in a dynamic fashion using the quantum security over the same fiber, carry the quantum and classical traffic of the user from the wireless access point to the data center. So we can run a various encryption, decryption techniques for different users, for different traffics. We can carry a different type of traffic at 100G, 10G channel over the same fiber with the quantum channel, multiple quantum channel. So this is a recent demonstration. Now, to scale this, we have moved from beyond prepared and measured, we showed previously, to a more entanglement distribution. So we have created an entanglement source, which is a well-known source arrangement, which basically you pump low frequency, high power laser to a crystal. And what gives us a broadband over the C-band entangled source, pairwise entangled bunch of wavelength over C-band So we create over the C bands a large number of wavelengths that are pairwise entangled together. So we pass this to basically a multiplex, a low loss demultiplexer, and put it to a passive switch, a low loss switch. It gives us, we can basically distribute the pair of entangled photons over different wavelengths to different end nodes, A, B, C, D, I. I mean, you see the A, B, and I here. Multiple nodes, we can pairwise and create dynamically entangle them together by reconfiguring the switch and the multiplexer together. So we can do all sorts of other tricky dynamic networking with that, by creating basically beam splitter and polarization controller loop there. We can also time share this entanglement source between multiple users. What we have done, we tested over the city of Bristol this distribution. So with 8 nodes over with the 30 entangled wavelength pairs, so we end up that situation that we have for each reconfiguration of the network, 10 network, different elements to optimize. So for that, to be able to cope with the complexity of that, we develop a deep neural network purely to control this entanglement distribution network. And we have managed to create a very impressive result. This shows the performance of deep neural network to control an entanglement distribution. You see there are a set of the nodes on the left, top of each graph. We have a Chloe, Alice, Dave, Gopi, and Bob entangled with the same different user on the other side. The thickness of the line shows the quality of entanglement channel. And the bottom under each graph, we see a red and green line. One of them shows the measurement we did in the experiment. The other shows the predictive result with before we do experiment using our machine learning techniques. So it shows a perfect match, and that shows that a very good quality of entanglement distribution. We use that to purely for doing the QKD-based entanglement or security-based entanglement for experimental research. Now, this is we did this demonstration 2 weeks ago, or 3 weeks ago, sorry. So this is the first that we managed to do a multi-channel entanglement, multi-channel classical, and prepared and measured channel QKD over the same fiber over C-band regime. So you see that over telecom wavelength. So you see that our entanglement source, we put it through the same mechanism, the multiplexer, and put it in the switch. So we create a multiple entanglement channel over the fiber. We put a prepared and measured off-the-shelf QKD channel. We added 8 QPSK channel at 100G, and then we added the 16 QAM channel classical to that. All of them over the CFAN, over the telecom wavelength, all of them over the same fiber. And we try to basically measure the performance of that. So we did it over the 50 kilometers of the fiber over our city. And you see that the A star and Bob star, Alice star and Bob star are the prepared and measured. The rest are the black one, Heidi and Chloe and Dave. Black one are the entanglement distribution, and we did it. And then we try to do our dynamic switch to switch our prepared and measured between different nodes. And that shows the performance of the using the performance measurement for the key distribution using this regime, all the channels together with various configuration. So we can achieve a 200 bit per second key rate up to 2 megabit per second key rates. Now moving a little bit beyond security, we need to have this useful quantum computer. You have seen from previous presentations or keynotes. A useful quantum computer depends on which study you look at it, but they are going millions. And there are a study showing beyond 10 million qubits you need. I mean, 10 million physical qubit. I mean, logical qubit can be less. But 10 10 million qubits, I mean, is a big challenge. You may be able to build it, but a million qubit processor, there is a famous quote that there is a need a football pitch size cooling system. Whatever regime you want to go, photonics, microwave, diamond, whatever you want to go, but you need that size of the cooling system. So you need to find a way to scale this to achieve useful quantum computer. Obviously, hyperscaler approach is the way to go. A smaller quantum processor, network them together. I don't want to justify it further. So what my team started doing that, we try to see how we can use our entanglement distribution network dynamically to connect the processors together and try to come with a dynamic network. We can share a lot of resources, entanglement resources, balance statement resources, and connect the processors together. Worth noting that we are looking at the gate-based quantum computers. There are cluster-based and photonics-based, which are different. I mean, we can look at them, we can discuss them separately. Nevertheless, there are several challenges. One challenge is that you distribute too much, means that you have to sacrifice your processing qubit for communication qubits to connect your processor together. You degrade the performance of the processors, one of the challenges. So here is what I said, the challenge here. So if you want to create a distributed quantum processor, you need to sacrifice what you see, Q3 and Q prime 0. You sacrifice your processor qubit for communication qubit to do a teleportation between your two processors. And then you need a classical and quantum links to do the communication between them. You can run your algorithm using teledata to teleport the data from one processor to the other, or do the telegating, teleport the part of the gate or a gate from one processor to another processor. But we are trying to see, if you want to do that, what would be the penalty you pay. The first penalty is the latency. The second penalty is the loss of the switch and link. The latency is important because of the decoherence time of your qubits, but the loss and delay is important as well, again, to do the right measurements. So this is a simulation. So we try to do what would be if we assume that our switch and links for short distance in a warehouse scale level. Distributed quantum computing has around 0.2 dB to 1 dB loss, switch and link together. And we want to do a distributed Shor algorithm, or part of Shor algorithm, let's say part of Shor algorithm, over 5 qubit and Graver algorithm 5 qubits. So number of non-local gates, we tried different things, 3 local gates, 7 local gates, and 11 local gates. That's what we can do. This is the performance of our modeling results so far. It shows that Shor algorithm, you can do reasonable performance with the loss introduced by your network and switch. With the 3 processors, you can tolerate the loss. You can get a right result. But with the Graver algorithm, even 2 qubits two processor doesn't work. You need to stick with 1 processor. So it shows that very much algorithmic dependence if you want to distribute processing. So distributing of the processor cannot be considered only the physical layer. You have to bring the algorithm part into this as well. The other is the decoherence time of your non-local gate. So you have your latency to do the teleportation and do the measurements for teleportation and entanglement distribution, and then you have a memory decoherence time that you keep the result to do to achieve the remote gates. So these are affecting, and we have done some modeling to see what you can do. I mean, this shows that you have basically two latency to consider. One is the memory decoherence time of your entangled photon, and the other is the measurements latency that you need to do. So it says that if you consider the tau of which is the tau is the latency, and the t is the memory decoherence time of the what I use the performance that I put there, we can get a with a 100 microsecond memory decoherence time, you get a error on your gate of 0.03, and then you can see the result with the 1 millisecond decoherence time. So the decoherence time is becoming important, And therefore, we came to build a system that we try to achieve the very high accuracy synchronization between our entanglement distribution and measurements. So we create a simple electronic-based timing distribution for this purpose. We are testing if we can achieve a 10 picosecond timing accuracy and then less than 10 picosecond synchronization time to achieve the synchronization. So that's also another activity we do. Now, we have recently started a project in UK. So we're looking at how we can create a quantum data center. The first phase of this is that you see a lot of companies are involved. I listed them below. But the aim is that at the first stage, we want to see how we can do a large scale user access, secure access with the technology I mentioned before to a quantum data center, which the quantum data center in the first instance is a classical data center, which our processor are accelerated with quantum processor. So there is a quantum processor accelerator, not the distributed quantum processing in monolithic quantum processor, but acting as an accelerator, for example, for machine learning or anything else. And the second stage, we are looking at how we can create a full-fledged quantum data center by distributing quantum processors together and create a network that does the quantum entanglement distribution, sharing the measurements capability, and do the classical distribution and make it multi-tenant so you can rearrange your topology of the network. Something that we found very interesting, creating a dynamic topology between processor bring an unprecedented advantage for the quantum algorithm, because the quantum algorithm developers so far think about the topology as a fixed topology of the circuits. Circuits or gate topology are fixed. If you can create a dynamic gate reconfiguration, then that creates a very interesting possibility for quantum algorithm developers. So we are working with the other partners to create a compiler to take advantage of that. So this is a very future roadmap that in my group we are taking. So with that, I would like to thank you, and I hope I was on time. And you can look at the website of the Quantum Communication Hub in UK to see all partners, what they do. I presented a networking view of that from that part. Yeah.
Thank you, Reza. I think we are perfectly on time. I think maybe you recovered some of the time difference between the previous talks and your talk. So thank you. And I think we should just probably just bleed into the panel, given we have about like 45 minutes or so. And we can just basically have an open discussion on several topics that that have been, some questions coming in from the audience, but some questions we have ourselves. So maybe we can just jump into that. Okay, so I think the first question is, I see that there's a lot of similarity between, like, for example, what you're talking about and what Jerry has mentioned in terms of IBM's supercomputer scale with distributed quantum computing. And there will be many such thoughts around really scaling quantum processing with large scale interconnects and stuff, right? So I guess my question is, are there technologies that are well suited for quantum data centers much more than interconnecting quantum computers across the world, right? Like wide area versus local area. Do you think there are specific technologies which are a lot more conducive to local area, which are much more promising compared to those in the wide area?
Is it for me the question? Do you want me to start?
It's an open question to either. I mean, I
can start. To be honest, in a short term, I would say that that would be within a warehouse scale in a control environment. I would see very difficult to see beyond the metro. I mean, even metropolitan area, a quantum network that is good enough in terms of quality and fidelity that can support the distributed quantum computing. That's my opinion. I mean, you need a very controlled environment. Again, depends on time scale. If you think about the 5 to 7 years, but if you go beyond 10 years, yes, for sure, yeah.
So any further thoughts, Maria?
Yeah, I think I think Reza said it. What I think it's important in the intermediate sort of era is to consider to do all the demos we can with links and quantum information propagation, entanglement propagation, and do that without requiring the scaling of the processors at the edge. In terms of quantum data centers, I think it could be inevitable in many architectures that instead of having scaling of the qubit architectures, you will have networking of smaller boxes. And that would be in the local area what you were mentioning. And I think for a local network, then the kind what Ronald showed as in the memories is small sort of processors in the end. If you start networking them, then you are having, instead of a scaling architecture of packing qubits and trying to figure out the noise situation, just networking them in smaller boxes. So that's something that people will be necessarily exploring as they try to scale up.
Makes sense. So moving on. So one of the questions that that we were thinking about is, this global quantum internet, right? What are the hardest challenges of deploying such a global quantum internet? Is it societal challenge, like just the laws, regulations, and stuff like that, or is it really the technology that will be the bottleneck?
Well, I can give it a shot. Reza, you want to go first to jump on it?
Go, please, Maria.
Yeah, I think, well, to start with, the standards and the language that we speak, the engineering language and the needs for standardization, in other words, all the NIST stuff, so that we can speak the same language. But aside from that, I heard the echoes of, once we have a quantum internet, can we foresee some of the regulatory stuff that we didn't foresee for the normal internet, and it comes to bite us. And I think for this, I know that there have been sort of anthropologists and social scientists and people who care about about ethics, just like the people who did the AI or the genome project, that they are looking at those as they are looking at for AI, they are looking at also for quantum. The question is that if you find the killer app you asked in the very beginning, probably you are not going to pay attention to that aspect, and you are going to jump to create that. The global, making a global quantum internet, it's an engineering sort of enterprise, and it will need a lot. There will be a lot of there will need to be a lot of demos to demonstrate what good is it. First of all, that we can do it. Probably we can. We know we can. Be it with swapping, be it with repeaters, but what good is it is something that we have to keep examining until we have an answer that convinces ourselves. But other than that, I think that in global geopolitics, etc., the way it is today, it is probably that everyone will want to have the regional quantum internet and the regional quantum security and the regional, CubeSats to do relays and cover particular spaces. So it's not clear that there can be ab initio this collaboration. Let's hope that that this can change, because this can be transformative for all humanity. But there is a lot on the way there. Reza, maybe you can chime in.
For me, I mean, yeah, because we are looking at the quantum internet, in my opinion, everybody is looking, including myself, is what was the definition of classical internet? I mean, is that going to be something replacing the classical internet, or be in parallel with that? Honestly, I don't know. There is a lot of promises on the quantum, but which on the security, for example, the quantum security, everybody was bragging, we want to have ultimate security, but PQC is now is going head to head. I mean, we don't know it's going to be that. On the computing, obviously quantum has an advantage, but it's not a universal. So I don't know if it's going to be a quantum internet replacing the classical internet, and I don't think it's going to be I don't know if it would be a public quantum internet. Maybe it would be something like a GPU. Some people, they are using it, some people are not using it. But this is something that still remain. We don't have, the problem is that we don't have a universal quantum computer as such, and universal quantum algorithm. So I cannot, I mean, it's very difficult to get a crystal ball to say is that. But in terms of technology, I think there is we need to solve the basic problem we need to solve is the problem of memory. If the quantum memory in a scalable way, economical way is solved, we see a very, very massive progress in scalable quantum, both security and computing. So that's, in my opinion, should be. I see in the 5 years time will be solved, and then my prediction is that in the 5 years time we will see 3 to 5 years time we will see a spike on the quantum internet vision and architecture because of the availability of various memory technologies. Yeah.
No, that makes sense. Moving on to a different topic. So in your opinion, right, so how are different countries or continents treating quantum technologies? Like, what is the focus in UK? How does it contrast with like the rest of EU versus how it's actually like being perceived in the US? This is both in terms of technologies as well as maybe applications too, right? Like you said, PQC versus QKD, there's a lot more emphasis in Asia and Europe around QKD, but lesser so in the US. And how is that shaping like where the quantum networking technologies and focus areas are shifting between these different continents essentially?
Well, in UK are moving, I think, like other countries, toward the quantum 2.0, if you like, and then for a long time there was a big debate on UK government on the security, importance of quantum is security. Because nevertheless, we need to agree that the quantum secure the links. And if you go to the cybersecurity agencies, the security of the link is the least problem for them than other part of the ICT ecosystem. So therefore, that doesn't come on top. But the network memory, which brings the computer and network entanglement-based networking, is becoming top priority for UK, at least in terms of quantum networking. And then still security has a big importance, but there is a very big debate on that would be a de facto the security solution for quantum security, but certainly is not a top priority security application. I mean, entanglement-based networking and memory-based networking, computing-based networking is becoming equivalently important with security. Yeah.
Over to you, Maria.
Yeah, perhaps we can say that in the US, within the quantum initiative, there is prepared appropriations, authorizations, not appropriations yet, for 250,000 quantum networks, and they will span all the above areas, including some additional ancillary applications. Like Reza said, there is no emergency, shall we speak about security, because the era of the quantum processing that could break all the most upgraded RSA codes that everyone is using is not yet here. However, post-quantum cryptography is something that is being developed, and also, there is something that it is physics-based only with MDI QKD, for example, where this is a matter for post and for quantum and for post-quantum. So you have the ability to do tests with measurement device independent protocols, and that will be something where we go on the 2.0 also for post-quantum with communications protocols that can do that. Ancillary also, what can you do with links as an ancillary, like we said earlier? What kind of other problems can you solve based on the technologies you developed and the hardware and the innovation that you develop with quantum networking, that it may not be completely obvious today? So we are going to see, I think, applications that they're not completely obvious today, be it using the network or the fiber as a sensor, for example, in order to do, there is within the architectures and the hardware developments of the quantum networking, there can be solutions that are not immediately coming to mind. And I think these will emerge in the next 5-10 years, probably surprising people that they can be immediately deployed in applications. Yeah. So I think the US will go around these ways. And of course, other than the DOE, you are hearing that the other agencies, other than DOE and NIST and NSF, the other agencies like the DOD and NASA, they have also an inherent need for exploring these kind of technologies for various reasons according to their mission. So I think the US, in terms of quantum networks, is becoming more involved, and of course we are paying attention what is happening in Asia and what kind of applications are there, and we are collaborating clearly and looking at what Europe is doing, and the UK specifically, as we are very close partners together with Canada and the UK. Yeah.
Yeah, so this segues nicely into that free space optics versus fiber, right? Like the terrestrial part. I think China, if you look at, they have security. I mean, QKD is their one of the main applications, and they've used free space, like essentially satellite, and compared to, I guess NASA has a different reason for using free space. I mean, they're looking at sensing, and quantum sensing is a big application, right? Completely different application, but there is clearly some role that satellites have to play around quantum networking. And then there is obviously the terrestrial part, which is basically the whole classical internet is built on. And I guess again, if you look at the geos, right, like some, like Asia is much more looking at for like wide area especially, right? You're not looking at terrestrial networks, you're looking at free space optics compared to like the classical internet. So there is that. So, but in your opinion, I think, do you see one is preferable over the other as far as the fault tolerance and fidelity of the links? Or do you think like one technology will actually emerge out, or you'll see the coexistence of both of these in the future? Maybe you can start with Maria, and then we can.
Yeah, I think hybridization is the way to go. You will have, fiber, free space, downlinks. So you will do all of the above, and then you would have to have all the transduction or the quantum frequency converters in order to figure out if you are going to be using different architectures different kind of memories and different kind what you have. Of course, when you are in space, you can't use cryogenic single photon detection. So you have to adjust your detections. And when you are in the ground stations, when you are collecting single photons, you will have to have telescopes that are instrumented with SNSPDs over large areas, so that you can collect the. I think everything everything will be kind of knit together in order to make the whole quantum functional and the relays appropriate for large distances. For example, you can use the free space and the in terms of fidelities and in terms of losses, you will have to deal with different problems in the different cases, turbulence, but in fiber you have other kind of losses and Raman losses, and you have to just stitch together the whole hybrid system, which I think will be in the end, that's what will work.
Anything else you want to add, Reza?
Yes, yeah. In UK Quantum Hub, there is two aspects in the wireless free space. One, on access side, we have a big activity that we develop handheld QKD devices from your mobile phone, let's say, to ATM machine, or you can think about it that they do the free space QKD. So that's on. The other is the satellite, and then we are looking to converge all of them over the fiber. I mean, that's what Maria says. So I think satellite is unavoidable for free space. You need to have it, and there is also element of the at least research in UK going on for the satellite to satellite communication to avoid adversary basically eavesdropping and interplanetary communication as well, because that's free space is much easier to do. You don't have atmospheric conditions, so that's for sure is the big and is a very large part of the communication program in UK. But I want to add that we have also access part as well. And the other thing we see that one thing that maybe make it relevant, we see from the national operators, British Telecom, there was an announcement that they have increasingly their customers, they are multinational corporate, they would like to use the QKD quantum secure services. So if you are within a city or a country, you can do the fiber, but if you want to connect your corporate across the different continents or countries, then you need a satellite communication for that. Yeah.
Right on.
Exactly. So essentially, if I were to just summarize, just like how we have Ethernet built out of copper, we have optical, blah blah blah, right? Like the phi layer is myriad of technologies. You could have RF, you could have Wi-Fi, you could have whichever. But at the end of the day, you're transmitting bits, and then you have your MAC layer, which is just basically saying it doesn't matter what phi layer you have, and just provide you a mechanism to address the individual stations that are participating in this channel, right? And so on and so forth. I think what you're essentially saying, the parallel will apply to the quantum realm as well, right? There's no one dominant technology. Different technologies, different ways of communicating your qubits are required for different applications. They all have to coexist. So which means we will have to build our protocols in just how we build classical, right? In layers, so that you're somewhat agnostic to the underlying layer and these abstractions and the interfaces between these abstractions are very well defined. And as long as your medium adheres to the abstraction, you're good to go. You don't need to worry about whether you represent your qubit in the form of a photon polarized in a certain way, or superconducting qubit in a certain way, or a trapped ion, or whichever, right? The same approach.
You care about the IPv4 or the IPv6, which changes every 10 years, not every so often.
Just one point to mention, we shouldn't forget that there is last 1 or 2 years, there have been a very good progress on a RF quantum, not photon-based quantum, but RF quantum, and that's something is take a time, but it's gonna come. So on the radio side, we will see that the quantum also will progress. Yes.
That's fantastic. Yeah, I heard about that. Yeah, that sounds fascinating to say the least. Moving on to a different, altogether different topic, which I kind of alluded in my initial one, right? So, what do you see artificial intelligence as playing a role in building the future quantum networks? Do you see AI having a big role in quantum networks? Both, I think the synergy is both ways, right? How does quantum enable AI, and how does an AI enable quantum? Any thoughts there, Maria? And
Reza, you want to go first?
I am happy to go, yes. To me, what we do, I mean, if you want to, I mean, it doesn't make a sense, as I mentioned in my talk, to assume that you have a separate fiber infrastructure for your quantum network. And if you want to use your existing fiber infrastructure, doesn't matter, then classical and quantum should coexist. And the coexistence, to me, in a dynamic fashion, you cannot avoid AI to managing that network. So, I mean, there is well-studied publication from my group and other groups as well. You can see that. On terms of the quantum for AI, I believe the first one of the low-hanging fruit for quantum computers would be running AI algorithms. Special purpose quantum computers that you can scale them, like a fiber-based, Poisson sampling-based quantum computers that are not universal. They are very well tuned to solve the AI problems, and you can use them as a co-processor like GPU in your data center and provide a service for your accelerating AI. So that's my view on this. Yeah.
Right. Yeah, so I think, Romana, you had set it up in the very beginning. I mean, AI is used for, for optimization of every function that you want to write with parameters, etc. You can imagine that you can do qubit calibrations of millions of qubits using AI to do that, right? Instead of, so you can imagine applications of AI on the hardware for quantum computing or for quantum networking, so that the full network is used at maximum, all the loads and the orchestration and everything. You can do it. You could use AI in order for the current network to be optimally used in the classical network, and you will do that for quantum. Now, when you're talking about quantum algorithms, well, we have found that if we're doing quantum AI, quantum machine learning, for example, in problems at the LHC, we find that they are not that using the quantum algorithms or quantum graph networks or that doesn't help us in solving problems better than normal AI. However, there is cases like the case that I mentioned, if you are considering systems in Heisenberg state all through, where you can imagine that quantum AI would be advantageous. And so it's part, I think, as part of, somebody also mentioned, I think maybe it was you, Romana, that we managed to do, or the IBM keynote speaker, we managed to progress on using quantum algorithms on for problems that we thought they are intractable. They are now tractable, and there has been a lot. It's mathematically involved, but there has been a lot of results where mathematically intractable problems with machine learning or with AI using quantum algorithms, they become tractable, classically tractable. So you have some, I think there's progress on how we deploy all these new tools and approaches in the toolbox. AI is in our toolbox for doing science, engineering, and preparing technologies. Is a very useful resource, combined not only the applied math aspect of it, but also the GPU, also the actual hardware that it runs. And it was mentioned also that the full architecture will require the GPU, the TPU, the QPU, a coprocessor that might be an adiabatic annealing, and so it's going to be, again, talking about hybridization. It's going to be a very hybrid computing environment where you have your HPCs amended with all these other technologies. It's not going to be one or the other, and it's not going to be locked in a room alone. So we're looking for a wild landscape of computation that will require, and the wild landscape also of linking of networks and networks of networks. It's going to be very interesting, I think.
Oh, absolutely, absolutely. Now, another question is, in order to get to the real global quantum internet, right? You need a lot of standardization. I mean, IETF existed. We had RFCs. I mean, as the basis for standardization. So, how do you see the current efforts in standardization? Is it too early, or for quantum standards to be developed, or what would be the right appropriate time for the standardization efforts?
I would say we should have started it already, and in coordination among, at least with people and places that they talk to each other. So I think this NIST has an effort, QEDC, the NIST consortium, they want the standardization also between, let's let industry do what industry does. Let's inject all the research, but let's start the standardization. It's a long journey to get the standards. So I am worried that I don't want to say we're late, but I think we're late. We should do that. We should be doing that in parallel with the progress, with the R&D progress. So I'm looking forward to a more sort of organized standardization, at least in Canada, the US, and Europe and Australia. We can do that, and so. I don't know, maybe Reza has more insight.
Yeah, I mean, you are right, Maria, but if you look at the security, for example, ETSI is very well advanced. I mean, it's a well-defined interfaces now. You can run interoperability tests. You can have multiple vendors. It's a on the key managements and interface with devices are very good effort is advanced. But when you look at the internet or IETF and so on, I think what Maria said is right. I mean, we are it's worryingly behind the curve of the technology. We need to start looking at what would be a routing protocol look like in a quantum internet, and what would be, these sort of things are still being discussed. There are working groups, but it seems that security is going very, very fast to a standard, but the rest no.
I agree.
Why is that actually, Reza? I think is it because really people are just experimenting with building quantum networks? I mean, the rates are extremely abysmally slow, low, and
I think people if you look at the product that you can buy, there are many on quantum security. Therefore, this industry pushed the standardization. But on the networking side or computing side, really, except a few startups that sell to the labs, there is nothing there yet. So I think the industry needs to be a little bit, they don't have that urgency to produce like the security at the moment.
Right, because afterwards, if everybody has their own, then you are having kludges, and kludges are going to be suboptimal, as we know. So.
Right. You'll end up with ugly boxes like the network address translation, which is a fix to a problem that shouldn't have existed in the first place. Right. So no, I totally agree with you. I think as much as I see, right, I think maybe it's also because the technology is still fairly nascent. I mean, there's a lot of efforts in various labs, but it has not really caught that widespread industry partly because even if I were to sell a quantum switch today, right, the question is, what do I do with it, right? Let's say I can interconnect like, maybe a few quantum processors, but what do I do with it is always the question. So it's like a chicken and egg problem, right? So what is that killer app? And that's why actually I was like asking that question. What is that killer app that is going to really hit that inflection point as far as, industry jumping in and saying, let's mass produce these devices and make sure they're all interoperable and really build this like next generation quantum network, right? That then, I mean, we can build all of it to your point, Maria, as well, right? You were mentioning we can build this. Well, maybe the technology is still nascent, but we can still build it. But what do we do with it?
I think this is why maybe the labs are providing a user base and sort of like building it and having users. So let's have a switch with users and let's see what the users come with in order to do something. Yeah. And then I think the labs, the national labs provide a very good sort of user base beyond the security. On the security side, I think what Reza said is there is some impetus there to have more.
I think that makes a lot of sense. So from your perspective, right, I mean, just segueing into the next question, so what should industry players really focus their efforts on at this stage of quantum networking?
Reza.
So to me, I mean, already, I mean, the quantum security, let's say, is flight off commercially very fast because there was a good investment from governments and then a lot of startups and then bigger companies start to either absorb startups or use the technology and build on top of that. So that's, I think we need to see the same push on the networking and the computing. On the computing, there is a good investment from the governments and national investments. There is a activity going on from the companies, but on the networking side, I think although there is a good investment from the national initiative, but there is a less emphasized by companies, which I don't know why. This is a question for me. People like Cisco or incumbent vendor that they do the networking to try to support academy to bring the technology to commercialization for networking beyond security, connecting computers and so on. We see the clear benefits was explained, but I think there is not as such of urgency from industry to do treat it as like they treated the security, and they took it very fast, develop it very rapidly. But on the networking side, I think industry needs to a little bit play a more significant role.
Yeah, and I agree with everything Reza said clearly. But I want to say also that, whatever industry is doing on the quantum computing side, there has to be a robust part of it that it is not hype. So that when we are talking about actually connecting processors, the part of the processor is not just over, the more demonstration on why do we need to connect quantum processors and what is the actual advantage of connecting them quantumly, and the quantum processors should not just be kind of like overblown, but kind of where they are today, so that the networks with edges, with quantum computing on the edges, have some sort of story to say. And I think probably the quantum computing industries, when they say that they will make their local clusters and they will quantum network them locally or in a local area or more widely, I think that gives impetus also to quantum networking companies to start working on that, other than just research demos and lab demos and fielded, but some more investment on the actual networking side. I think that would help. And again, the researchers should do what they can on the research side and on the demo side, and then the industry has to actually come through with that.
No, that's
Just to add to what I mean, Ramona, if you add one more thing on top of what Maria said, if you look at the startup scene, you see the massive number and investment on the quantum computing, a massive number and investment on security, although security become less and less. But there is a very little, very few, you can count it with the finger of the one hand, the quantum networking startups.
Mm-hmm.
So this,
No,
I think that's a major problem and bottleneck at the moment, yeah.
But I think what you said is interesting, right? So the reason why I think quantum security took over is it's kind of it's an application at the end of the day, right? Networking is not an application. Networking is an enabler for applications, right? So unless you have applications, creating a marketplace for a network remains hard, right?
Correct.
That is the biggest thing. And this is where I feel like maybe quantum sensing, maybe distributed quantum computing. Either of these two are probably, especially distributed quantum computing, just based on what Jerry's talk was all about, that part is very, very much, I think, what probably will catalyze a little bit of this quantum switching industry, perhaps. And quantum sensing, I'm thinking it's going to be a little bit more wide area, right? Because you have quantum sensors that are going to be deployed everywhere, and your quantum computers or quantum supercomputers are going to reside somewhere in the cloud. And you need to not lose fidelity of your measurements in the quantum. So therefore, you have to transmit those, that measurements in the quantum realm and not serialize it to classical realm. You lose the fidelity. What's the point of having an expensive quantum sensor if you can't process it appropriately? See, these two applications I do see are probably the near-term catalysts. But beyond that, I'm still, it's, quantum sensing is not necessarily it's like a WhatsApp application where everybody will start using it, right? It's gonna be a niche application that maybe NASA would care about, or a few other folks. How do we make that, or maybe some other application which really catalyzes the need for a real large scale quantum network? I think that is the interesting dimension in question in my mind.
And there is a lot of vision about that, but the action is the how do you execute the action, and how do you have from the research side all the way to actually field the application and see how it works and if it works. So there is a lot of visionary ideas about networks for scanning gravitational fields of asteroids and figuring out what is in there, and understanding, in geology, in imaging, for anything. So at some point, all this whatever we have sensors for anything, we will have quantum sensors for everything, and they have to be processed somehow. And so this is where the rubber will meet the road, and we will have to do it in the optimal way, not suboptimal way.
So another question that came in during your talk, Maria, especially, is around what level of, the question is around, at what level of functionality will we see quantum networks being useful for fundamental physics research?
Oh yeah, I think that's this is something that we are working a lot with the DOE in terms of. So you have seen, first of all, the squeezing at LIGO and all of these quantum metrology methods. This is going to be all these quantum interferometry type of measurements in order to figure out space-time deviations from general relativity, and figure out if we have some sources of disturbances of space-time that are not within Einstein's general theory of relativity, and they can reveal something about the quantum makeup of space-time, or the role of entanglement in creating the fabric of space-time. And then with all the quantum sensing. I mean, the detectors in particle physics are sensors. They become now so precise that you can have arrays of those sensors, how you read them out, if they're cryogenic. All of these technologies are being employed in order to figure out experiments for dark matter. And we are looking at quantum sensing for the collider experiments, so quantum detectors. Eventually, I think once you push the limits of precision in the various sort of axes, be it space, time, energy density, etc., and you arrive at exquisitely precise measurements. It's all quantum sensing after that, and it's the challenge is optimally using it, not just having the quantum sensor and then dropping it, as you said, in classical sort of processing, but doing it for real, because that will give us the big Feynman dream, where we can actually reveal, understand the nature at the quantum level through and through, not with intermediate sort of collapses.
Or quantization effects, right?
Yes,
Like,
exactly.
yeah, you're converting a quantum signal into your classical, and then you lose a lot of information, and
Exactly.
this ties
And
back to our previous discussion around.
yeah, we do know about that, because when we have billions of channels that we read out and then we drop the information, well, why did we do it at this level of granularity if we're going to drop the information or aggregate it? So there is some interrogation on how to do that optimally, and think through from the beginning, or as we learn at least how to do it, to do it optimally.
No, that makes a lot of sense. I know we're kind of approaching towards pretty much the end of the allotted time, but I'm trying to see if there's any other audience questions. I guess somebody mentioned.
I'll come and meet you in Santa Monica, though. That's a question of mine. That's a statement. I want to
No,
see
absolutely, Maria.
Maybe we'll drop a link from Caltech to Santa Monica. How is that?
That would be fantastic. Let's absolutely make something like that happen. And ideally via London, so that, or Bristol.
You can do
So
that.
Well, we have already a link to both UCLA and UC San Diego. I mean,
Yeah.
whichever.
Let's do it. Let's connect and start doing complex architectures.
Yeah, I mean, I used to teach networking class, way back when I was a professor. But there's this classic napkin on a paper, like there's like 4 nodes, right? The UCLA, SRI,
Yes, the ARPANET.
the ARPANET.
Very good.
That's the equivalent of where we are right now. But
Let's do the quantum ARPANET.
quantum ARPANET.
Connect
Exactly.
also with Berkeley through Las Vegas. There is a lot of vision. Let's start drawing the lines and dropping the nodes.
Absolutely. No, I think it's been a wonderful panel. Thanks for sticking around and participating in this very enlightening discussion. And I learned a lot, certainly, and I hope our audience has also learned a lot. There's still a lot more to do, and there's a lot of information out there. It's sometimes a little bit too dense for average computer scientists to sort of understand all the intricacies in the quantum realm. But
Yes.
I think that's where
Let's
a lot
not
of
stop
challenges
at Fourier transformations, please.
Is that where you would want our audience to get started on?
No, let's not stop at Fourier transformation.
Oh, I see.
Fourier transformations.
Yes.
Let's not stop there. Let's go beyond that.
Absolutely. But yeah, wonderful having you, and I hope it was a great session for our audience as well. And with that, I think it's time to thank you once again, and maybe we will cut into a break. Thank you all for sticking around, and we'll meet
Thank you for having me.
already.
Bye.
And there is a very interesting afternoon session, so
I will
Yeah,
definitely.
stay tuned for the technology session at 12:30 in about 45 minutes.
Bye.
Thank you all.
Bye-bye.
I'm excited to officially announce our Outshift newsletter called The Shift. We'll be covering exciting news and developments across emerging technologies, business impact, and AI advancements. Subscribe today.
Hi, my name is Vijay Pandey, and I lead Outshift by Cisco. Outshift is Cisco's incubation engine, responsible for delivering what is next and new for Cisco in emerging tech areas such as modern applications, generative AI, and quantum. As organizations rally to capture the potential of generative AI, much remains unknown. How can enterprises manage the complexity of AI-first products and tools to drive innovation? How do they determine the best use cases that can be scaled to achieve competitive differentiation? And what software and hardware solutions should be used to accomplish this? These are all valid questions. Today, I'm excited to share Outshift's initial thoughts on how the world is rapidly evolving with the advent of generative AI in our first ever AI series. It feels like it was just a few years ago, folks were talking about an AI winter, about money, research, and product hype shifting out from AI towards quantum computing and other ventures. Now, quantum is yet another step function waiting to happen, but that's for another day, another conversation. For now, with generative AI, we are rapidly and continuously evolving at exceptional speed. It's hard to keep up with everything going on. Difficult for us, even as technologists, to imagine the plight of the customers and the consumers and the creators. The questions we hear quite often are, how do organizations keep up with this pace of change, stay relevant, build durable products or processes around generative AI? Where do you even begin? Like most companies, we too are navigating these complexities. There's a hype cycle, the AI washing of everything. But this is a technology that will fundamentally pivot us into a different world for sure. At Outshift, we are seeing that generative AI is both driving up productivity and creating new products with innovations across applications, data, and models. Enterprises want to adopt generative AI and build game-changing products, drive up both productivity and value from it, consume it, and build products around it. There is a sense of elation in certain use cases and massive hesitancy in others. The hesitance comes from security, from trust, IP infringement, bias, fairness, scale, and cost concerns. As the technology industry evolves, we at Outshift want to help our customers establish their game-changing experiences and help them manage these growing concerns. We are eager to share more with you soon. Stay tuned for upcoming conversations with AI experts and influencers. We'll discuss how to deploy and manage AI in the enterprise and how to achieve the potential of enterprise-ready generative AI applications.
Hey, welcome back, everyone. Today, we are going to invite 4 speakers for our afternoon session. But before that, we would like to review the pool questions we have from the audience. It seems that most people today are from the quantum communication and networking side. But surprisingly, we do have a lot of audience joining with no quantum background. This is definitely a good signal for us because the general public are paying more attention towards the quantum technology. Okay, back to our physics. As we know, building a global quantum network not only requires system-level planning, but also relies on the development of component level. Today, we have luckily invited 4 speakers from different backgrounds to talk about the most recent advancements in quantum devices. So before we take off, let's have a quick forecast of how long will it take to have a multi-node quantum network with gigahertz rate and unit fidelity. The pool will be here for the entire session, and please leave your answers. Now, let's welcome our first speaker, Professor Kai-Mei Fu from University of Washington. Professor Fu received her PhD degree in applied physics from Stanford University in 2007. She started her quantum photonics lab at the University of Washington since 2011. Her current research includes integrated photonics for quantum devices, defects, entanglements, as well as their applications in quantum sensing. Now, let's welcome Professor Fu to the stage.
Okay, thank you very much for that kind introduction. And it's my pleasure to talk to you today about our work using quantum defects and frequency conversion for quantum networks. And I'm joining you today from the University of Washington in Seattle. And so this is quite a diverse audience we saw from the poll. So I welcome questions, throughout this presentation. So as an overview, I'm going to introduce quantum defects, what they are, how we make them and use them and integrate them into devices in Diamond, and then end my presentation talking about frequency conversion, which will be needed for most quantum defects for realizing scalable quantum networks. Okay, so you've already heard in the morning about quantum networks, but there are people that are quantum new. So just as a reminder, so in this network, we have nodes. The nodes are qubits, which can be in superpositions of 0 and 1, and then they're connected by edges, and these edges are signifying entanglement. For my talk, these nodes are actually matter qubits, so very similar or exactly what you've heard from Ronald Hansen's group in the morning, where the edges are denoting entanglement between actual spins, physical spins. Okay, and of course, there's 2 types of general applications for quantum networks. One is the communication type networks that are very large scale edges, and then the other is actually a universal quantum computing networks where the edges would be very short in this case. All right, and so what is a node? When I'm talking about a node, I'm talking about a qubit, and this entanglement has to be generated. So in each node, there needs to be 2 states, something that can store 0, 1, or a superposition of the 0 and 1, and at least one of these states needs to be coupled by a photon to an excited state. I'm not going to go over the protocols over how you generate the entanglement, but it's this coupling to a photon, which enables you to create this edge between this. So we're looking for some type of qubit that also has a 3rd level that can interact with a photon. All right. And when we look at this kind of abstract level structure or energy level structure, we need something called a ground state spin coherence. That's actually the memory time of your quantum bit. You, of course, need to be able to initialize your quantum bit. You need to, in these protocols, be able to address just a single one optically. And the photons that get emitted from these centers need to be identical. And that means the time bandwidth properties of that photon, whether from any single emitter in your network, need to be identical. And so we often think of atoms as being able to have multiple energy level structures that can satisfy these requirements. As you heard earlier this morning, this can also be defects. So for example, the nitrogen vacancy center in diamond, and these are just little chips of diamond here that can be commercially purchased. If you remove 2 of the carbon atoms in that diamond lattice, replace one of a nitrogen and leave one as an empty site, then you're going to get energy level structures that can allow you to do these network protocols. In real life, in a spectroscopy lab, the energy level diagram and the processes that happen for a defect, and even for a single atom, but a defect's even more complicated than an atom, is quite complex. So what you end up doing is measuring and studying all of the energy levels and processes that occur, and then distill out the energy level structure, or isolate out of this complicated structure the energy level structure that you needed for creating that entanglement link between 2 of these defect nodes. In the 3-node network that's been realized with NV Diamond, and so this is the only like long distance memory network that has been published. The fidelity between 2 of these links, and this was 0.8. The hertz, so you just heard, when are we going to have gigahertz rates? The rate was close to 10 hertz in this really amazing demonstration. And then the 3-qubit fidelity, so this is called the GHZ fidelity, was about 0.5. So this is not going to be near-term secure communication. And there are certainly many challenges associated with building up these networks, technical challenges. Two particular challenges regarding this rate is photon collection. How do we get every photon that these defects emit? Currently, they're really getting mostly lost. And then if you do create a device that can get these photons at high efficiencies, how do you keep these photons staying identical? That's going to affect the fidelity. So the collection, your ability to collect the photons affects these rates, and your ability to not disturb them is what's going to affect these fidelities of the quantum entanglement. Okay. And then there's, of course, the question of, can you distill the type of energy level structure you need out of here? I think in general, the belief in the community is if your crystal is perfect, you really understand this Hamiltonian, then yes, you can. But then as you go on into the future of scalable quantum computation or networks or sensing, I also show a device that's made for sensing. Your question is, can you distill the properties that you need, like this 3-level diagram of indistinguishable photons, inside an integrated device, right? That's the outstanding challenge. And so, as I mentioned before, the photons and the defects have to be identical. They're like atoms, but we're now in the solid state. And this is challenging because unlike an atom that's trapped in high vacuum, that's cooled to ultra low temperatures, we're in a crystal. And your nearest atom in the crystal is only a few angstroms away, which is fine. But if you are parts per million purity, you have an unwanted purity that's only a few nanometers away. So the material level of purity has to be really, really high. Additionally, these qubits, they are excellent sensors as well. So surfaces, things that you fabricated, they're also being perturbed. So there are many ways that we attempt to improve performance, and I'm just going to talk about the different tactics that are all extremely active areas of research. One is defect discovery. So today I'm going to focus on NV sensors in diamond and a little bit about silicon vacancy sensors in diamond, but there's actually a lot of quantum bits that are being explored, like erbium for telecom emission, and defects in silicon are getting rediscovered. They were discovered a long time ago, but they're rediscovered now for quantum applications. This is a very active area. Materials innovation. I said parts per million purity is not good enough for quantum communication and quantum computation with these defects, because they're so sensitive to their surroundings. And parts per million is considered good enough for most applications. So now there's materials innovation. How do we get to higher purity levels? And also, how do we measure that? Because not only do you have to achieve it, you have to be able to measure it. Protocol developments, how do we develop things that are robust to the errors that we're seeing? Tuning, just as the defect is sensitive to things that are unwanted, you can put down controls when you're in an integrated device, like a defect in diamond, in order to undo what the environment is doing. And then the focus of today's talk is emission enhancement. How do we make the photons emit preferentially where we want them to go? And then frequency conversion as well. And both emission enhancement and frequency conversion, they're both better for collecting photons, not losing photons, and also for mitigating the fact that defects emit at different photons that are slightly different, which I'll talk about as well. Okay, so moving on to the second part of the talk is creation and integration of diamond-based defects in devices. All right. So every atom-like or defect-like quantum memory is going to need to be emitting its photon in a preferential direction, and that photon's going to need to be captured. There are also protocols where perhaps you're looking at the phase of a photon that's reflecting off of a cavity that has a defect in it, but the requirements turn out to be very similar. So we'll just imagine that the only requirement is that you need to collect this photon. And if you put the photon in a microcavity, a microresonator, then what happens is that you've enhanced the probability of the photon to be emitted into the cavity. And that is, and you can actually mathematically quantify what that enhancement is. But normally this atom wants to emit photons in every single direction. Now that I've put it into a cavity, and assuming the quality factor of the cavity is high enough and the mode volume of the cavity is small enough, I can get this photon to emit into the cavity, which can then be coupled to a fiber or coupled to a waveguide, coupled to a fiber. So putting it in a cavity shortens the lifetime of the emitter because you've made it emit more often, which coherently broadens the line width. So if they are emitting at slightly different frequencies, they're more identical. So that's a plus. And it also enhances collection because it adds directionality to it. We perform all of our fabrication at the Washington Nanofabrication Facility at the University of Washington. The type of devices that we make are planar devices, typically. And we do this by using a light guiding layer, which is the semiconductor gallium phosphide, which we have deposited or assembled onto the surface of diamond. And before we have assembled this, we've created these nitrogen vacancy centers right near the surface of the diamond via implanting nitrogen and doing a high temperature anneal of the diamond itself. In this way, we're interacting with the evanescent field that's in this cavity. The NV center emits into the cavity, which then can be coupled into this bus waveguide. Why are we using gallium phosphide? We're using it for this application because it's a high index, large band gap material. And these defects are emitting in the visible frequency. These are red photons. I want to draw your attention to other types of hybrid platforms. One is you can do this with silicon on top of rare earth doped oxides. So this has recently been done for erbium, which is a rare earth defect. We can't use silicon because our defects, the NV center is invisible and the silicon is just going to absorb those photons. And in fact, finding something that is relatively high band gap and high refractive index, because we're also working with high index diamond, is challenging. And there's only a handful of materials known that even theoretically can do this. And so we're focused on gallium phosphide in this case, where we make the gallium phosphide again on top of the diamond. Right. So in prior work, actually from 8 years ago, we had these hybrid devices where we could excite a nitrogen vacancy center, and then we could couple the light into a bus waveguide, and we could collect and analyze the photons. And it worked quite well in terms of a photon collection efficiency. But if you're looking at the spectrum of the light that's emitted as a function of time, here we're tuning the cavity onto resonance, and suddenly we get a lot of light that's coming from that defect out of the grating coupler. You can see that there's a little wiggle. Oops, that's happening. And this little wiggle might not look like much on this resolution, but it's enough to completely destroy the indistinguishable nature of the photon. So these photons that are in Ronald Hansen's work, which are in these solid immersion lenses that are 10 microns from the surface, that are not in an integrated device, don't have this large wiggle. And in fact, we attributed this wiggle from the fact that we're etching into the diamond itself in this case. So just to test this, we also looked at inverse design photonics a few years ago, where this is for a planar geometry, where you can collect from the top surface from implanted centers. Again, in this case, it's about 100 nanometers from the surface. And here you can see these inverse design photonics. They're quite nice. You can get like a 14-fold enhancement of the emission in these devices. And when we did this, you can see that there's actually no diamond that happens, no diamond etching that occurs in these types of devices. However, just the exposure to the plasma that etched this gallium phosphide caused the defect charge state to change. It could be recovered, but whereas you look at the spectral diffusion before device integration and device fabrication, afterwards it's much degraded, and this is a 3-fold larger scale bar. So from this prior work, what we've been working on are ways that we can avoid all diamond fabrication completely. And I think for using quantum defects, that's going to be it's a very promising route. You just let the defects be optimized in their material, how they want to be, and and then just assemble the device on top of them. Additionally, for this next study that I'll talk about, we are using a different defect. We're using the silicon vacancy defect, which is centrosymmetric and is less disturbed by electric field fluctuations in this case. And so the idea here is that we pre-design a cavity. So this again is just like this cavity here. It's not one of these whispering gallery cavities, but it's a photonic bandgap cavity, which confines the mode. And because the silicon vacancy wavelength is slightly longer than the NV center, it's around 730 nanometers instead of 630 nanometers, we can find designs on diamond that can hold a cavity mode, even with this tiny mode volume. And what you can see here, at least on the scale of these measurements for this particular defect here, which is labeled P1, you don't see the spectral diffusion, and you can again see the enhancement of the light that's emitted into the cavity and then out of the gratings. In this particular case, we do have some spectral diffusion. Our measured cooperativities are on the order of 0.1 to 0.5. This is for the experts in the room. Up to 10 turns out to be possible. We're now working with defects that have been annealed and created from collaborators from Ulm University, which don't have the spectral diffusion, and the next generation of devices. To put this type of planar geometry in perspective, most work in diamond is actually engineering 3-dimensional structures out of the diamond itself that are suspended membranes. This is really beautiful work that that's led out of Misha Lukin groups and Marco Lonkar's group at Harvard. They just recently showed a 2-node network out of the silicon vacancy. Their cooperativities in each node, one was 12.4 and one was 1.5. So the cooperativities that we can get in this hybrid planar geometry are starting to approach what you can do in all diamond, actually etching three-dimensional structures in this case. Okay, so then in the last part of the talk, I'm going to talk a little bit about multi-resonant sum and difference frequency conversion. So as I mentioned before, we want this types of structure, this three-level structure in order to create entanglement. And the way the entanglement is generated is you collect the photons from each of these defects and you interfere them on a beam splitter. And depending on the click of the detector, you can herald an entangled state between these two defects. However, if you look at the loss in a fiber for the most common and most promising defects and emitters, it is quite high, and you really want either defects that emit at 1550, such as erbium, but erbium also doesn't emit photons very readily because it is a rare earth ion, or you need a way to convert the light from these shorter wavelengths to the longer telecom wavelengths. And so you can do this with material that has a chi-tune nonlinear coefficient, and where you mix the difference between the two frequencies, a coherent field that's a classical field of many photons, to convert one color frequency to another color frequency. And this is been done with nonlinear waveguides, integrated resonators, with single resonance enhancements, in all of the protocols for quantum networks that are more practical now, where they get the 3 nodes, for example. These are kind of bulk waveguide devices that they're using. So they use a lot of power, but that's okay because there's not yet that many nodes. So what I'm going to talk about now is how do we get to lower power frequency conversion. All right, so what we want to do, of course, is have 2 of these processes where we can convert our visible wavelength to 1550 so we don't lose photons anymore. Additionally, you can see that it can also convert the wavelength to the same frequency if these are slightly different, and then we can do the protocol. So this is kind of getting, 2 birds with 1 stone if you can do this efficiently and well. Right? And so before I mentioned that we are interested in gallium phosphide because it had a high index and large band gap, but it's also notable that gallium phosphide has a large chi-2 nonlinearity, chi-3, and also acousto-optic figure of merit. I'm not going to go through these. This is mostly not my work, but I just want to do a call out to this material that has now been recently used for frequency combs and also microwave to optical conversion, which could also be interest for quantum network applications if the qubits, for example, are superconducting qubits, and then you want to go to the optical domain. What I'm going to focus on today, though, is triple resonant sum frequency generation. In all of this work, this is all done with non-commercial gallium phosphide, which is grown on very small gallium phosphide wafers. So just a call out to some recent work that we have. I mean, materials development is a pretty huge part of these quantum technologies, is that we're now looking at 12-inch wafers of boron gap that is lattice matched to silicon for these applications of these hybrid technologies. And here is the reference for this new material for frequency conversion. Okay, so in this particular case, we again have these cavities, but now these cavities are supposed to enhance the field at our quantum defect, at our mixing coherent field at 1080, and then at the telecom. And our goal is to get this triple resonance to occur. All right, and so these types of devices that we make are gallium phosphide on oxide, and these are the standard dimensions. So it's about a 10 micron wide ring in this case. You can see we end up with slightly different wavelengths than the design wavelength. And what we do just to find this triple resonance, originally these resonances are not happening at the triple resonance condition. And so what we actually do is we temperature tune until all of these come on to triple resonance while we're using a very broad band mixing coherent pulse laser in this case. And so as we tune the temperature, this is on a log scale, this is on a linear scale. As we tune the temperature, what you see is here is when the telecom is coming on resonance with the visible. Here is when the pump laser is coming on resonance with the visible. Here is when all three hit. And that's what really lights up here in the visible, in the linear scale in this case. So with these types of devices, the published results can be found in the publication down here. We're focusing on engineering the photon after emission. We get a small signal conversion of 8% per milliwatt with optimized coupling and fabrication. These devices could work as 45% per milliwatt, which means you need a few milliwatts of power in CW. So when it's pulsed, it's much, much less power to achieve this. The outstanding challenge, however, is that these worked by tuning the temperature to hit that triple resonance, so we can get this enhancement factor to get these low power frequency conversion to happen. And long term, we need this triple resonance to happen at really specific frequencies. We can't just tune them all until they magically line up. And so that is an outstanding challenge that we're working on right now. So in summary, I hope I give you an introduction to defects as the quantum memory nodes for networks, some of the challenges that we're facing, but there are also opportunities to meet for device fabrication with these defects, and then frequency conversion as a promising way to convert to telecom and to mitigate inhomogeneities. The people who are in my group right now that really contributed to this work, Alan Logan, Nick Yama, and Christian Pedersen. I'd like to acknowledge our funding, and then since we're not in person, just tell you to come out and visit us, and of course, come and see beautiful, beautiful Seattle. Thank you.
Thanks, Dr. Fu. We do have a few questions here. The first one is that people is curious about how scalable these quantum emitters based on diamond defects.
Yeah. So right now it's not so scalable. Right now, we're not collecting enough photons that are indistinguishable enough to scale to many, many qubit nodes, right? And they're not identical enough. I think the huge breakthrough is going to be, so let me just see, I put in a number. Numbers are nice, right? I think a huge breakthrough is going to be when we can reliably, with photonics, get high cooperativities. And that's something that's happened in superconducting qubits, which enabled a big leap forward. And we're kind of just at the point of seeing them. So some devices can have them, some devices cannot. So now the question is, how can we get this reliable? And I don't think that is an impossible task. We're really, really close to being able to do this.
Understood. Appreciate. I have a few other questions. The first one is that you mentioned indistinguishability is not that good from current diamond defects. So I think, for most solid-based qubits, the broadening is a big problem. So how do you well control your broadening to make sure that this indistinguishability is good enough to have a good home Mando dip?
Yeah. So again, I think it's going to be multiple things, and I think a device is going to have all of these in the end. And the key to this is going to be not having to look and tune everything, having something that's auto tuning. And so there's going to be three things. One is the materials. Like, you need to be able to create them so they're good enough to start. And this already is true with the silicon vacancy near the surface. The second one is you will want this Purcell enhancement, right? Because it's going to mitigate. And then the third one is you will want, just like superconducting qubits, is not different, right? They're always tuning them. They're always
exactly
tuning them. With defects, these electrodes are going to have to be part of the device. You're always going to have to be listening and tuning to make sure that they haven't drifted too far out of compliance.
Yeah, understood. Thank you. So regarding the material you are using for your transducer, you are using gallium phosphide. But if I remember correctly, I think Lukin's team, they are using periodically pooled lithium niobate. So what is specific advantage of using gallium phosphide here?
So periodically pooled lithium niobate, the index of refraction is too small for working in high index material. So maybe if you're on silicon and you're doing everything on low index material, that part is fine. The Chi2 nonlinear gallium phosphide is actually higher than that of lithium niobate as well. So those are two potential positive sides. So it'll be really interesting now that the material's at 12-inch and available to see how good gallium phosphide can be.
Makes sense. Thank you, Dr. Fu. We are running out of time, but thank you for joining us today.
Thanks. It was a pleasure to be here.
Yeah. Okay, so let's welcome our next speaker. Our next speaker is Dr. Matthew Chow. Dr. Chow received his PhD in physics and leading the superconducting nanowire single photon detector research team at JPL since 2012. His current research includes superconducting detectors, free space optical communications, quantum communication, as well as applications of time-resolved single photon detectors and contents. Now, let's welcome Dr. Chow, and the stage is yours.
Thank you very much for the kind introduction. All right, so I'm Matt Chow from the Jet Propulsion Lab here in Pasadena, California. And I'm going to be talking today about superconducting nanowire single photon detectors. I just wanted to first call out all of the folks who are actually doing the work here in the lab. So there's a number of JPL staff members who work at least some fraction of their time on this project. And then we also have a few postdocs and grad students who are doing their PhD research with us. I also just wanted to highlight we have very close collaborations with the SNSPD groups at NIST Boulder and at MIT campus, Carl Bergren's group. So our three groups really kind of operate like one big operation, which has enabled a lot of very fast development. And we also have a network of collaborators that use our detectors in different kinds of science applications. And we also are always looking for more students and postdocs in particular, and even nanofabrication engineers. So feel free to contact me if you are interested in what you see. Okay, so I'm going to be telling you today about superconducting nanowire single photon detectors, which are detectors for time-resolved single photon counting. These are detectors which click when a single photon arrives. They're really truly a digital detector, and they're digital right from the moment that the photon is first absorbed. So the way the detector works is actually pretty simple. It's a superconducting wire, which is about 5 nanometers thick, typically, and anywhere from 100 nanometers wide to even a few microns wide. It's meandered to fill up some active area on a substrate. When a single photon comes in, the heat from a single infrared photon is enough to switch the wire out of its out of its resistive state and out of its superconducting state and into the resistive state. So when that happens, the resistance of this wire jumps from being basically 0 ohms to being a kilo ohm in a matter of picoseconds. Then the current, which you flow through this wire, which can be kind of a lot of current, can be up to 10 microamps or so of current. It suddenly doesn't want to flow through your nanowire anymore. It will want to flow through your amplifier if you hook an amplifier up in parallel. And so this gives you a very nice voltage pulse out that you can then cut a threshold and know to very high accuracy exactly when the photon arrived. And this doesn't have a lot of negative things like after pulsing or crosstalk or other issues. We typically enhance the efficiency of detectors by embedding them in a quarter wave optical stack. So we may start with a silicon substrate and then deposit a mirror, either a metal mirror or a DBR mirror, and then a quarter wave of SiO2, and then our nanowires, and then another quarter wave of SiO2 and an AR coating. And so with that, we kind of keep the nanowires at the antinode of the electric field, or if you prefer to think about photons, we let the photons bounce around a few times until they hit the nanowire. So this technology has made a lot of progress in the last few years, and there continues to be more progress all the time. So this is sort of showing highlights of some of the recent results from our three groups, MIT, NIST, and JPL. So our colleagues at NIST have shown, these are all world records, actually, by the way. So our colleagues at NIST have shown high detection efficiency, as high as 98% system detection efficiency at 1550 nanometers a few years ago. So this is actually, this includes all coupling losses to the detector and such. So if you put 100 photons in at the top of the cryostat, you get 98 clicks. The detectors have extraordinarily low dark counts. They actually have the intrinsic dark counts have actually been shown recently to be below 10 to the -5 counts per second, which is less than 1 dark count per day. In most practical applications for, quantum networking and quantum information, your detector is open to some, room temperature backgrounds. And so you're dominated by room temperature background loading. But the actual intrinsic dark counts of the detector are extraordinarily low. And this has actually made the detectors extremely interesting for dark matter detection applications and some astronomy applications involving very rare events. We've also been working throughout our institutions at really extending the wavelength range of SNSPDs to very funny wavelengths. So our colleagues at NIST have made SNSPDs going down to almost to the Lyman alpha line, 100 nanometers in the UV. And at JPL, we've been really working on increasing the decreasing the energy threshold of the detector to go out to really, really long wavelengths in the infrared. So we recently have some results with some detectors fabricated at JPL where we actually have done time resolved single photon counting out to 29 microns in the far infrared. And we actually are optimistic that we can push this further, perhaps as long as 100 microns. And this actually opens a lot of new potential science opportunities for doing time resolved single photon counting at really, really long wavelengths. I have some more slides on this, so I won't totally dwell on it now, but SNSPDs have been, we've been able to make them with very large formats. So we worked on a project with NIST. This device was fabricated at NIST, where using a time domain multiplexing scheme, NIST was actually able to fabricate an array of 400,000 SNSPD pixels in a single array. So this is a 500 rows and 800 columns SNSPD array that was recently demonstrated at NIST. And this is the largest superconducting detector array by about a factor of 20, and actually puts for the first time SNSPDs onto the same sort of footing as some semiconductor detectors, and opens up a lot of new possibilities for doing time resolved imaging with SNSPDs. So that can be very relevant for quantum imaging or biomedical imaging or remote sensing, other applications. We worked on a project a few years ago to demonstrate a very high time resolution in SNSPDs. We were able to get the jitter down as low as below 3 picoseconds in the visible and below 5 picoseconds at 1550 nanometers in a sort of specialized structure appropriate for waveguide coupling. And I have some slides here. I'll tell you a little bit about, if we have time, some detectors that were really meant for quantum communication. These are detectors that can count at 1.5 gigacounts per second while maintaining 100 picosecond time resolution, which is exactly what you need if you want to do quantum communication on a 10 gigahertz clock. And so we have these peacock-shaped detectors that, I can send you the paper if you're curious. Okay, so these are some of the applications that people have wrapped their head around so far for SNSPDs. One thing that is near and dear to our hearts here at NASA is using SNSPDs for free space optical communication. I'll tell you a little bit more, but we've built optical communication ground terminals for a few NASA LaserCom demos. I have some slides. We're particularly excited about this deep space optical communication project, which will be the first ever demonstration of optical communication from interplanetary space. It's supposed to launch with the Psyche spacecraft as soon as Thursday. Quantum information science, obviously, is a community that has latched on to SNSPDs very early. You put these two things together, you get space to ground quantum communication, which is a very natural application for SNSPDs. But then there's also a number of potential very interesting applications for SNSPDs in astronomy, in biomedical imaging, remote sensing, and fundamental physics. We have a couple of collaborations with folks who work on dark matter detection experiments using SNSPDs. So this is just very briefly, I started to mention some of the work that we do in support of the NASA laser communication projects. So we've built these ground terminal instruments where we have SNSPDs. There are really two main space missions that are upcoming, which will be demonstrating free space laser communication capabilities. One is this deep space optical communication project, which will go out to the asteroid belt, to the Psyche spacecraft. So this will be the first ever demonstration of free space laser communication from interplanetary space. The longest range demonstration that was has been done so far was from the moon to the Earth in 2013. The Lunar Laser Comm demo, which we were also involved with. But this DSOC project will, the moon is of course 400,000 kilometers away. DSOC will work out to about 400 million kilometers. So it's actually 1,000 times longer range than any other laser comm demo that's ever been tried. So which means it's 1,000,000 times harder in terms of the amount of light that you get back. The laser spot, when it reaches the Earth from those very long distances out beyond Mars' farthest range, is about 1,000 kilometers. So if you imagine even with a 5-meter telescope, you have a very tiny pinhole in your 1,000-kilometer laser beam. So you are deeply, deeply, deeply in the photon-starved regime, and you have to do time-resolved single photon counting. You only really get single photons back at the receiver. And so what you see is that a lot of the instrumental requirements for doing deep space laser communication are actually very similar, if not even more challenging than space-to-ground quantum communication. So it's a very natural, a lot of natural synergy between some of what's going on these days in classical deep space laser comm and space-to-ground quantum comm. The other thing I should say about DSOC, it will work at up to 267 megabits per second at short ranges and a few megabits per second from like Mars' farthest range. So, okay, for DSOC, we had to make a detector that could count at about a gigacount per second and was large enough to couple to a 5-meter telescope. So we made an array of 64 SNSPDs that were meandered to sort of fill this 300 micron diameter active area. And this detector can do that. So it's free space coupled, has a 78% system detection efficiency, and can count at about a gigacount per second. We couple the light into the cryostat through a series of filters to block out the infrared blackbody radiation. And so it's this free space coupling. This is kind of what the cryostat looks like. This, you can see, is one of the things that kind of enables some of these time-resolved imaging applications that I was mentioning, is that you can stick either this sort of quad cell detector that's there in behind your lens, or you can put an array of detectors that's pixelated and actually do imaging into the cryostat from a setup on the optical table. And so that opens up a lot of really interesting possibilities to have whole cameras of SNSPDs that you can use in different kinds of experiments, maybe quantum imaging experiments and other things. This is showing a little bit what the readout sort of looks like, where we have 64, it's a 64 element detector. Each detector has its own readout line, which means we have 64 amplifiers inside the cryostat. These are not the world's lowest noise amplifiers. They're cheap cell phone amplifiers, but they work fine. And then we have worked with a colleague of ours in Austria, Thomas Lehner, who has made a series of very fast high bandwidth time taggers that can keep up with this very large stream of data. So for DSOC, we use one that streams data at a 1.5 gigatags per second, but we actually have one that he has been using that actually streams at 6 gigatags per second across 128 input channels. So it is possible to really handle really enormous data volumes with SNSPDs. And this is just showing what this ground terminal infrastructure looks like when you put it in the field somewhere other than a lab. This is the Palomar 5-meter telescope, which is a really, really fun telescope to work at here in Southern California. the light comes in from the top of the telescope, comes down here and gets coupled into our cryostat here with our 64 SMA cables going to our readout electronics. And this is sort of an example of what you can do if you have this kind of setup. You can also do imaging arrays, which I think really open a lot of very interesting possibilities for quantum optics and quantum imaging. This is some work that we did with NIST a few years ago now, where we had a 32 by 32 array of SNSPDs that were arranged in rows and columns. So if you get a correlated pair of clicks on the rows and the columns, you can tell which one fired. And we used that to do time-resolved imaging. We had extraordinarily high pixel yield. This device was fabricated at NIST, I should say. And then we put it in that test bed that we had at JPL with the 64 readout lines and the free space optical access. And we could steer a laser beam around and do time-resolved imaging on all all 1024 pixels. Almost. I think there's 7 or 8 dead ones. But in recent years, we've taken this up even further. So we've been working on a better multiplexing scheme for time-resolved for time multiplexing, time domain multiplexing, which is called a thermally coupled imager. We use a superconducting readout bus here, and then we have multiple nanowires arranged on the readout bus. The way this works, when the photon comes in, remember the SNSPD acts like a switch that just quickly opens and shunts the current. The current flows not through an amplifier, but through a heater. And that heater is physically located on top of another superconducting bus, which then quickly goes normal and then quickly recovers. If you look at the time of flight of toward the two ends of the bus, you can actually tell from the relative arrival time on the left-hand side and the right-hand side which pixel fired. And with this, you can read out an almost arbitrarily large number of SNSPDs. Here, there were rows and columns of SNSPDs, but then the rows had one of these we call thermally coupled imager readout buses, and the columns had another. And with this device was fabricated at NIST, but they had a 2D array which had 500 rows and 800 columns. So this is actually a really stunning advance that actually takes SNSPDs, as I said before, for the first time into the kind of territory that semiconductor devices can have. This actually was recently accepted into Nature. There's a paper which should be available, I believe, October 26th. And this sort of shows how this works, that you can kind of use this time multiplexing to see individually all of the different pixels clearly resolved from another. So this is like an XY plot of this row readout bus and this column readout bus. And this is sort of showing it with a mask imaging through for the NIST logo. And then this is kind of showing you how this works, that the jitter of each detector is much smaller than the separation in time between the two detectors. So you can cleanly resolve which pixel fired if you sort of zoom in here, and you can read out this really large array of SNSPDs. The overall count rate across the array is not huge. It's like 100,000 counts per second across this whole array, because you have to wait for this bus to recover. But for certain applications, it's still really interesting, especially super low flux applications like space-based astronomy. And then switching gears a tiny bit, another thing to talk about, as I mentioned, we have these very, very high count rate arrays, which we developed here at JPL with quantum communication specifically in mind. So this is, we call this detector the Peacock detector for obvious reasons. It's a fiber-coupled array of nanowires. And then the bond pads kind of come out here are the little sort of feathers on the Peacock. So you plug a fiber in just like a conventional SNSPD, fiber-coupled SNSPD, but instead of one nanowire, which meanders back and forth, that mode from a single mode fiber is spread out over 32 individual SNSPD readout, SNSPD sensors. And so the ones in the middle get more light, of course, and the ones at the edge get less. But we're able to together scoop up about 98% of the mode volume here. And so this detector can count at 1.5 gigacounts per second, and it maintains, as I mentioned, 100 picosecond timing resolution. So this is sort of what happens when the device starts to go into saturation. So any one wire may saturate at some tens of megacounts per second, but then 32 of them saturates above a gigacount per second. And so if you can operate in a condition of some compression, you can actually count as high as a gigacount per second. And we also, as I mentioned, our colleague Thomas Lehner, he's cooked up this very fancy 6 gigacount per second 128 channel time tagger that we can use for this. Now, the jitter of the detector, if you put light in at a low count rate, is really low, as you normally expect. So it's about 17 picoseconds, full width half max, and it's about 45 picoseconds full width at 1%. But what you really care about is what happens to the jitter when you actually are sending photons at a gigacount per second. That's where things typically fall apart if you have personal experience in the lab with these things. And so it turns out one of the problems that we have is that when these pulses are coming really fast on top of each other, one right after the next, the detector may not be fully recovered at the point that a new pulse comes. So you might get a short pulse compared to a normal full-size pulse because the current hasn't fully recovered all the way up. That if you were to just cut a trigger level, which is a certain fixed voltage, then you will be actually triggering on the wrong part of your pulse, and your pulse will kind of walk out from underneath. This is a phenomenon that's been known with detectors since the 1960s, of course, and there are different techniques like constant fraction discriminators and things like that you can use. But we thought it would be helpful to apply a correction scheme that works digitally. So what we did is we implemented a scheme where we measure the sort of inter-arrival time between pulses. And then we can even measure a second order or third order inter-arrival time to like the second pulse or the third pulse back. And when you do that, it allows, you can make a lookup table. So we took a mode lock laser with a fast rep rate, and we basically scanned this delay, and we figured out deterministically what the delay correction needs to be to make up for this fact. Because at the end of the day, this pulse shape thing is completely deterministic. That's not a stochastic process, right? And so you can you can mostly back it out if you just apply this correction factor. So we apply this calibration with a fast mode lock laser, and then we apply this correction, and you see that we can really improve the timing jitter at high count rates. And so this sort of ugly green curve is what you get with one wire, which is counting at 50 megacounts per second. So if you had, that's really, really fast. This is sort of what the center wire would be approaching at a gigacount per second. What the most strongly compressed wire would be at a gigacount per second. And we see there that the if you don't apply any correction factor, you get this very ugly yellow curve where you get some well over 100 picoseconds of timing jitter. But then when you apply these corrections, it goes down to 38 picoseconds, full width half max, and the full width over 1%, falls by almost a factor of 2 here, compared to, and that's often what you care about in a quantum comm application. So applying these correction factors turns out to be really, really critical in order to actually achieve low timing jitter at the same time that you're counting at really high count rates. Let's see. I don't know if you want to leave time for questions. I can just quickly skip through this. We also have single pixel detectors with impedance matching tapers that have low jitter. We can get, if we apply put them in the same kind of cryostat with the same free space coupled filters, we can get dark count rates at the same time that we get high efficiency. So This is showing a free space coupled SNSPD, which you might, turns out you can actually get very low dark counts with free space coupling. This is a less than 0.1 counts per second of background counts while maintaining 72% system detection efficiency. If you look at this 16 microamp point here. And so that's a big improvement over just shoving a fiber in front of the detector. So you lose maybe 10% of efficiency going through all of these filters, but you gain about 2 orders of magnitude in dark counts. So actually free space coupling, perhaps counterintuitively, can be just as good, if not better, than fiber coupling when it comes to low dark counts. And these detectors, because they have these impedance matching tapers, which more properly transform the voltage, they also have built-in photon number resolution, which is a kind of a nice feature. So if you have 2 hotspots that hit your detector at 2 different places, the actual amount of the nanowire, which is made normal, is quite small, is maybe 100 by 100 nanometers, something like that, is 1 square of metal, basically. So that it's almost never happens that 2 photons are absorbed right at the same hotspot. And so generally 2 photons, even if they arrive at the same time, will give you 2 independent hotspots. So then your resistance jumps to not 1 kilo ohm, but 2 kilo ohms now, right? And then you see a higher voltage at the end. Of course, you don't see twice the voltage, but with these impedance matching taper, you can still see something. And so with this, you can set 2 thresholds. So this is showing different photon number events. So the blue is single photon events. The red are 2 photon events and 3 or more here. I always regret not putting this on a log plot here, but this goes down to about 30 dB here at the bottom. Okay, so in conclusion, SNSPDs are extremely high performing detectors for time resolved single photon counting. I didn't talk about it in this talk, but I'm happy to talk more if anyone's curious. They work from the ultraviolet to the far infrared, which enables lots of super interesting new kinds of science. As I mentioned, we can now make big SNSPD arrays for time resolved imaging, even approaching megapixel formats now. And then these high rate low jitter SNSPDs that I showed you, they can enable this quantum comm on a 10 gigahertz clock. I would say in our community worldwide, we have a very vibrant, active community where we're always coming up with entertaining new tricks. So thank you very much for your attention and interest. And if you want to know any more about this technology, please feel free to send me an email at mattshaw@jpl.nasa.gov.
Okay, Dr. Shaw, it's definitely a very amazing results. I still remember, like in my PhD, we were always daydreaming of doing some fancy quantum experiments, but unfortunately, we have never had a chance to get those fancy detectors as what you have demonstrated. So we have some questions from the audience. So the first one is that, do you need to do an individual calibration for each detector in that array? I mean, for the time calibration.
Oh, for the for this time walk correction?
Yes.
Yeah. So well, we do the calibration of all the basically we do it all at once. So it's the array itself is basically illuminated with one mode from the single mode fiber. So the light is all in one common spatial mode. And then we send in, so it's hitting the detector, all at the same time. So we send in a relatively bright pulse with a, we send in pulses with a mode lock laser with a fast rep rate. So this had a 2 nanosecond repetition time, 2 nanoseconds between pulses. And then we can use that to sort of sweep through and calibrate, what the sort of offset is, here. So basically with 2 nanosecond accuracy, you can kind of go through and figure out for every given delay, how much of an offset do you need to apply to pull out this effect of the temporal walk based on the pulse shape. So you get that basically for all 32 detectors at once when you do that experiment, because you're illuminating the whole detector and we have a time tagger that gets all that. We plug it into a 32 channel time tagger, so we get all of that together at once. I should say we're actually building a system now. It's not been built yet, but it actually has 4 of these 32 channel arrays in one detector system. So it's a 128 channel cryostat with 120 channel time tagger. And so we will actually have 4 of these detectors in there, so we can do Bell state measurements on a 10 gigahertz clock or other things. So if anyone is interested in using a setup like that, you're welcome to get in touch. Did that answer the question?
Yeah, I think we have a follow-up question regarding this. So
Okay.
Paul is asking, do you need to change the wrap rate to sweep through the relative delay of your detectors of nanowires?
No, you don't have to change the rep rate. You just need you want a rep rate that's fast enough so that you can kind of sample what the shape of these pulses look like. So you remember, this is kind of tens of nanoseconds in this shape, right? So you want to kind of go from 0 to whatever, some hundreds of some 100 nanoseconds or something like that in your lookup table, so that you can so you don't need to change the rep rate. You need a rep rate which is fast enough that you can get a lot of samples, but you don't want a rep rate that's so fast that it becomes hard to tell what's going on. And so 500 megahertz was kind of a sweet spot. So we used a Prytel laser that had a variable rep rate, but we don't actually have to vary the rep rate to do the calibration. You just need to take one set of data with one rep rate.
Okay, thank you, Dr. Chow. So now we will move to our next speaker. Our third speaker is Dr. Gala Moody from UC Santa Barbara. So Professor Moody wrapped up his PhD research at the University of Colorado Boulder in 2013. At Santa Barbara, Professor Moody's current research includes the development of novel design, fabrication, and testing approaches for integrated photonic devices and quantum materials. Now it's your turn, Professor Moody.
Great, thank you for the introduction. Can you hear me okay?
Yes, it's perfect.
Great, wonderful. So today I'll be presenting some of my group's work on nonlinear integrated photonics, and a lot of what we focus on is quantum light source development. And this spans a few different materials, a few different areas. I'll focus on nonlinear materials and nonlinear photonics for entanglement generation and entanglement distribution. But before I dive into some of our research, I'd like to kind of give an overview of where the field is at and kind of how we got to this position so far. So the field of integrated quantum photonics is pretty young, actually. It began probably about 15 years ago, starting in 2008, with some pretty simple experiments. So for example, just 2 photon interference on an integrated photonic chip. And in the past decade or so, we've seen a lot of advancements using integrated photonics to do much more complicated things. This can include silicon photonic nonlinear quantum light sources, as well as integrated photonic circuits, advances in quantum emitters, like we heard from Kai Mei, with integrated photonics with those to achieve Purcell enhancement, other kinds of quantum emitters as well, a lot of effort worldwide with quantum dots and integrated photonics. And then, in the past few years, even, more advances in different areas like 4-photon graph state generation, boson sampling with quantum dots, expanding to more photons and more qubits. For example, some nice work out of MIT with 128 single photon emitters in diamond integrated with integrated photonics. So this is a really active research area in integration and scaling. And I think a lot of that is leveraging the silicon photonics ecosystem, right? So this is a chart from Global Foundries presented at FIOLS in 2020. What they're showing here is the loss, the waveguide propagation loss for different kinds of sort of waveguide geometries. And for this particular silicon foundry photonics, these are designed for co-packaging with microelectronics and photonics. And so you can see, depending on the type of design, one can achieve pretty low waveguide propagation loss, below 0.5 dB per centimeter, for designs of photonic designs that are compatible with microelectronic integration. So this allows one to start thinking about scaling up the integrated photonic technologies with the microelectronics co-integrated, which I think is going to be pretty critical when thinking about scaling. And so these kinds of advances have enabled some very nice progress in the number of integrated components on a single chip. So for example, I'm plotting here the number of integrated components on a single chip versus the year for the past decade or so for silicon on insulator made in a foundry process. And so you can see a little over a decade ago, we just had a few components on chip, whereas now different groups using silicon foundries can put thousands of components onto a single chip to do some pretty complex quantum state engineering and sort of small scale quantum information processing. So an example of that from 2023, this past year, published in Nature Photonics from a collaboration with some of the researchers at PsiQuantum in Bristol and PKU, is something that looks like this. So here is a 200 millimeter silicon on insulator wafer fabricated in a silicon foundry. And then if you start zooming in and keep zooming in further and further, here's the chip that they've fabricated, that they've studied. And it looks something like this, where you have lots of interferometers, lots of beam splitters, lots of waveguide crossers, lots of nonlinear elements, lots of pair sources to do something like generate a graph state. And so in this particular example, they were generating up to 4 photon 3-dimensional qubits using spatial path encoding on this integrated photonic chip. And so in addition to the chip, this requires a lot of auxiliary components like pulse lasers, amplifiers, single photon detectors like we've heard about in the previous presentation. And they can do something like achieve like 20 millihertz 4 photon count rates. Something like that is kind of around where state of the art is. So I think this does open up the question, though, in terms of what is the right path forward for trying to make useful sort of scalable quantum systems. How do we get, maybe to phrase this a little bit differently, is how do we go from a few qubits to something that is more useful quantum system, whether that's for communication and networking or for quantum computing. There's a really nice sort of analog to microelectronics and digital electronics that we experienced decades ago, where you went from vacuum tubes to digital logic and VLSI. We're experiencing similar growth pains in quantum systems in both communications and networking and computing. And I think the key question is, how do we go from something like a quantum advantage for very specialized tasks that maybe aren't so useful yet to something like a useful quantum network or a useful quantum computer? And that's an open question on how we might do that. And my viewpoint on this, and I think maybe many others probably share the same viewpoint, is that we have to think about sort of networked quantum systems. Right, you're not going to fit everything onto a individual chip or a single wafer. You have to start networking chips and thinking about this in a very modular way. And that naturally lends itself very well to quantum networking, where you want to network different devices. And we heard this from Kai-Mei earlier as well, where you may have nodes that have sort of spin qubits as memories, and then you need to network those together with entanglement, either intermediary nodes of quantum light sources or intermediate nodes of Bell state measurements, for example. And so developing large scale quantum networks, these are the same kinds of problems that one thinks about. And I think with quantum computing, they're the same kinds of challenges as well. You're going to have something like a warehouse of server racks of different quantum technologies. These could be detectors, sources, modulators, switches, things like that, in order to start thinking about how to make this larger scale useful quantum system. And so if we think about what are the different technologies that we need to develop in order to be able to do this, here's kind of just a laundry list of things that I can think of, different enabling components and devices that one would need. And this includes laser systems, quantum light sources, memories, interferometers, single photon detectors, modulators, pulse shapers, and so forth. So we've heard a little bit about these different aspects throughout the day today already. For each of these, we need to have low loss. So this could be low waveguide propagation loss, also low insertion loss. We don't want to lose photons. We can't amplify our quantum states in the normal way you think about it with classical photonics. So we need everything to be very low loss. We need to get the light off chip. We need to get the light through components and not lose that light. Typically, we need wide bandgap materials to do this, so that way we don't absorb light. So silicon is okay up to a point, up to a certain count rate, and then it starts saturating because you start absorbing photons. And then especially for active components like modulators or lasers or nonlinear quantum light sources, we want to use materials that have really high nonlinearities. And so what I'm going to focus on for the rest of this talk is the research that my group does on generating quantum states of light using nonlinear optics. And so this could be Chi2 sources or Chi3 sources, for example. And I'll give some details on the specific ones that we focused on initially. These are the kinds of sources that have been focused on in industry primarily, mainly because they're readily available, and two, because they're sort of state of the art with what we have right now. And so there's two different approaches that one could take to use nonlinear photonics to generate quantum states of light. And they're adopted by different companies for different purposes, for example. And so one is the continuous variable approach. This is basically generating squeeze states of light using nonlinear photonics. This can produce entanglement into two-mode or single-mode squeeze states. And one could leverage this for computing by basically taking arrays of squeeze light sources and sending them through interferometers with specialized detectors, for example. The other approach is discrete variable integrated photonics. And so this is kind of similar to nonlinear frequency conversion, but you're annihilating pump photons to create new photons that exhibit some level of entanglement. And I'll talk a little bit about details of how we do that with our integrated devices. In either case, if you're generating quantum states of light using nonlinear photonics, then you want a really highly nonlinear material. You want as high of a Chi2 or a Chi3 nonlinear optical response as possible, because that makes your conversion as efficient as possible. And then you want to do that in a material platform where it has very low waveguide propagation loss. So that way you're not losing the light that you're trying to generate. So I'm showing here just a number of different material platforms that have been developed for quantum applications. This is not an exhaustive list. So there are a few others as well that I didn't get to update this table with. And then I'm showing this as a function of the different properties of these materials, so the Chi2 response, the Chi3, the refractive index, the band gap, and the scalability, which I'm kind of loosely defining here in terms of how large of a wafer has someone made with these materials before. Maybe not necessarily for quantum applications, but just fabricating these materials. And I think what I'd really like to point out is the optical nonlinearities here, and especially for the 3-5 materials, which is a lot of what my group focuses on. If you look at the Chi2 or the Chi3 optical nonlinearities, these materials have some of the highest optical nonlinearities. And so just from a materials perspective, they're very good for quantum light generation using nonlinear optics or nonlinear photonics because of these high nonlinearities. And so that's not the only consideration. One needs to also think about the band gap, for example, which the band gap for these is wide enough for telecom photons. These can work very well at 1550 because you're not going to absorb any of that light, especially with 2-photon absorption. They're maybe not as good for if you're trying to generate quantum states in the visible, because then the band gap is smaller than, for example, lithium niobate. So there are trade-offs to consider depending on the specific applications. But if you're thinking about 1550 or 1310 telecom photons, then from a materials perspective, these are a very good choice. And so a lot of the research in my group, in collaboration with a few others, including John Bowers here at UCSB, has been focused on developing this platform to make low loss waveguides and different components using the 3-5 materials. And so we focused a lot on what we call compound semiconductor on insulators. This compound semiconductor can be aluminum gallium arsenide or indium phosphide. Those are the two materials we specifically focus on mostly. And I'm showing here a picture of 100 millimeters of 4-inch diameter wafer where we have bonded an indium gallium phosphide thin film and removed the substrate. So you can see sort of a nice uniform thin film across this 4-inch wafer. And then what we'll do is we'll put this into our clean room at UCSB, and we'll do all the fabrication of our integrated photonic structures here on campus. And we'll end up with something that maybe looks like this, where we have multiple copies of the specific design of components and devices that we're trying to fabricate. And then at the end of that, what we'll do is we'll dice up this wafer into chips. So we have these very nice chips here that have different components on these different chips. For example, one could have modulators, one could have quantum light sources, more complex circuits to do certain things that I'll discuss towards the end of this talk. Okay, so a couple of years ago, one of the first things that we studied and demonstrated was somewhat simple now. It's just a micro-ring resonator coupled to a waveguide. And so here's the micro-ring resonator. You can see this is the AlGaAs material. And then here's the waveguide that couples to the resonator. And then everything else surrounding it is silicon dioxide cladding. So this is aluminum gallium arsenide fully clad by oxide material. And then what we do is we couple light into one of these waveguides. It'll couple in and it'll start circulating around the resonator. And then we'll couple light out of the waveguide. So any light that comes out will couple on the other side of the chip. And we'll use fiber-based coupling and then have other components and experiments on the tabletop to do the analysis and measurements of the quantum states. And so in these first experiments, we were generating entangled photon pairs, and we were using spontaneous 4-wave mixing to do this. This is a Chi3 optical process. So the idea is pretty simple. So with any material, it's a Chi3 material. You can couple light into the waveguide. It'll couple into the microring resonator. And as the pump light from the laser circulates around the resonator, what will happen is probabilistically, 2 pump photons will get annihilated to create 2 new photons through conservation of energy, conservation of momentum. And these 2 new photons, traditionally called signal and idler photons, will be entangled in time and energy. And so we need to know where to place our pump in terms of wavelength. So what we can do, showing on the bottom here, is measure the transmission spectrum of this resonator. So we send laser light onto this chip and measure the power at the output. And then we sweep the wavelength of our laser. And every time our laser is resonant with one of these modes, we'll see a dip in the transmission. And these dips correspond to the cavity modes. And then we can do linear characterization of our device. We can figure out, is this a good device with high quality factors? And quality factors of the cavity that are high mean that it has low propagation loss. And so we can achieve quality factors on the order of a few million, which corresponds to about 0.2 dB per centimeter of propagation loss. And then what we can do is we can park our pump laser on one of these resonances and then take the light that comes out and do some off-chip fiber-based filtering with commercial off-the-shelf components to do demultiplexing, filtering, go to single photon detectors to do measurements of the photons. And so in this particular experiment, we would take, for example, idler photons here and the corresponding signal photons at slightly lower energy or higher wavelength, and then do analysis on those photons. And something important to point out is that the entangled pair generation rate for this kind of process scales as the nonlinearity squared. So this is also, it's the nonlinearity normalized to the mode area, as the quality factor cubed, and then as 1 over the radius squared. So what this means is you want really small resonators, small mode volume. You want really highly nonlinear material, and you want really low loss material. So you need to try to optimize all of these simultaneously in order to get the best pair generation rate. So it's not just about optimizing the quality factor, because one can achieve, for example, close to like 1 billion Q quality factors in resonators, but those tend to have very, very large volume and very large area. And so then you kind of lose out in that sense. And so it's really optimizing all 3 of these at the same time in order to try to enhance the pair generation rate. Okay, so we've done that in our material platform. And on the top here, I'm showing, for example, the different modes that are generated from this kind of ring. So if you pump, for example, at this wavelength, then you can generate photon pairs at each set of modes. So for example, the modes highlighted by stars, or the modes highlighted by the triangles, or any of these other sets of modes that exist in this resonator, where we've adjusted the resonator geometry to try to achieve quasi-phase matching, very low dispersion, and that allows us to create modes across something like 200 nanometers of bandwidth. And then if you isolate, for example, just one of these sets of modes, and you just measure the count rates on your detectors, we can saturate our single photon detectors, for example, with pretty low on-chip power, hundreds of microwatts of on-chip power. And then one can also look at how many coincidences do we actually measure per second in the lab, and we can get something like upwards of 40,000 pairs per second that we're measuring from the chip. And this is a little bit lower than maybe what you would expect based on chip, and that's just because of loss in like our off-chip fibers and filters and things like that. Okay, so to kind of summarize those results and to put that into a little bit of context, I'm plotting here the efficiency, which is basically how many pairs per second are you generating normalized to the pump power. And then on this axis is basically these different, it's the scaling factor. It's the nonlinearity squared, quality factor cubed, and 1 over volume squared. So you can see the efficiency of the 3,5 materials is some of the highest compared to, for example, silicon or silicon nitride. And that's to be expected because you can make pretty low loss structures with really high optical nonlinearity. Okay, so as a proof of principle demonstration of what we're trying to do more recently is take these photons and actually send them through a campus fiber optic network to understand how to distribute entanglement across fiber optics in a real world setting. So we've installed a fiber loop, for example, under one of the busiest roads on campus where we can send photons back and forth across this loop. And as an example, do something like a time bin quantum key distribution experiment using entangled photons. This is a little bit different than using pulsed lasers and decoy states. This is actually based on entanglement distribution. And we can achieve something like upwards of almost 10 kilobits per second. And then, of course, we start to see loss as we go through more and more fiber down below sort of a kilobit per second key rates with less than 5% error for entanglement distribution. Okay, so I'd also want to just highlight there is progress in a lot of other material platforms. So there's lots of work in different materials, primarily silicon nitride, and then there's also some work in aluminum nitride, also coming out of France and 3,5 materials as well. And also out of Illinois, there's some nice work with indium gallium phosphide and Chi2 photonics. Okay, so here's a summary of maybe all those results. I'm going to skip that for the sake of time to make sure I have some time for questions. But if anyone wants to take a quick screen grab, you can kind of see here's at least a somewhat up-to-date table of the different materials that have been developed and some of the progress for the parameters for these quantum light sources for integrated photonics. Okay, so beyond sources, we're also interested in looking not just at bipartite entanglement, so generating two photons that show some level of entanglement, but going a little bit beyond that and starting to think about more complex quantum state engineering. And in order to do that, we need to develop other on-chip components as well beyond just microring resonators and waveguides. So last year we spent a lot of time in developing these components, and these include tunable Mach center interferometers to make programmable circuits, to use these as demultiplexers and filters, working on optimizing the rings for pair extraction, for example, making very low loss waveguide crossers, for example, so we can make the waveguides cross on our circuits. And so this table here is plotting the performance of these different components that we've developed for our quantum photonic platform compared to silicon and silicon nitride that are designed also for similar applications. These are maybe not necessarily the best that one could achieve in these two platforms, but what one has achieved for those platforms for quantum photonics. And you can see that they're pretty comparable across the different platforms in terms of insertion loss, filter performance, and things like that. So we have a pretty decent handle on how to make these components on our platform. We don't envision scaling this up and making thousands of components on chip, but this does allow us to do some more interesting things using our nonlinear platform. And one of these, for example, the next thing you think about doing is instead of just one micro ring, let's use 2 micro rings. And so what this chip is doing, for example, is taking the laser light that comes in on chip. We have a tunable Mach center interferometer. This allows us to control the amount of laser power going into these 2 waveguides. So we just use that to basically split the laser. And then the laser is going to pump both of these microring resonators, and these have some probability to each generate a photon pair. Then we go through another tunable interferometer to filter out the laser light and split off the photons from the signal photon on one path and the idler photon in another path. Then we go through a final interferometer to interfere the photons on chips. This is a Honglu-Mandel experiment on chip. And then we can measure the photons coming off to characterize the light. And so what this ends up allowing us to do is we can use this to basically make 2 of the 4 maximally entangled Bell states where we can swap between which of the 2 we want to make depending on the phase of this interferometer, for example. And we have pretty decent performance, indistinguishability of at least 72%. We're working on optimizing that in terms of how we're pumping our sources with pretty good 4-fold rates. I think we're upwards of about 100 millihertz now. So it's about a factor of 5 higher than silicon, for example. Okay, other things that we're investigating are looking at squeezing. And so, for example, with a single microring resonator, depending on how we couple that to our waveguide, we can extract more of the light coming out of that microring resonator. We can pump it a little bit harder, and we can use this to generate quite a bit of on-chip squeezing for not much on-chip power requirements. So one could think about doing some interesting quantum state engineering this way, very similar to the previous slide that I showed, but using squeeze states instead. Basically split the pump co-propagates in opposite directions, counter-propagating directions of our microring resonator. We generate squeeze modes coming out. We can do pump filtering And then we can do demultiplexing to separate the different frequency modes. Then we can do interference and then generate something like a 4-mode cluster state of continuous variable squeeze states. Okay, so lastly, one of the things that we're also looking at is looking at arrays of micro rings. And so, for example, this is a chip. It's a little bit of a blurry image, but there's 20 nominally identical micro ring resonators on a single bus waveguide, and each one of them are tunable. So each one of these can produce this frequency comb of entangled pairs that I showed previously. And so then if one just looks at the transmission spectrum of sending laser light into this waveguide and you look at the transmission spectrum, so the power coming out, you see something that looks like this. You see all these different sets of modes. And basically each within each one of these groupings are upwards of 20 different frequency bins. And each of these corresponds to a different microring resonator. And so one can use this, for example, to make frequency bin encoding for QDITs. So you get some Hilbert space scaling as d to the n, where d is the number of frequency bins. So showing in this plot, this is something like upwards of 20 different frequency bins within 100 nanometers. And then n is the number of microring resonators that are tuned in close groupings here. And so that's also up to about 20. So one could, in principle, think about doing something like 20 to the 20. Now in practice, that's going to probably be impossible to measure. So we'll have to think about how to carefully do those measurements to understand these kinds of devices. And this is going to be done in collaboration with Pavia. So this is Marco and Daniela's group at Pavia. And so one reason to do this is this leverages the high brightness. We don't really have this trade-off where if you want to do anything like with frequency bin information processing, you tend to need to make the frequency bins very close to each other so you can get modulators to interfere them. So you need to make a very large ring to do that, to get those modes tightly spaced, but then your pair generation rate is very low. In this case, we don't have that trade-off because we can use very small rings and then basically just interleave all of those frequency combs so you get very tight spacing with really high rates. Okay, so I'm starting to run out of time, so I kind of wanted just to summarize here real quick in terms of some of the things that we're thinking about and where we want to go going forward. We are thinking about heterogeneous integration and primarily 3.5 on silicon nitride to leverage a lot of what's being done on low loss silicon nitride, and then just adding quantum light sources based on 3.5 materials onto the low loss nitride platforms. Also, I think there's some challenges, but also an interesting route to go towards is Chi2 versus Chi3. So doing things like parametric down conversion instead of 4-wave mixing, the efficiencies should be quite a bit higher than what we've already demonstrated. And then I would love to see something like much better chip to fiber coupling. So right now we typically have something like 2 to 3 dB of loss of just getting light off chip. And our lives would be a lot easier if we could beat that down to something like 0.1 dB, which I know is very challenging, but that's kind of a big goal that we want to try to achieve. And one motivation on why we want to go to silicon nitride for a lot of the circuitry. And then there's other things one could envision doing with systems on chip. So thinking about lasers and sources, or adding frequency converters or microelectronics to start thinking about more packaged quantum light sources that one could use. Okay, so with that said, I'll just summarize here. I'll leave up my email in case anyone has questions. I'm happy to answer questions. I do want to acknowledge collaborators, but also the students that have really driven this research, including Trevor, Josh, Nick, and Lily. They've been the ones who've been designing, fabbing, and testing all of these different devices. And they're a super team. And some of them will be graduating pretty soon. So if anyone is interested, feel free to reach out to me and happy to chat. All right, thanks. Happy to answer questions. Thanks.
Thanks, Dr. Modi. I think you already answered a question in the chat that you already talked about the indistinguishability of the single photon source and how you optimize it. And so I do think I have a simple question for you. You have mentioned that, for example, in your case, you are using aluminum gallium arsenide as a single photon source. You also mentioned that, okay, for the photonic integrated circuits, you need other integrate other platforms together. So you have provided a platform of doing simulation and design for the aluminum gallium arsenide. But what about the entire design of the entire peak?
Yeah, I think it depends on the application in terms of what you might need. If you want to do something somewhat smaller scale where, if you have 2 rings and you just want to do like on-chip interference, you don't really need to go to heterogeneous integration and integrate with other material platforms, because that introduces its own challenges as well in terms of getting light between different photonic layers. But if you want to do something larger, where maybe you have large arrays of sources and lots of interferometers, then you probably will benefit from going to something like taking a foundry wafer, like silicon nitride made out of foundry, and then doing some post processing step where then you add on your quantum light sources onto the front end. Or even better, if we could really get much better chip to fiber coupling, then you wouldn't even need to think about heterogeneous integration. You just have your nonlinear quantum light source chip, you take light off and go on to some other chip that has all of that programmability that you need. And so it really depends, I think, on the specific application and what one has in mind in terms of how many components do you need on chip, what are the functions do you need on chip. That'll dictate sort of what is maybe the best long-term approach to take.
Oh, understood. Thanks, Dr. Moody.
Yeah.
So we are a little bit run out of time. So if anyone has questions, please just send an email to Dr. Moody, and you can get, I believe you can definitely get good answers.
Great. Thanks, everybody.
Yep. Okay. So here comes our last speaker of the day. So Professor Paul Kwiat comes from Urbana-Champaign. He started his stylish biophysics career in UC Berkeley, and after that, he's spending some years in Los Alamos doing some excellent physics. Then he collapsed his research group at University of Illinois Urbana-Champaign in 2001. So his current research surpasses multiple quantum physics, including quantum teleportation, quantum communication. Now, let's invite Dr. Kwiat to review his measurement results for today's talk.
Thanks very much. Can people hear me all right? Hello, can you hear me?
Yes, I think it's just showing like sharing in progress.
Yeah, I'm getting there. Okay, how's that?
Perfect.
Great. So thanks very much for the invitation to participate in this. It's been kind of interesting, really interesting watching the other technology talks and some of the ones in the morning as well that I was able to see. I have a habit of always changing my titles just a little bit. So I'll talk about some problems that we need to solve and some partial solutions for those problems, specifically in the areas of sources and memories, and also trying to move toward hybrid networking, where we're not just in fibers, but also in free space. Just to acknowledge the team that's been working on this, I'll be presenting some research from these various students that are in my group, but we're always on the lookout for fun collaborators and new postdocs and new students. So if you're interested in stylish dressing, give me a ring, so to speak. Okay, so these are the topics I'd like to discuss. This is sort of it seemed to me like it's almost like a Jeopardy categories, four different categories on Jeopardy. But I'll start with talking about sources and multiplexing, say a little bit about quantum memories, and then moving toward free space, and then hopefully a little time for discussion at the end. Okay, so this is a list of a list of properties that one would want for a good single photon source. And it turns out they're more or less exactly the same things that one would want for a good entangled source. So one would like a source that's deterministic, which means that when you ask for a photon, you get one, and it comes into a well-defined spatial temporal mode. You'd like it to be efficient, which means that if I'm trying to make single photons, with a high likelihood, I produce one photon, or with a low likelihood, I produce more than one photon. Or if I'm trying to make a pair with a high likelihood, I produce one entangled pair, and with low likelihood, more than one entangled pair. And I'd like the quality of the photons to be high. I want the photons to be indistinguishable from each other, and I kind of want them not to be entangled with some other photons in some other way that I don't like, because that will make it difficult to do multi-photon experiments. So in terms of single photons, of course, we could use attenuated coherent light sources, just like a attenuated laser pulse. And that's okay, actually, for some things, like for quantum key distribution. But for most everything else, quantum networking is not going to be sufficient, because we have Photonian statistics for the number of photons that are being produced. If you have a single emitter, like a single nitrogen vacancy center, a single defect, a single quantum dot, those are great because they can have very good so-called G2. G2 is the, let's say loosely, the likelihood that you produce 2 photons when you're only trying to produce 1. Because there's only one emitter, if you can excite it just once, it's only going to give you 1 photon, so that's great. They can be almost deterministic. One difficulty is the photon tends to go off in all directions, so you need to use cavities to get it to go where you want. Oftentimes they need to be cryogenic, which is not such a good thing, and it can be quite challenging to get the different emitters to look identical, as Jaime talked about earlier. The other thing you can do is use a pair source, like Galen talked about, where you have 2 photons, and then if you detect 1 photon, you know that there's another one. And that's really quite good because they can have very good mode matching. They can run at room temperature. One downside of them is that they're probabilistic. So you don't know if you're going to make 1 pair. And that in and of itself might seem like it's the worst problem, but it turns out the worst problem for quantum networking is not that you don't always make 1 pair, it's that sometimes you make more than 1 pair. And that turns out to be very problematic, as I'll talk about. So here I'll talk about spontaneous parametric down conversion. This is the so-called Chi2 process that Galen talked about, where I have 1 high energy pump photon that splits into 2 daughter photons. But everything I'm about to say also applies for the other type, the Chi3 process, the spontaneous 4-wave mixing. So all the math is exactly the same. It just, whether or not you send in 1 pump photon or 2 is irrelevant for this. So the problem is that the photons that come out are have thermal statistics. So that means that if I look at the likelihood of producing, say, 1 pair as a function of the mean number of photons per pulse, first of all, you're always most likely to produce nothing, because it's a thermal light source that is producing no pairs is always the most likely thing, and then 1 pair is next likely, and 2 pairs is likely after that. But you can show pretty easily that the distribution is kind of shown here, where mu is the mean number of photons per pulse, and that saturates, so that has a maximum value of 1. So let's say this, when mu is 1, that gives you the highest probability of producing exactly 1 pair, and that probability is 0.25. So that seems not too good, that the source only gives you a 0.25 probability of getting a single pair. Now, if you can use multiplexing, it turns out you can improve that. You can improve the success probability. So here shown, for example, are 4 separate sources. And if you could drive all of them and to kind of ignore the middle box, the temporal multiplexing box, but we can ignore this middle central box for the moment. But you drive all 4 of them and you detect 1 of the photons. So we're producing a pair and I'm detecting 1 of them, that's the red one here, and I can tell which source was successful. Well, then I can switch the output of that source into the same output mode. And so I'm able to map, say, 4 in this picture or 16 in some other picture, all these independent sources all into 1 mode. So that is basically going to multiply the success probability by a factor of 4 or by a factor of 16 or something like that. So that can be extremely effective for increasing the single photon probability. So what we've done in our lab was actually work with time multiplexing instead. So with a conventional heralded single photon source, we're pumping with a bunch of pump pulses, and 1 out of, in this case, let's say a couple out of 8. So roughly 1 out of 4 gives a pair, but you don't know when that pair is going to be created. So it could be anywhere. So there's a low probability of getting a photon pair in any given time bin. But if we can consider groups of those time bins all as sort of 1 event, then if you have enough of those time bins together, it becomes very likely that you'll get at least 1 time bin that has a pair in it. So how does that help you? That helps you if you're able to then map various of these time bins all into 1 final time bin. So that's kind of what's shown here. So I have a source, I'm driving it with a bunch of pump pulses, let's say up to 40 different pulses. I'm going to detect which of those pulses had a photon by catching this heralding photon. And then I'm going to store the other photon in the storage loop here. I'm going to store it until the 40th pump pulses come by, and then I'll release it. And so depending on when I get the heralding signal, that will tell me how long I need to store inside this buffer, this quantum buffer, but then I'll always release it at the same time. So in that way, I'm able to map a bunch of different time bins all onto 1 time bin, and that improves the efficiency quite markedly. So this is just showing, let's just focus on the blue curve, the mu is 0.18. So this is saying that there's an average of about 0.2 pairs per pulse. And if I go to more and more time slots, if I go all the way up to 40 time slots, it becomes almost certain that I will have had a pair sometime, I will have detected a pair, I will have produced a pair, I will have produced and detected one of the photons somewhere in those 40 bins. Now, the actual efficiency in terms of a single photon source is not that high because the storage loop itself has some loss, but nevertheless, we've been able to see up to about a 67% probability of producing a single photon at a well-defined time into a single mode fiber. And as far as I know, that is still the world record for that. And that's really shameful because our field of quantum optics, we've been working on single photon sources for a very long time. And you'd like to think that we'd now be at 90% or 95% like Matt Shaw and his detectors, which are awesome, but we're just not there. So we're currently at 67%. The photons themselves, this is for any experts that are out there, have a quite high purity, up to, at the moment, measured up to about 95% purity. That's sort of how well they'll interfere with each other, and we know how to get that higher. And the next thing that we're working on right now in my lab is to try and add in time bins, 2 different time bins, so we can have time bin entanglement that's being multiplexed as part of this source. Okay, let me just talk a minute about, well, actually, let me just say one more thing about this. So we're running at the moment at something like a megahertz. And so that means that basically 1,000,000 times a second, times 2/3, we're producing a single photon, or if we do this with pairs, then we're producing a pair. And that's to be compared with the thing you maybe just heard that Galen was talking about, where their sources are very, very bright in these waveguides, and that's amazingly awesome. But the insertion loss going into and out of them really is quite detrimental for these sorts of things. So this is just looking at the effect of loss. So everything that we're doing at the moment is with bulk optics and in free space. And I'm just showing here what is the effect of loss on this enhancement factor. And you see the single photon probability, say on the left here, drops really pretty drastically. If you have even only 10% loss in one loop of this storage system, you lose a lot of the benefit of being able to use this for multiplexing. Or shown here, if we're trying to think about enhancements factors of trying to get multiple photons at once, again, the benefits drop quickly as the transmission in the loop drops. Another issue is because we're in free space, we don't have to deal with dispersion, which is great. But if you do these things on chip, that is going to be another issue that's going to be a problem, because if you're having to go either 3 loops in the chip or 50 loops in the chip, those you're going to pick up different dispersion for those different round trips, and that is going to make the pulses distinguishable depending on how long they've been in the memory. And so that's another challenge to doing this on chip. I want to highlight that, just not to say that I want to necessarily do things in free space, but for the moment, that seems to be the only way I know to sort of circumvent those problems in an easy way. Okay, so we can ask, what are these things good for, and just analyze a little bit how helpful they might be. So what I have drawn here on the left is sort of the primordial aspect of a quantum repeater, which is that I have 2 entanglement sources, 2 EPR sources, and I want to link them together. And you do that by combining the 2 photons and making a Bell state measurement. That is basically just mixing them on a beam splitter. And as long as they arrive simultaneously and you get a particular pair of detectors in this measurement going click, then that will basically entangle the 2 outer photons, the one going to the far left and one going to the far right. So that's a way of stitching together and going over longer distances. And you could eventually imagine doing that, for example, with satellites, where you've got sources and satellites, and then you're going to try to combine them. Now, because things are arriving maybe at different times, you want to have some sort of quantum memories to be able to do synchronization in order for this to work. One difficulty is that if I'm doing this with sources, and sometimes those sources are not making 1 pair, but they're making 2 pairs. If I just kind of go to this one, and one of the channels is really lossy, well, you can be spoofed in this Bell state measurement by having 2 pairs from one source and no pairs from the other source. So this is just to say that those multiple pairs that I talked about are really problematic, which, as we'll see right now, is multiplexing can be helpful as a way of preventing that. So if you don't have multiplexing, you basically have to drive your sources very weakly so that you don't get double pairs from one crystal. And this is just plotting, if I had a scheme where I had these multiple down conversion sources or entangled pair sources, and I'm trying to do 2 entanglement swaps at these yellow squares here, how likely would I be to do that per attempt as a function of the separation, assuming I was going through standard optical fibers? And you see that the rates drop off really poorly, even if I'm, well, this is per attempt, but even if you're driving at, a gigahertz, then that means if you're going out to 100 kilometers, you're only going to get 1 successful event per second. So that's not great. If you can do multiplexing, times 4 multiplexing or even times 64 multiplexing, then you can really improve the efficiency by multiple orders of magnitude, basically because you can suppress this likelihood of getting 2 pairs by doing this multiplexing. So with this, for example, it's feasible with soon technology to be able to have swapping entanglement at rates of 1,000 a second over some sort of 100-mile link. I add in one more curve here, which is what would happen if instead you do this like with a really good quantum dot source that makes a pair of entangled photons, and assuming that you could couple them out with very high efficiency, which no one has quite done for a pair of photons yet, but assuming that that's coming in the next 5 years, that actually ends up being, that's a big win because they're just not making the multiple pairs. So quantum dots, the other types of centers that Kai Mei was talking about, those could all be beneficial over and above these other types of multiplex sources if you can get them working. Okay, I'm going to change gears and talk about quantum memories. So we often need to synchronize things in quantum communication. That was one goal. And you don't, in general, need to store for an arbitrary amount of time. You need to store for an arbitrary number of clock cycles. And so what we really want to be able to do is store for some number of clock cycles. And we've already heard about schemes using atomic systems. We actually are pursuing something that's in some sense simpler, which is just the fact that light takes a finite time to propagate a finite distance. And so if we can just delay it, you could think about using a fiber loop, but for reasons I'll come to later, that's a bad decision. But just having it go through free space, that can be beneficial, and just bounce off mirrors, and that can have very high bandwidth. You don't necessarily change the quantum state because these can be polarization insensitive. By changing the configuration, you can change the delay line. This can work for any set of wavelengths, just depending on what coatings you put on the mirrors. And that's where fibers don't work, because fibers kind of only work well for like telecom wavelength. And there's the possibility of storing multiple K vectors in spatial modes, which again would be difficult with optical fibers. So this is just a picture of one of our delay lines where we're having, this is basically a 1 microsecond delay in 2 mirrors that are separated by a meter. And we're just looking at a little bit of leakage. These are actually old coatings, so they're leaking more than normally what we would now have. And you get this beautiful pattern. We're bouncing back and forth about 400 times so that we can store for quite a long time. If you want to store for less than that, you could just have a single loop that has a polarization switch in it. That's what's shown here, where light comes in as horizontally polarized. And if I switch it to vertical using this Pockle cell, it will then just keep going around in the loop until I switch it again back to horizontal, and then it will leave the system. And we can do that with, let's say, 1% or a couple % loss. That's pretty good. Unfortunately, if you wanted to go, say, 537 times in the system, then nothing gets out. So that's not so good. But what we can do instead is we can actually combine sequentially different storage systems that have different amounts of delay depending on how long just the optical path is. And that optical storage can be quite good by using very high reflectivity mirrors. So, okay, so we've been able to store for 1 to 999 cycles here. with, in this case, a measured transmission of 35% when we're going for 537. Whereas if you just went through this one system, the first loop 537 times, not absolutely, you know, it would be 10 to the minus 10 or something like that would get out. Let me just say, you know, you get better mirrors and things work better, not surprisingly. So at the moment, we're able to store for about 10 microseconds with an efficiency of about 60%, which is very good. And we've also been able to show that we can store quantum states and preserve the fidelity of those quantum states really quite well, regardless of which of these memories we're going into. And so it seems to work quite well as a quantum memory. The big advantage is that it has extremely high bandwidth compared to any of these other atomic systems, which maybe have, you know, 100 megahertz or maybe a couple of gigahertz or something like that. This is higher by many orders of magnitude, and so that's really useful if you want to store a multiplex system. Like Galen was talking about, all of these photons that have nearby frequencies. If you do this with an atomic system, you just have to put them each into their own system, or you have to do frequency shifting, whereas this can certainly store all of them. Truth in advertising, though, if you want to store for a millisecond, this will never work. So that's a problem, and then we need to do something else where we need to put it sequentially on one of these other kind of systems, I guess. Okay, last topic, moving away from fiber-based systems to go up into the air. So, you know, current quantum networks, as you heard this morning, typically they're pretty small. They're not going over very long distances unless you have trusted nodes. You could put trusted, you know, you could go over long distances, but the problem that fiber has loss, and so the transmission drops exponentially with length. You know, typically for something like 200 kilometers, your transmission will only be 10 to the minus 5. If you want to go 1,000 kilometers, that doesn't drop to 10 to the minus 5 over 5. It drops to 10 to the minus 5 to the 5th power. So basically nothing gets through. If you can do quantum repeaters, then you can fight that, but we don't have any quantum repeaters yet. And there are applications like going over water or through space where fibers just aren't going to work. So doing things in free space has some benefit. And we envision an eventual quantum network that will have both fibers with quantum repeaters, but will also have various free space links through the air, through satellites, going to moving vehicles. So one of the things that we're looking at now is basically trying to do quantum communication with drones and with moving vehicles, and trying to see, you know, what we can accomplish in that space. One motivation for that is that if you're trying to send terrestrially, you know, through free space, there's turbulence. And let's just say that, without trying to explain this whole slide, if you go up, the effective turbulence goes down pretty quickly. And so even if you can go up only 50 meters, exchange some quantum signal, and then come back down, it turns out that makes your life better by, you know, a couple orders of magnitude, at least in principle. That then also enables you, if you've got a bunch of drones, for example, to do things in a reconfigurable way, so that we can reconfigure the network by moving things from one place to another. Also, if we wanted thinking about doing quantum sensing, being able to have movable sensors is clearly something that would be beneficial rather than having the sensors just fixed in one location. So this is just a photograph of two of our drones sitting in flight in the air, locking, sending quantum signals from one to the other. We have one of the drones has a transmitter, one has a receiver. At the moment, we're just doing so-called decoy state quantum cryptography. I guess I'll just say that. The main challenge with this whole system is just getting the things to lock onto each other optically. That turns out to be a big pain in the neck, I'll say. Who knows who it's online? Anyway, it's challenging. So we have the whole system is modular, so we can take the gimbals off of the drones and we can put them in the backs of vehicles, for example, and that enables us to do drone to vehicle or vehicle to vehicle communications. Yeah, so in terms of pointing and tracking, we have both a core system that points the gimbals at each other. That's for slower fluctuations based on cameras. And then there's fine steering using beacon lasers and fast steering mirrors that enable us to correct for much faster vibrations. So we've been able to now do air-to-air locking with drones separated by, let's say, 10 to 50 meters with something upwards of 60% transmission from one drone into the other drone. And when you turn off the locking mechanism, everything goes away. So the locking is definitely doing something very useful. And we've been able to use that then to do quantum communication, like quantum key distribution between drones in flight. We've also been able to do communication between a drone and a car. The drone is flying alongside the car, and also between two vehicles that are next to each other on the highway. Two vehicles that are kind of traveling next to each other at 70 miles an hour on the highway. So this is maybe the start of other types of applications of quantum networking to the transportation space. Okay, going up even further in free space, I had mentioned satellites, and so I just want to, for the very last thing, just talk a little bit about this other satellite project that we're working on, the SEEK project, Space Entanglement Annealing Quantum Experiment. This is a project that is funded and running under JPL at NASA with collaborators from University of Waterloo and National University of Singapore, and a source from ADVR. So the goals of this, there are sort of two main goals. One, we're not trying to communicate, we're not trying to send anything from space to Earth. That requires a much more expensive experiment than this is. We're just trying to create entanglement on the satellite, detect it, verify that it's all working with a new sort of source that hasn't been flown, and then also to try and investigate radiation damage on the detectors and ways of preventing that. So previous experiments that have flown entanglement sources have all used bulk optics, where we either have so-called Sagnac source or a sort of a beam displacer source shown here. And those often require alignment post-launch, which we don't want. And so what we're doing instead is basically a waveguide source. You could think about this as a one-shot version of what Galen was talking about, because we don't have resonators. We're just going once through a waveguide. We're producing photons, one is horizontal, one's vertical. And if you go off a beam splitter, and it happens to be the case that one photon goes each way, that gives you this nice polarization entangled source, which has really quite good parameters in terms of fidelity with an entangled state and being able to do violations of Bell's inequalities. So the whole thing sort of exploded looks like this. So we have a diode laser at 404 nanometers. That gives us pairs at 808 nanometers. This is the magic beam splitter that sort of creates the entanglement. We can control that and how we measure that using liquid crystals. And then we have detectors, avalanche photodiodes after polarizing beam splitters. So one issue is that the detectors will get radiation damage. That's certainly been seen before. So if you keep detectors up in space for about a year, they will have a dark count rate that will go up by tens of thousands of seconds, per detector over the course of the year. And if eventually your signals are only 100 a second, then 10,000 a second noise is a bad thing. It turns out that if you can heat the detectors for about an hour at 200 C, you can thermally anneal them, and that will fix that to some extent. But it's not that easy to do that in space. People don't really want to heat things at a high temperature in space because it's hard to do thermal management. It turns out if you also can just shine a 1 watt laser onto the detector for about a minute, it has apparently the same effect. So the last thing we would like to do with the SEEK project is to do annealing while the detectors are in space to extend the mission lifetime, and also to do a direct comparison of this laser and thermal annealing. So we're quite confident that when we put the detectors up, the dark counts will go up, and then we'll anneal and they'll come down, and then they'll go up again and we'll anneal and they'll come down again. What we don't know is, will they always come down to the same level, or are there going to be some damage that will be unannealable? And I think this will be the first experiment that's really been able to detect, certainly to test that in space. Anyway, we're excited. This is kind of what the thing looks like as we've been putting it together. And now this is sealed for the first time. The whole thing finally sealed up over the weekend. Everything is like all epoxy together. And I'm happy to announce that we took it for a vibration test today. We had to go off to Kentucky for a vibration test. This is where you basically shake the thing like it's in a dryer to simulate having a launch. And I'm very happy to say that it survived all 3 of the vibration tests. I was super, super worried because we're coupling into fibers, and most of you have floating optical tables. If you're experimentalists, you never want to think about actually like dropping the thing on the floor and keeping it aligned. So this was a for us a big milestone, and we're hopefully due to launch in spring to be put onto the space station. Okay, so future quantum network hopefully will be hybrid, but where will we end up? To go to a modern movie. Hopefully we'll go to many places, although it may take us a little while to get there. So this is just a summary of what I said. Multiplexing is certainly helpful. Quantum memories are working kind of okay, but there's certainly still work to be done. And hybrid networks are possible, but also a lot of work to be done on that. And happy to answer questions. And if you have them that I can't answer here, here's my email.
Thanks, Dr. Kwat. That's definitely fascinating news about your research. So we have a few questions flying around. The first one is about the multiplexing. So we can see that you mentioned that you can do both time multiplexing and spatial multiplexing to improve your performance of the source. But so time multiplexing makes sense, but makes sense to me. But for the spatial multiplexing, don't you need to do any like Mendel's induced coherence to make sure they're indistinguished with each other, since you are pumping each pumping each crystal separately?
Yeah, so this is a super nice thing about down conversion crystals, is that you buy 2 crystals from the same company and you pump them with the same pump laser. The photons will be indistinguishable with each other, and so it's going to be no problem. If the 2 photons from a given pair are entangled with each other, like let's say spectrally, and you don't want them to be, and that will screw up the spatial multiplexing, but that will also screw up the temporal multiplexing. So that screws up everything. So you have to just make sure that they're in a pure quantum state, sort of individually spectrally. But as long as that's true, that's the one huge benefit of the down conversion as a source, is that the photons from my sources and sources in John Ray Pan's lab, they'll interfere with each other just fine.
Okay, so you do not induce coherence to make sure they are overlapping perfectly in spatial modes.
As long as that they're overlapping perfectly in spatial mode. We're coupling them all into, say, single mode fibers, in which case then they're guaranteed to be in the same spatial mode.
Okay, makes sense. Thank you. I think the second question is about your memory. So we can say that memory has very broad bandwidth, but does this memory can support any heralded function, like if heralded is quantum memory?
Oh, the question is it heralded? So it is absolutely, it is absolutely not heralded. So you don't know when a photon went in, other than seeing at the end that one came out. That's 100% true. I will say that is also true of almost every other quantum memory. Even a lot of the matter ones are also not heralded. So they can store, but they don't know that they've successfully done that. The thing that the world really needs, let me put up, is the one box I didn't talk about. Where is it? Oh, it's back. One box right here. Okay, this QND. What you really need is a quantum non-demolition detector that detects when a photon goes through. And in principle, if you have a very nonlinear optical material, you can convert that into a quantum non-demolition detector. So the things that Galen is talking about might be able to do that really quite effectively, and they would then be able to convert any quantum memory, including the one that we have, into a heralded quantum memory, and that will be critical for going forward.
Understood. Thank you, Dr. Kwat. And I think if anyone has any questions, please send your message to Dr. Kwat separately. Thank you.
Thanks, everyone.
Yep. Okay, so before the end, we also like to hear your voice again. So we are also seeking your answers to what hardware development you want to see in the next summit. So please bring the poll to the public. Okay, I think that's all about the day. Before we set you free, please remember to come over tomorrow morning at 8 a.m. We will have some new sessions tomorrow discussing about quantum security, quantum networks, and advances at Cisco Quantum Lab. Thank you.
Have a good night, everyone.
Thanks, Paul.